How you feeling?
Dude, I'm a little bit nervous, man. Have you seen this lineup? This is like what happens if everything that needs to be known about ML ops gets taught today in this conference. And then all of a sudden, nobody needs to go into the ML ops community anymore. Now, I don't have a job. What happens? Like, I'm starting to really think twice about this whole idea of having a conference and having it be this good. That's how I'm feeling.
What's up, everybody? Welcome to another edition of the Apply Conference. I'm so excited to be here. I know what you're probably thinking, and to be honest, I'm thinking the same thing. How did I get invited back? Well, it's a surprise to me too. I'm not sure how I didn't get fired yet, but let's just go with it. I hope that in the next couple days with you all, I don't say anything stupid to make me not get invited back again, because this conference is shaping up to be one of the best conferences ever. Let's just put that on the table right now. I've got all kinds of secrets planned for you. I'm going to take you on a trip throughout my little pueblo that I live in Germany, in between the incredible talks that are happening today and tomorrow. So before we jump into our first guest, the keynote guest of honor, I want to talk to you all about a little something that is happening here. And let's just throw this out there right now. We've got some house cleaning slides that I need to take care of. If you can see, I bumped up the production value this time around, so it looks all kinds of smooth and all kinds of nice. But here's the thing that I want to mention to everybody. If you would like some swag, jump into the photo booth and give us your best pet, your coolest 80s, or vacation escape photos. We're going to be giving away swag all the time during this conference. We've got all kinds of great partners that have helped us along the way to give us swag that you're going to love. Next up, I want to make sure that everyone knows, if you are in New York City or San Francisco, we're doing live events in combination with this virtual event. So if you haven't registered already, you can scan the QR code. I'm going to make it easier for you right now. Check this out. Scan that code right now and register for the event. Next thing that I want to mention while we are on this topic of registering for other things. Oh, here, excuse me. I forgot to mention what you're going to win. There's a little glimpse of the swag bag. Get into the Apply Slack channel. That's where it's all happening. I can see some people already throwing things in there. I've got a little glimpse of what is happening in Slack right now. Let's check it out. You should be able to see some of the cool things that are being posted, and you can check all of that out by going to the Tecton Feast Slack. We will drop a link to that in both of the chats so you can join me and everyone else, our guests of honor, and ask questions to all of the speakers. More about that. And if anyone has any questions, let me know. I'll be in the chats. And last but not least, I have to draw attention to the fact that we've got some hands-on workshops happening today after the event. If you want to get your hands on some code and get your hands dirty, I highly suggest you do that by joining these workshops. So again, scan this QR code real fast. You will be able to register for the 2 workshops that we've got. First one is with Danny Chow. He's talking about Feast and building real-time ML features. And the next one we've got is with the AnyScale crew, and it's bring your models to production with RayServe. Wow, this is great. I'm so excited. I hope you all are excited. I'm going to try and page Mike right now because he is the one that is going to give us the keynote of honor. Mike, you all probably know this guy by now, but this is Mike Del Balso. He's the CEO of Tecton. And as I like to say, one of the reasons why we keep hearing about the word feature store. So Mike, what's going on, dude? Great to have you here. Uh-oh, I don't know if it's on my end or...
My bad.
Wait.
I had my headphones muted. Can you hear me now?
There he is.
Sorry.
This wouldn't be a virtual conference.
Yeah, no, this is live, guys. Welcome everybody, and thanks for the intro, D. This is super cool. It's cool to see, just like I'm just reading the chat on the side, all the different countries people are joining from. Welcome back, folks who've been to Apply before, and welcome to all the new folks. What's Apply about? It's really just about, it's a community conference. It's about people who are doing machine learning in production, building machine learning applications, sharing what works for them, sharing best practices, sharing tips, sharing patterns, all of that kind of stuff. So this is, hopefully there's something that to learn for everybody, something that you can take back to your own teams. And let us know, like give us feedback throughout the conference, after the conference, let us know what's useful, what's not useful. Today, what I want to talk about is something that's very important for every machine learning application, which is a concept I want to talk about called an ML flywheel. So this is kind of like something that I think is pretty important for every team that's putting machine learning into their product. And so let's just talk about just some examples of what kind of machine learning we're focused on. Machine learning that is powering recommendations in your e-commerce website, for example. So here's, this is obvious. This is Amazon. Netflix has a bunch of recommendations that are, movies. That's, a live production ML application that's powering that. If you're in financial services, of course, you're detecting fraud. And so there's a variety of ways in which we want to power our products with machine learning. How do we do that? It's really tough. It's that's kind of like, the reason we're all here is to figure out how to get better and better at this, because it's still really challenging. There are a number of different stages in the life cycle of these projects, right? There's, ideation. That's where we're kind of coming up with the ideas that we want to build. That's where we're designing experiments. Development is when we're actually building this stuff and actually running experiments. Productionization is putting this stuff, actually deploying this stuff, putting it into production, and doing live serving with it. Operation is all about on an ongoing basis. We're not just making one set of predictions. We have to maintain this stuff into production. In production, we have to debug it. We have to be on call, all of that kind of stuff. And so when we look at this, everybody knows, if you're a part of this conference, which parts of this are hard, right? That productionization and operation are the places where we face some real challenges. And this is tough for all ML teams. And today I want to just talk about a concept that is a framework, a mental framework that is really useful to keep in mind as you're developing your ML application to make the productionization and operation a lot easier. And that's this concept of an ML flywheel. But first, machine learning teams. Who are these teams? So the first group of team, first of all, machine learning teams, this is you, right? So you may be in one of these two teams. I'm going to highlight two types of teams. The first is an ML product team. This is someone responsible for building the end ML application. So think about a fraud team, a recommendation team, a pricing team. These teams tend to have, all of the personas, every type of team member all in the same team. The ML engineers, the data scientists, product engineers, and they're reusing a variety of, whatever is provided to them by the data team and the infrastructure team. So data sets and different tools the infra team provides to them, but they're ultimately delivering their recommendations to a product. So this is kind of like a use case team. When a company has a variety of ML product teams, they will build, sometimes they build an ML platform team. And so you may be on the ML platform team. And these teams are responsible for supporting the ML product teams, right? So typically, the ML platform team is kind of centralizing a lot of the engineering efforts that are duplicated across these ML product teams. So it's a lot more concentrated on in engineering here, and they're supporting a variety of they're providing reusable components, a training system, a serving system, et cetera, for the ML product teams, who can then, because they have the engineering support, they can then focus on more of the data science and product specific challenges. But this is a lot of stuff, right? I mean, we're trying to put ML in our products. Look how much complexity there is here, right? There's multiple teams. They have to collaborate. You have to hire different people to do different responsibilities in each team. All of this is just in service of the product. What does the product actually need? Like if you're the web team, the e-commerce web team, and you're just trying to show predictions, what do you care about? You're just trying to get a decision. And so everything, all of this machine learning is kind of just like an implementation detail for the end consuming team, where they just really want this decision. So they're looking to get a decision from the ML teams. And that's really, you can think of it as the ML teams are implementing a reliable and repeatable decision API that's accurate for the product teams. I think this is a good way to think about it. It's kind of it helps you understand. It helps kind of help you keep in mind what you're ultimately providing to the product. And maybe it's not get decision, maybe it's get recommendation, get price, get fraud score, depending on your use case. But ultimately, you're providing one signal, one decision to the product. How is this different than other machine learning use cases? Well, we're focusing on ML infused products, and that means we're making these decisions repeatedly, right? This is not just analyzing a document one-off or doing a one-off scoring type of thing. This is, for every user that comes to the website, we need to score them, and we need to score them today, tomorrow, and forever. And so how do we really make reliably and repeatedly make accurate decisions? That's the kind of the key challenge here, and that's what all of the ML ops stuff is about, is doing this reliably and repeatedly and keeping it accurate. And so, we do this as humans, not through machines, but we just every day do this as humans, right? So, we do this through a typical feedback loop. We do something in the real world. We observe how it went. So we make a decision, we act, we observe how it went. We kind of combine that information with all the other information we know. We update our learnings, we update our model, and then we make another decision. And so, as a quick example, like imagine you're a career basketball player. You don't care just about your performance on one game. You're optimizing for, can I get better and better and be a more valuable basketball player over time? Well, you play one game, you make some shots, you miss some shots. After the game, you go and study the performance in the game. You're watching the tapes. You're combining that with all of your other knowledge. You're learning, practicing, and then you're playing your next game and you're getting better and better. So these great decisions that are repeated require this kind of feedback loop. And every ML application that we're talking about is building this too. So so this is something that you have in your ML application. You have the product, you're trying to deploy, you're making some decisions, you're delivering some predictions to the product, say it's a recommendation, but then somebody, it may not be you, but somebody in your company is logging, has a variety of tooling to log and monitor what actually happened to the customer. Did they click on the item you recommended? And then bringing and then organizing all of that data and organizing all of those logs, turning them into model data sets. And then on the ML side, we start, extracting features, building new models from it, updating our model, and then with that model, excuse me, and those features, then we're building, then we're doing all kinds of online computation to deliver those predictions in real time and update the product and make new decisions, right? And make new predictions. So this loop is not an instant loop. This could be this can take a long time, this loop, but every application has this loop. That's how training data sets get generated, and that's how predictions get made and delivered to the product. So it's my claim in this talk, and this is kind of the whole point of this talk, that this feedback loop is extremely important, and it's very important for you as a machine learning practitioner to be aware of all parts of this loop when you're building your ML application. There's a couple of core parts: collecting the data, organizing this data, learning from it, and then deciding. Great machine learning applications require a great ML flywheel. And we see this when we talk to teams that are very successful with machine learning. They actually are very intentional about this ML flywheel. They're actually they build tools to design and manage this ML flywheel, and they think a lot more about the whole end-to-end loop than individual parts of it. And what we find is that teams that are not so successful with ML, they struggle with this flywheel. They may not realize that, they may not even be thinking about the bottom half of this flywheel in the first place, or they may not realize a lot of the complexity that happens in the decide stage, and be ignoring some of the key infrastructure elements that are part of their ML application, but or that should be considered part of their ML application, but is not thought of as a first-class ML system. So this concept of the ML flywheel is very important. And let's talk about why that is. Teams that have their ML flywheel working, ML just feels natural and easy for them. So, in that world, you have very clear ownership across the whole ML lifecycle. It's the ML, the whole ML application becomes much more debuggable and reliable. And because you know who owns each part of the flywheel, it becomes much easier to move fast. It becomes easier to make decisions, to make changes, and understand the implications of all of these decisions. And then this allows your iteration speed to be much higher, and then that means that your models getting better and more accurate much quicker. There's a compounding effect from the flywheel. Every iteration, the system's getting better, and so in machine learning, we're trying to get as many iterations in as possible so we can compound to the best performance. When it's not working, it's very painful, and most people are in some kind of in-between state, but most people have many elements of the not working part of this flywheel, or sorry, the not working kind of model that I'm showing here. Things go slower and they break more, basically. The iteration speed's much slower. And because you don't know, there's unclear owners for each stage, especially in the bottom half of the loop. It's really hard to make changes. Small changes become really big tasks. I want to add a new feature to my model. Well, that data is not available in my data set, so I need this person over here to log some new data from the product, but I don't actually know who that person is. And so then that's a whole bunch of coordinating across a number of unknown people. That's just a big project for me, and I might not do it. When there are these unclear dependencies, there's a lot more things break, and it's really hard to promise a certain level of reliability. And that just makes it really hard to understand the changes you're making and the impact of them. So we want to have really strong ML flywheels. But why is this hard? Well, there's a ton of, excuse me, there's a ton of tools, right? Everyone has a different stack. There's not just one of these tools. Not everyone's using the same 5 tools, the same 10 tools here. And so what's really needed is a way to make it easy for teams to orchestrate these tools for them to work well together. And so individual teams can go really deep on on individual tools, right? But the challenge for the ML flywheel is having them all work together coherently to support a self-improving ML application, a reliable and repeatable ML application. So what we really need is a way for all the stakeholders, the data scientists and the machine and the engineers, to build and orchestrate their ML and data tools into coherent ML flywheels. So we need a way to organize this stuff into the flywheels very easily. And this requires simple abstractions to define these flywheels and manage the infrastructure and the corresponding artifacts, the data sets and the metrics and the models, all of that, and in a way that fits naturally with the best practice workflows that we have, right? So it should fit into the DevOps workflows for the engineers, fit into the data scientist workflows as well. So now let's kind of look at a specific dimension of these flywheels. Let's look at the data side of things, which is the main kind of like blood flowing through the flywheel. Data flows are at the core of this flywheel. So let's look at some data sets, right? So I have the product, we're making predictions in the product, then we're going to log a variety of things. We're logging some metrics, we're logging which predictions happen, which features were served, which outcomes we observed, so some labels. We're joining all of those data sets together. This is the organized stage. So we're joining them together into feature logs and label data sets. And then when we're building our models, we're potentially extracting new features. We are generating new training data sets. And then online, when we're making at the decide stage, when we're making predictions, there's a variety of different data sets we need. We could be scoring multiple candidates or generating a variety of candidates, extracting features for all of them, scoring them and turning them into predictions. So there's a lot of data sets that need to be managed throughout this, throughout the flywheel. And so this is pretty tricky to do. How do we do that? Well, feature platforms have had a really big impact on part of the flywheel. They've made it pretty easy to manage the data sets, to declaratively define the data flows that happen in the learn and decide stage, and manage all the infrastructure and data sets throughout those stages so far. And let me just kind of like do a little bit of an aside and show what Tekton does to help kind of like make that more concrete. So Tekton makes it really easy for someone to provide a simple declarative feature definition. So on the left side, this is a feature definition. It's just a simple Python file where you define some metadata. So you say some things about, hey, this should serve online. This should serve. This should also be available in our offline feature store. You can say who the owner is, a variety of other metadata, and then you provide your feature definition, your feature transformation. What Tekton does is it takes that Python file and it converts it to a physical implementation. So it's spinning up the right infrastructure. It's setting up the right data schemas on all of them and connecting them all together. It's orchestrating the data flows on that infrastructure and backfilling your features into your offline feature store. So it can be pulled for training data sets. It's loading up the most recent features into the online feature store so it can serve your model at scale in real time. And so this is managing the infrastructure and the artifacts end to end. And that's had a really big impact for that top half of the loop. And this is the kind of like data management that we're looking for the whole loop. So how do we bring these data management patterns to the whole ML flywheel, right? How do we kind of extend that kind of capability to everything? And so there's a couple of things that you should be thinking about when you're putting together when you're coming from the top half of the flywheel and you're trying to really make sure you have a solid story for the whole flywheel. The first thing is kind of simple. It's close the loop. So so that means simply bring this bottom half of the loop into your purview. It doesn't mean you have to be responsible and own all of these things, but know who these people are. Who is the person in your organization that is responsible for logging what happens in the product and delivering that data into the data warehouse? Ultimately, you want some sort of log observation API to make it really easy for you to add a new label that you want to log, a new feature, something like that, some data that could power a feature. So we want to make it really easy to capture observed events. And then we want all of this to be the entire loop to be implemented on top of your cloud data platform. So, you don't want to spin up a whole new data stack to support this. This should all merge in with what your data team is doing today. They're probably using a data lakehouse or a data warehouse in some way, or a data lake, and having all of this be implemented on top of your existing data stack. Second is really having a unified data model throughout the whole ML flywheel. So what we want to have is, the user takes some action in the website. They click on the recommendation, let's say, or they click on the ad, and then we want that to update all of the relevant data sets within the flywheel pretty quickly. So we want that to update our features, our fraud features, let's say, features that are being used for predictions right now. We also want that ad click, maybe that's something that we're predicting. So we want it to update a labels data set and then update a training data set. So there's this element of freshness that we want to have, and we want to have that propagate through all the data sets. And secondly, we need to establish these coherent, compatible data schemas in all elements of the infrastructure throughout the loop. And so that's something that we need to handle as well. And then finally, not every use case is the exact same. And we want to support use case specific architectures. So there's not one size fits all, and not every use case needs the same underlying infrastructure. If you're doing a batch lead scoring model, it's very different than what a real-time recommendation system is going to need. And I'll just show you like an example of some complexity here. This is from Eugene Yan's blog post, a really great blog post about discovery and recommendations. When you're making a prediction for when you're making like real-time recommendations or ranking, there's a lot. It's not just a simple a model service that's just taking in some features and making a prediction. There's a number of steps online that the machine learning application is doing. It's first generating some candidates. It's taking in the query, generating some candidates, then filtering those candidates, then generating features for each of these candidates, then scoring each of those candidates, then doing the ranking based on that. So there's a lot more infrastructure online and that type of use case. And different use cases need different infrastructure here. So, so the point is to make sure that your ML flywheel includes the use case specific architectures, infrastructure that you need as well. And if you don't, then you risk having either using the wrong infrastructure, which will be inefficient, expensive for you, or your flywheel will not be complete. So this is something we're focused on at Tekton. At Tekton, we're focused on building, helping teams build their ML flywheels and helping build a unified management of the data lifecycle for the ML applications. This means simple declarative definitions become managed infrastructure and managed data sets throughout the flywheel. We have use case optimized architectures. All of it is implemented on your data stack, and the point is for it to fit really well into your dev team's workflows. So your DevOps workflows and your data science workflows. But overall, you should be thinking about how to optimize the flywheel for your use case, and why is this important, right? Well, for platform teams, what does this get you? This makes it much easier for you to support more use case teams, more ML product teams with less resources. And that's kind of what all ML platform teams are trying to do. They're just trying to, keep up with demand and support their customers. For the ML product teams, it lets them iterate, build, and deploy faster. There's a lot less glue code. It makes for fewer mistakes. There's a lot less maintenance, so things become a lot more reliable. And you also need fewer people per project. It's just easier to do this work because it makes it much easier to have purview over the whole flywheel. And it gets you much closer to that mythical decision API that I was talking about at first, which is what everybody wants to get to eventually. And this is not just for the recommendations use cases I mentioned, but it's my claim that every ML use case has to be thinking about this. So whether it's fraud detection, pricing, recommendations, we deal with gaming use cases, security, enterprise SaaS, search, ranking. a variety of things that are all implementing this flywheel in one way or another. So I recommend that you think about the flywheel and figure out how it maps to your world as well. We're always around to help out. And then just a quick plug. So I mentioned Tekton. Tekton is an enterprise feature platform. We are a developer platform to make it easy to manage the data sets and run the feature transformations and all of the data flows throughout the ML application. And Feast is a completely open source production feature store. You can get started with that right now. Check out feast.dev. Okay, thank you. I think I got through it in time. So now, okay, so that was ML Flywheel. And now I want to introduce the next speaker. The next speaker is someone who is very special, frankly. He's a very accomplished academic, a very accomplished entrepreneur, executive, and inventor. He's very influential in this space. He's the co-founder, he's the creator of Spark and the co-founder and CTO at Databricks. It's Matei Zaharia. So please welcome him, and I will hand off to Matei. Welcome, Matei.
All right, thanks a lot, Mike. Let me just share my screen here. Great, yeah, thanks everyone for coming to my talk. So I'm going to talk about something happening on the data infrastructure side. It's something that, you know, it's a new kind of system called Lakehouse that a bunch of companies are trying to build. So it's, I think, an interesting component of the data stack that I think over time will become increasingly important. And this is something that we at Databricks started to design and build pretty early on, but many other companies are doing it, as I'll talk about. I think it's actually a natural evolution of a lot of the data management systems we have today. So basically, I'm going to talk about a couple of things. So first of all, I want to argue that a lot of the problems that data and ML engineering faces today, not all of them, but definitely a bunch of them, stem from the complex data architectures that companies are forced to deploy, which involve, lots of different systems that are better at managing, different types of data for different workloads. And often moving and coordinating between these systems is a major problem. So that's the first thing. And because of this, people are looking to simplify the kind of systems you run. And Lakehouse systems are a new design that kind of tries to combine the benefits and use cases of what used to be separate systems before. So in particular, they support data engineering, SQL data warehousing, and machine learning on the same data store. And they're also built, the reason it's called Lakehouse is because they're built on data lake storage, which is low cost and very scalable. So that's basically the outline. So let's start with, what are the problems that people face with data? At Databricks, we work with companies that do a wide range of different things, from sort of simple SQL-based reporting and warehousing to machine learning. And interestingly, we talk with them all the time. We ask them, hey, what do you wish your data platform did? Should it be faster? Should it be more scalable? Should it be cheaper? Whatever. But actually, the top problems that users have with data today tend to be with the data itself. The data quality, first of all, and then timeliness. So if you don't have high quality data going into your application, whether it's simple analytics or machine learning, then you just can't do anything with it. And same thing to some extent with timeliness. If it takes forever to get the new data for you to look at, it's a big problem. So we're not the only ones to see this. Actually, quite a few surveys of the industry show this. For example, here's a survey of data analysts from Fivetran. Basically, they found that 60% of them reported data quality as a top challenge, and 86% of them had to use stale data, with a lot of it being more than 2 months old. And this is just because it takes a long time for data to make it through the system where they can actually do analysis. And also, all of them basically had unreliable data sources. And the same thing is true with data scientists. If you look at where they spend their time, there's a lot of work on understanding data and, of course, on building the infrastructure to run their data and ML pipeline operationally, which, is a lot of which is covered in this conference. So I want to argue that, even though getting high quality and timely data is intrinsically hard, some of it is a problem of our own making because of the way that data stacks look today. And it's basically for historical reasons. It doesn't have to be that way for a technical reason today. So let's look at the history of data management systems for analytical data. So this space kind of started in the 1980s with data warehouses. And back at that time, companies had what were called operational databases. So they had these live applications that would do transactions, like say the booking system for an airline or something like that. But they wanted, as more and more computer applications were deployed, they wanted to analyze what's happening. So people designed this other type of database called the data warehouse that's optimized for analytics over large amounts of historical data. And the idea was you would take your operational data stores, you would extract, transform, and load or ETL data into them regularly. And then in this warehouse, you would see data from lots of applications together, and it will be optimized to do efficient reporting. And this is a full SQL database with a lot of powerful management features as well as performance optimizations. So things like schemas, indexes, ACID transactions, maybe multi-version control, so you can look at an old version of your table and stuff like that. So it's a very rich, easy to use environment. And this worked really well. It's a huge industry, continues to this day. In the 2010s, though, some new problems started to come up for this pattern, which are basically three problems. The first one was that the data warehouses were very SQL and table-centric, mostly designed for, historical, but sort of smaller scale data compared to what we have today. And they didn't support unstructured and semi-structured data, which was becoming increasingly common. The second one is that the cost to store large data sets was quite high because, again, they were just designed for a smaller data volume from these business events. And then the third one was that because the only interface is SQL, they can't easily support data science and machine learning. So as a result, we got a second type of system that probably like almost everyone in the conference uses, which is called a data lake. So this is basically low-cost storage that is designed to just store raw data in whatever format you want. For example, Amazon S3 or Hadoop file system for on-premise or like Azure Data Lake storage or all these other cloud storage systems. And in this space, so basically it's very easy to just upload your data, whatever format and type it is, and just store it in there and then build applications downstream from it. One of the other things that was really different with data lakes is that because they came out of open source, they were designed mostly around open data formats like Apache Parquet, which means that the data is actually directly accessible to lots of engines once you store it in there. And as a result, we have this huge ecosystem of tools on top that know how to read these data lake formats like Parquet and can work on top of it. In fact, even Apache Spark started that way. When I started it, there were a few systems like Hadoop that were widely used, and there was all this data in open formats, and it allowed me to write an engine that is better at certain things and just have it work on people's existing data, which is great for everyone involved. And with this data lake, though, you have very limited management features. It's just a file system, basically, or actually even weaker semantics than a file system. So you still have to have jobs that load the data into other systems for more powerful management and performance features. So for example, you would still run your data warehouse and you would just load a subset of your data into it regularly. And today, these data lakes in most enterprises are where the vast majority of bytes are stored. It's not necessarily where most users query the data, but that's where most of their data lands and is stored. Okay, So what's the problem? This looks like, we've kind of solved everything. We have a low cost, cheap storage tier, the data lake, and we can still run our existing stuff on top. So yeah, it definitely, it does let you run all these things, but the problem is that it's complex to use. And in particular, it's a lot more complex than the single warehouse you had in the 1980s, where as soon as an event happens in your operational system, it just gets loaded into there, and analysts can immediately query it and can start analyzing whatever happened. Okay, so a few different problems happen. So the first one is that data reliability suffers. You've got at least these two different storage systems, and in practice, you might have even more things here, like say a Kafka message bus or something like that. And they have slightly different semantics, maybe different dialects of SQL, different data types in their tables and so on. And you have all these jobs that are supposed to move data between them. So when an event gets copied, say, from the data lake to the data warehouse, there is a chance that something goes wrong and actually it's corrupted, or that one of those jobs goes down or has a bug. Okay. Second problem is that timeliness suffers. You have all these extra ETL steps that need to get the data in there, or even worse, if there's no pipeline for some new data set, you have to wait for someone to build a pipeline before you can analyze it. And then, of course, you also have high costs because you're duplicating some of your data, and you've got these extra jobs that are running that are basically just transcoding from one format to another, and copying bytes from one system to another. They cost a lot, and they're not really doing something useful. You're just spending sort of cloud credits on that. Okay. So that's where Lakehouse systems come in. The idea here is to implement the data warehouse management and performance features, and in general, other features of what are today separate storage systems directly on top of these data lakes and open data formats. And the idea is, there's very little sort of technical reason why you couldn't have, say, great data warehouse performance backed by S3, or a great kind of message bus system or things like that. In fact, a lot of the modern systems already use cloud storage underneath. So we want to do that with these open formats and give people ideally a single tier in their data architecture that all these workloads can run against. So if that works out, it would look a little bit like this. You'd have your data lake at the bottom. It's still something like Amazon S3. And on top of it, you'd have this interface that is a management and performance layer that gives callers sort of higher level abstractions on top, like say transactions or versioning. And then on top of this, you can have a few interfaces. You can have SQL for everything that talks SQL. And you can also have direct access to the files, because then these open formats for high throughput systems, like all the machine learning engines that I showed, or things like Apache Spark, or whatever the next great engine that someone designs is, it can just directly read those files at high performance. So this, looks nice. It's always nice to have just a single layer. But the question is, can we actually do it? Can you get great performance? Can you get governance and management features that are, the reasons we have these different systems today? So I'm going to talk about three kind of areas of work that are enabling this to work. And these are metadata layers on data lakes, which add transactions, governance, and other management features. Lakehouse engine designs, so in particular for SQL, which is where there's been the most investment in performance in kind of these standalone systems. Can you actually get great performance on today's open formats? And then I'll talk about how the ML stack interfaces with these, which is also pretty interesting because you can take advantage of all the optimizations that are done in the other layers. So I'll talk about each of these in order. Okay, so metadata layers. So this is kind of the key technology that's enabling, Lakehouse in a sense to be possible. Basically, these are these layers on top of your raw files that try to provide richer semantics. And quite a few companies have developed these at roughly the same time, basically around 2016, 2017. So at Databricks, we developed Delta Lake. There's also Apache Iceberg, which started at Netflix, and Apache Hudi from Uber. And now actually a lot of the cloud vendors are also offering kind of cloud services that are sort of proprietary, but try to do some of these same things. And the idea in these is actually quite simple. Basically, you've got a collection of files. That's what the low-level storage system is, but you want some higher-level interface on top. And these systems basically just track which files are part of a table version or a data set, and use that to implement transactions and other functionality, as I'll talk about. And basically, when a client application wants to read, say, a table, they can ask this layer what files are part of this table, and they get a list of files, and then they just directly read those. So it seems really simple, but this layer of indirection adds a lot of opportunities for great functionality. So let me just talk about one of the things, which is transactions. So normally, if you're using a data lake, one of the problems with that, one of the reasons you can't just run all your workloads against it, is that there's no isolation of workloads, of concurrent workloads. So for example, let's say we're storing a table, which is a bunch of events. It's a bunch of files. It looks nice. If everyone just reads the table, that's great. Then they can all read it in parallel, and it's very fast, and everything's great. But sometimes you'll have workloads that try to modify the table. For example, you'll have someone who tries to delete all the events about a specific customer. And when that happens, you have to modify or add and remove individual files. And there's no way to do this atomically for the whole table. So for example, you might need to take file 1 and rewrite it into file 1b, and then delete file 1. And you might need to do the same thing for file 3, because there are events in there. And of course, if you have a job that's running and doing this, different things can go wrong. So for example, if this is in the middle of running and it's updated file 1, but not file 3, some job might go in and see a broken state of the table where some records have changed, or worse, it sees 1 and 1b at the same time, and so it sees duplicate data. And of course, if your job that does the update crashes, that's also a problem, because then you've left the table in that corrupt state forever. So how do lakehouse systems solve this? Basically, it's this layer of indirection that keeps track of individual table versions as a concept. And in Delta Lake, just as an example, it does that using a log of transactions or changes to the table, and the log itself is stored in S3 or in your cloud storage system. So you don't actually need to run a separate service to do this. In fact, this is as highly available as S3. As long as S3 is up and you can read and write to it, you can do ACID transactions on your table. So this is a simplified version. Actually, the log format's quite a bit more optimized than this, but you can think of each entry in the log as telling you which files are part of that version of the table. So for example, version 2 of the table is file 1, 2, and 3. And then when you do an update like this one with deleting stuff, you can have a job that's running to do the update. It can rewrite a bunch of files, and everything's fine because readers look at the log and they only look at file 1, 2, and 3. They ignore these extra files because they're not part of any committed version yet. And then when you're done with your update, you can atomically add a new log file. There's various ways of doing this in each cloud that says, hey, version 3 of the table is now all these updated files. And so readers who look at this after you do this will see everything updated together. You'll never get this inconsistent version. So very, very simple idea, but now you can actually have concurrent users and workloads and do all kinds of management operations on your data directly in the data lake. You don't need to move to a SQL warehouse to do that. And based on this simple sort of idea, we've also built quite a few other rich management features in Delta Lake. So for example, you automatically get multi-version sort of tracking with this design. So you can easily look at the log and say, what did the table look like, say, a week ago, and read that version of it. So that's really nice. You can also easily do zero-copy clones of the table. You can create a new table, say for development, whose log starts by pointing to files in a previous table, and then you can just remember the changes. So it's very cheap. It's a little bit like forking something in Git, where you can just quickly develop on a changed version of it. Of course, you see its whole history, so you can see who's been working with it from the log. And then another cool thing that's pretty widely used is since we have this log, you can view each table as a stream of changes. And you can actually use it, basically, you can use a Delta table as a message bus. So you don't need to run something like Kafka if you just want in-order delivery of some events. Of course, since this is based on S3, the latency, isn't as good as Kafka. So definitely there are workloads where you would need a separate message bus, but for a lot of things, you can actually just have your table, be a streaming input source for something else and get all the changes. Okay, and this is an idea that's that's become quite widely used. So Delta Lake itself, I think, is the most widely used system in this space. It's used at thousands of companies already to manage exabytes of data. One kind of really striking thing for me was that on Databricks, we went from 0% to more than 70% of our write workloads going into Delta Lake since we launched this in 2017. That's very unusual for a new storage format. That's usually one of the things it takes a long time for people to adopt. And there's also really broad industry support with all these tools that can integrate with it. So I think this type of layer is definitely here to stay for data lakes, and it kind of strictly makes them better. Now, this is great for, okay, we made data lakes better in terms of management, but it's still not enough to replace the separate systems we have today. And one of the core issues people worry about is performance, because with data warehouses, you've got these, basically 40 years of engineering into building these bespoke systems with co-design, storage, and compute and query planning that can do analytical queries. So can you get performance SQL on a data lake? And it might seem that it's hard because you're stuck with these open formats. Maybe it's harder to change them. So maybe you can't implement all the optimizations in a warehouse. But it turns out that, first of all, today's open source columnar formats are pretty good, and they are evolving to meet new needs over time. And second, you can also use the lakehouse design with the layers I showed before to implement a lot of optimizations on the side that improve performance. So for example, you can keep auxiliary data structures like statistics that are updated with each transaction, so they're always consistent. You can organize the data within each file. You can reorder the data to minimize I/O. You can do caching, and you can also design engines, like a data warehouse engine, but for today's open formats that actually perform pretty well. And these things together help with both cold and hot data. So all the things you do on storage let you minimize the amount of bytes you have to scan. And then once you do scan those bytes, you can do a lot of things in memory or in the CPU to make the execution faster. So a bunch of companies are building engines for these. I'll talk about what we are building at Databricks with Photon, which is our engine. It's basically a version of Spark that is faster, that uses modern kind of warehouse techniques. So I'll just briefly show how some of these things work. So one of the optimizations is auxiliary data structures, right? So even if your base data is in an open format like Parquet, you can also build many data structures on the side that speed up queries. And with something like Delta Lake, you can maintain them with your transactions, so they're always up to date. So for example, one of the things we do in Delta Lake is called min-max zone map. So for each Parquet file, we have statistics about each column, the minimum and maximum in it. And normally Parquet actually has these inside the file itself. But the problem is you have to do a lot of IOs to look at the footer of each file and figure out its statistics and decide whether it's relevant to your query. So you have, if you have 1 million files, you have to do 1 million IOs to see what's in them. With Delta Lake, we just take these and we basically store them in the Delta table log. And 1 million of these entries, especially once you compress them, will just be a few megabytes. So it's super cheap store that stuff in there. But the cool thing is that they're now all together in one place. So when you read your snapshot of the table, you read all the statistics, and you can immediately narrow down to which files are relevant for a specific query. And you only have to do one I/O. It takes a few hundred milliseconds to do that with S3 instead of millions of them. So just to show you how you use these, basically when you get a query with conditions in it, you can eliminate a lot of files based on their min-max statistics to know they're not relevant to the query. So in this one, actually only the last file could have records in the range we care about. And then when you run the query, you can just read that one file. Okay, so that's one optimization. Another thing that we do is optimizing the data layout within each file. So if you know which records will be accessed, are likely to be accessed together, you can sort your files and sort the records inside them to keep those close together to minimize I/O. And there are a lot of techniques here that you can use. We implemented a bunch of them, including space filling curves that let you cluster the records in a file along 2 dimensions and have locality in both. So this means if you query on a range of each of those dimensions, you have to read a lot less than the whole file. So that's this one. And of course, on top of these systems, you can do caching. We implement caching on top of solid state disks, and we have this special sort of half decompressed format that's actually faster than just putting Parquet on an SSD. And then in the engine itself, you can implement all kinds of work, like for example, using vector instructions on the CPU. And we've done that in an engine that basically is compatible with Apache Spark. So we're running a lot faster than the open source Java-based engines for SQL workloads. So, and it turns out with, at least so far, like the Parquet format hasn't really been a limitation. It's a well-designed format, and we can match the performance of of data warehouses with custom formats using this open one. So yeah, so if you put all this together, you actually get pretty competitive systems. We've been running benchmarks against a lot of the popular cloud data warehouses. We have a bunch of these. This is one we posted about last year, where you can see on a pure data warehousing benchmark, TPCDS, that like ships with every data warehouse in the industry, we're actually doing quite a bit faster than a dedicated system that does that. So at least today, I don't think there's any technical evidence that like you'd get better performance or that you shouldn't use these open formats and use Lakehouse if you want the best data warehousing performance. Okay. And then the final thing I'll talk about is how this ties to machine learning and the interesting things you can do with Lakehouse for that. So with machine learning today, as you saw in a lot of talks, you have the challenge of how to set up your data pipelines and make them reliable. And it's pretty hard because you'll probably want data from a lot of different systems in your company. You might have some data in your data lake. You might also have stuff in your data warehouse. And with the data warehouse specifically, it's kind of painful to do machine learning with it, at least with large amounts of data, because ML workloads need to basically read entire tables or entire, large data sets. And data warehouses with the SQL interfaces are mainly designed for sort of smaller queries that extract a small subset of the data. So just reading the data through SQL from these is often really slow. Basically it has to be transcoded from the internal format to some open format that the ML engine understands. And you have to have a bunch of nodes doing that. Now, you could decide to not read directly from the warehouse. You could export the data to a data lake, but then this is yet another ETL step that could go wrong, that could break your ML pipeline if this has gone wrong before you even get to look at the data and run ML on it. And you could also try to keep your production data sets in both the data warehouse and lake, but that's even more complex, and more things can go wrong as you're then trying to run this application. So with the Lakehouse, first of all, just by having a single storage tier, it makes things quite a bit simpler. The ML frameworks, many of them can already support reading Parquet. And as long as you have a small sort of shim layer that tells them which files to read, they can just integrate with the transaction management and other features in the Lakehouse. And then they can just read those files in parallel directly from cloud storage without having some other node in between that's translating them into a different format. And you can also use engines like Spark, which have declarative APIs that can do query optimization. So that's pretty nice. But then the other cool thing is you get these built-in features like data versioning, streaming, and so on that help with the ML lifecycle. So for example, in ML Flow, we automatically track which version of a table you used in an experiment, so you can get back that same data. So a lot of these systems are now integrating with kind of leading ML platforms like Feast, Tecton, and ML Flow. All of them can work with Delta Lake, for example. So it's an exciting area, and there's a lot more to be done here. But I think having a powerful data management system is really important for doing ML. So that's mostly what I wanted to talk about. I'll skip this, just showing how things work. But yeah, if there's one thing to take away, it's that today's world with many separate data systems, I think doesn't have to be that way for a technical reason. It's that way for historical reasons because of how these evolved. And I think over time, we'll converge to ways to do very high quality, SQL workloads, data engineering, ML, and so on the same system that is based on low cost cloud storage. And that's what we're trying to do with Lakehouse systems. And I think it's something you'll start seeing throughout the industry. Thanks.
Awesome stuff, Matei. Dude. Legendary. I appreciate you coming on here and teaching us about this. Do you got a few minutes for some questions?
Sure. Yeah, if you'd like. Yeah.
All right. So first one up is about assessing data quality. Mm-hmm. How do you assess data quality and what makes it good or reliable data?
Yeah, that's a great question. Yeah, it kind of, it definitely depends on your setting. I think, so there are different approaches to doing it. Like one approach is to have automated tests that run against it, like checking, is a large fraction of the data null and so on, or are these values out of range? And with the systems I showed, you can run those tests and you can actually roll back to an old table version if you see a problem, or you can decide, not to push a change into the production version of your table. But there are quite a few other problems because you might have records that look okay where there's still some kind of bug. So I think you have to periodically have sort of end-to-end sanity checks that see, okay, these tables consistent with each other? If I put in some records to my pipeline, what comes out at the other end, and so on. I do think the biggest thing is to try to have a simple architecture with fewer moving pieces. Yeah.
Excellent. Someone was asking about the differences between Snowpark and Databricks.
Yeah, I think there's a significant difference. So Snowpark is a proprietary API for running Python and Java workloads on Snowflake, and so it means you have to code up your application against that. You can't use like any existing application that was built on Spark, for example, despite its name. Databricks is mainly focused on running open source engines and supporting the open source APIs. So, for example, the stuff I showed with Photon, we took great care to make sure that it's just a version of Spark. So, like, people can take any job written against the open source Spark API and run it on there. And same thing for machine learning. You can run TensorFlow, PyTorch, Horvath for distributed learning, XGBoost distributed, and so on. So we are just focused on supporting open APIs and designing platforms around them that make it better or faster to run those. Yeah,
makes sense. All right. So in case anyone is wondering where I'm getting these questions from, if you go to Slack, the Apply conference channel, throw your question there and I will ask Matei or any of the future speakers too. So next up, how are aggregations and addition of business logic handled in the case of the Lakehouse? Does that part look the same if it were a data warehouse?
Yeah, you definitely need to do work to create downstream tables from the raw data you get. So you can't just use the raw data. So we've seen people use this pattern where they classify tables into bronze, silver, and gold. So bronze is the raw data that comes in. Silver, you have pipelines that they often use the streaming mechanism I talked about, where you can listen to changes in a table and then update some downstream thing based on that. And then they have a final tier called gold, which is things that they're pretty sure are vetted and very easy for everyone to consume. But one of the really cool things is if you're an analyst or a data scientist coming in there, and 99% of what you need is in the gold tables, but there's some fields that aren't in there or some aggregations that aren't, you can still go and query the other tables in the same system and bring in all that stuff. So you can have access to everything. You don't need to, let's say if you're working in like Snowflake all the time as your warehouse, but there's some stuff that isn't in there yet, you have to learn and get access to a whole different system to then query, query S3. So with the one tier, you avoid that. Yeah.
Okay. All right. So next up, how do you support Databricks for on-prem installations in hybrid cloud?
Yeah, great question. Yeah, we don't have a Databricks on-prem product, but since it's only running these open source engines and formats, you can run Spark on-prem, you can run Delta Lake on-prem with HDFS. So quite a few people use that and then deploy workloads either in the cloud or on-prem in a similar way. So that's one of the ways. Yeah.
All right, I think we got time for one more. So if someone wants to drop it in last minute, while I'm waiting because I see somebody's typing in Slack, I really want to know, because I know you've got the Data and AI Summit coming up, and you're always thinking ahead. I think a lot of us look at you as quite a visionary in the space. What are some big things that you think need to happen in the next year in this space?
Mm-hmm. Yeah, I mean, there's a lot of stuff I think to still figure out in the ML space, and it's really cool to see that ideas that used to be only at very advanced tech companies, such as feature platforms, are now gaining wide adoption. So I think there's a lot to do just to figure out a good set of concepts that you can tie together that bridge between data teams and machine learning teams. And I think there's still a lot to figure out there. I don't know. Let's see. I think the other kind of interesting trend that I think we're starting to see with these feature platforms too is the need to do more stuff in real time. I think that's also really cool, and that's one of the things that we're investing in. We're seeing a lot of growth in with Spark streaming engine, for example. So I think that's going to happen more and more, but I think that's a slower rate of evolution overall than the ML platform one. Yeah.
Excellent point. The bridging the gap between the data and ML. I like that. So last question from Ash. Have you seen companies adopt data mesh architecture as opposed to data platforms?
Yeah, great question. We have seen that. And one of the cool things with the cloud now is, now that most of your storage is in systems like S3, you could have different teams managing the storage and still run computations efficiently over all of it, because it's all in the same data center, right? Even if they have different AWS accounts or whatever, they're in the same region, it's in the same place. So it actually makes it easier to have this decentralized ownership of data. And it's one of the things we've been trying to support. I actually work a lot on the governance and data sharing products at Databricks, and we definitely see this pattern of distributed ownership. So yeah.
Excellent, man. Well, I appreciate you coming on here. That's all we've got for now with Matei live, but he will be in Slack. I know there's a few more questions for you, so feel free to take the conversation over there. Matei, this was awesome, dude. I really appreciate it.
Great. Thanks a lot. Yeah.
We're going to keep cruising. Next up, we've got another huge name, Chip is coming to, as Matei was talking about, this whole movement towards real time. Chip has been talking about it quite a bit. I don't think she needs any introduction, but I'm going to do it anyway, see if I can give her some justice. I mean, it's incredible the things that she's been able to do. She's written fiction books. She also just came out with an amazing machine learning MLOps book that if you have not seen it, go get your hands on it. We'll leave a link to it in Slack. And she's a speaker at the ML Systems course. I mean, she's a CEO. Chip, I don't know how you have all the time to do all of this. It's incredible to see the amount of effort and just trailblazing that you're doing in this space. And I'm going to hand it over to you because I really want to hear what you got to say today.
Thank you so much for the really kind introductions, Dee. I have been wanting to chat with you for a while, so it's really exciting to finally see you. And I'm sad it's not in person. Otherwise, I would have loved to grab coffee. So I'm gonna start my slide, and I hope that you can see my screen. Can you see my screen?
Yep. Yeah.
Okay, so yeah, my name is Chip. I'm a co-founder of a startup called Claypot AI, which is a machine learning platform for real-time machine learning. And I also teach machine learning system design at Stanford. I usually start the talk with, I'm very excited to be here, but I'm so a bit nervous to go after Matei because like Dee said, he is a visionary in this space. And I don't think there's no way I'm gonna top his talk. So please be patient with me. So anyone here is from Vietnam? I'm very hopeful I ask every talk, but I'm not sure if anyone here, but usually I never see anyone from Vietnam. Okay, I guess no one then. Okay, so yes, okay, finally. Thanks for coming. I know that's pretty late in Vietnam. Hey, Lin. So today I'm going to talk about machine learning platform for online predictions and continual learning. So a trend that we have, I have noticed in the last few years is that the industry is moving toward online predictions and continual learning. And one common denominator for both of them are that they both require good monitoring solutions. So in this talk, ideally, we want to cover on 3 topics: online predictions, monitoring, and continual learning. But because of the limited time, so I will try to cover the first 2 topics first. And if we have time, we're gonna go over continual learning. And I will find events like this a little bit hard to give talks to because I don't have a good sense of what people are interested in or what you have already seen a lot. So please feel free to ask questions or stop me at any point. And I know that I have an accent, so sometimes I speak really fast, so feel free to tell me to slow down as well. Nice, I see a lot of people from Vietnam here. Okay, so the first is online predictions. I believe that at this point, people have pretty much know the difference. A lot of people are very much familiar with the discussions between batch predictions and online predictions. So batch prediction is when predictions are computed periodically, maybe once a day. So before requests arrive. And online predictions is when predictions are computed on demand after prediction requests arrive. So batch predictions is the problem with batch prediction is that it's non-adaptive. So because the predictions are computed before requests arrive, you can't take into account relevant information to make relevant predictions, and it shows a lot in tasks like recommended systems or dynamic pricing. And another problem with batch prediction is the cost. So when you generate batch predictions, you tend to generate predictions for all the possible requests out there. So we just talked to a company recently, and they have about 3 million users. So they generate predictions for these 3 million users daily. However, they only have only a small fraction of these users log into the platform daily. So which means that's 99% of their computed predictions actually not used, which is a huge waste of compute power. So online predictions, the big challenge is the latency, because predictions are computed after requests. So you would need a machine learning model that can return prediction requests very fast because users don't like waiting. So batch predictions, the workflows look like this. So good generate predictions offline in batch. And a lot of I think for a lot of companies load these pre-computed predictions into a key value store like DynamoDB or Redis to reduce the latency at prediction time. And when as applications, when a prediction request arrive, they're gonna fetch the pre-computed predictions. So not all use cases need online predictions. So batch prediction works pretty well for a lot of tasks like churn predictions or user lifetime value. So like if you want to like predict what users are gonna leave the platform, it can pretty run that like once a month or once a week. It's fine. So with online predictions, there are two different types of online predictions. So the first is that you do online predictions, but with batch features. So batch features are features that are computed offline, for example, like product embeddings. So imagine that you want to do session-based recommender systems. So you might want to look into all the products that a user has seen in the last half an hour, and so based on the items that users have seen in the last half an hour, you want to get the embeddings for these items, and you want to like add them together to create a feature embedding, and then you generate the recommended items based on these embeddings, pre-computed embeddings. So the embeddings are usually computed beforehand and load into a key value store, so that you reduce the latency at prediction time. So another level of like online predictions is when you want to do it with online features. So in the case of embeddings, you can compute embeddings offline. However, for tasks, for a lot of tasks, you might want to get features that's computed online. So for example, if you want to calculate to see like what products should be trending right now, you might want to look into the number of views that own products have in the last 30 minutes. So to compute the number of views a product has in the last 30 minutes, you want to compute that features, just its features online. So the workflow is that like you compute batch features like embedding offline, you load that into a key value store, and then at prediction time, you will look into like what features are needed for this specific request, and then if it's like a batch features, you fetch it from key value store, and if it's online features, you compute that from the recent click stream. So you can either compute that using a Lambda functions, like you can have a microservices running a Lambda function to compute the number of views a product has in the last 30 minutes. However, Lambda has running it that way has a lot of problems. So one problem is that Lambda functions is stateless. I want to check in like how is everyone doing? I haven't seen. Yeah. Okay, good. So yeah. So I will have a difficult time trying to understand like how the audience receives the talk because I can't see your faces. So if the topic is like slow, boring, you can move past it. I have a lot of slides here. Cool, thank you. So the problem, so like you set up, so like to compute online features, some companies we see that they set up a Lambda microservice. So they just compute the recent number of views. So the problem with Lambda is that it's not stateful. So it's stateless. So like if you want to compute the number of views an item has in the last 30 minutes, you will need so like, and if the views come in like every minute, you one way is that like every time you want a number of views in the last 30 minutes, you just like go over the last 30 minutes. But you might want to just like every minute, you just want to update, calculate the number of views in the last minute, and then combine it with the number of views in the last 29 minutes. So like with Lambda function, we need to set up an external database to store the state of the computations. So a much more efficient way could be like to use stream computations engines such as Flink, and also and Matei just mentions that Databricks also have Spark streaming. So yeah, so that's what for online features. So feature service here. So you can see that the difference from batch prediction to online prediction with batch features and online prediction with online features. The key difference is in the feature service. And feature service, a lot of companies we talked recently are looking into what is called like feature store. So for this to work, a feature store or like feature service, we need certain properties. So one is that it needs to be able to connect to different data sources, like both offline, like batch data sources, like data warehouse, Snowflake, BigQuery, and streaming data sources like Kafka, Kinesis. So yes, that's one requirement for feature store is a dual data, like multiple data source connections. And another is that it will need to be able to store feature definitions. So for example, like if you want to specify that, oh, we want the number of views of a product has in the last 30 minutes, then you might want to, so you need to define that query somehow. It can either be in SQL or in like pandas or like data frames, or it can also be in like PySpark. So the feature store will need to be able to like store these definitions and compute that, which brings us to the next requirements of the feature store is feature computations. So they have feature definitions and have data source. So you want to apply these feature definitions to the data sources to get the computed features. So in a lot of feature stores that I have seen, they're very light on feature computations, and especially on the streaming part, because streaming is hard. And I see the feature store tend to leverage tools like Spark streaming, which I think is a great addition to Spark. But I think there is still a lot to be desired about Spark streaming. And but luckily there have been a lot of exciting tools that allow us to do stream computations very efficiently, like vectorized, materialized, and decodable. Oof, did somebody say burn? No, I mean, Spark streaming is great. I have a lot of respect for Databricks. It's an amazing company. But Databricks does come from a batch computations background, so it definitely takes time. So it can definitely become a great streaming computation engine. Oh gosh, I hope that Matei is not in the talk and that doesn't hit me. Okay, so another is that like after you compute these features, you might want to persist the features. You might want to persist the computed features for either reusing for the next predictions request, because like sometimes you might different prediction requests might want to access the same feature, or different models might want to have the same features. So if you persist certain computed features, you can reuse them for future prediction requests, or you can also reuse them for when you want to retrain the model on new data. So so in this case, if you want to persist computed features, then feature store is more like a data mart, like more database. It's a store like pre-computed features. And I think like another thing that people have been talking about a lot is to ensure the consistency between training and serving for predictions. So here we have this diagram for online predictions. So online prediction is so in this so batch features is pretty consistent between you can do it predict you can use the same batch pipeline for both for batch features in serving and training. However, for the online features, that's where it gets tricky. So in online features, during predictions, we might want to use stream computations to get the features. But when training for the same features, we might want to use a batch process. So a lot of a big promise of the modern feature store is to help you ensure the consistency of the features during predictions and also during training. So like I think it's a very difficult topic, because like if you compute the training features in the feature store, then yes, it can reuse the same feature definitions and then go back in time to generate historical features. But if you generate training features outside feature store, then it can be very hard to ensure the consistency. And one last point that I want to talk about on the feature store or a feature service is that when we generate batch features offline, like for example, after we generate embeddings offline, we might want to we might be able to do a lot of tests to make sure that the embeddings make sense. But if we do online generate online features online, and we reuse that immediately for predictions, then we need to have some way to ensure that these online features have good quality, and they are not just like, just not something like breaks in the pipeline that lead to the wrong features. So that's the last aspect of the feature store functionality, is feature monitoring, to ensure that every feature generated in the feature store, the feature service, will be usable and like correct or like within certain expectations. So I think for this key functionality of feature store, I think that's like the things in blue, that's what I believe that feature stores today are doing really well, like connecting to different data sources, storing feature definitions, or like persisting computed features. However, I think there's still a lot of room for like other functionality, like feature computations, or like transferring feature consistency, and like feature monitoring. And it's very, very likely that a lot of modern feature store like Tekton will. I think a lot of feature store are like actually working on this, and I'm very excited to see where the feature stores are gonna go. Okay, so we talk about feature of monitoring, which brings us to the next topic of monitoring. So the first question, I think we most of our time, so I'm gonna go through this quickly. So the first question we need to address when talking about monitoring is what to monitor. So what companies really care about is when they have a machine learning model is business metrics, like F1 accuracy, click-through rate. So however, like it's pretty hard to monitor the business metrics directly, because usually you would need a lot of like labels or feedback from users, and not every task has labels or feedback from users immediately that we can use to monitor the models. So like one way to get around it is that like companies try to collect as much feedback as possible. So for example, for e-commerce, you can leverage users' feedback to like as a proxy to see how the models is performing. So for example, like if you do recommended systems, you might want to look into user feedback like click, or like adding an item to cart, or like whether user buy an item, or like whether they return an item. So like this different feedback through the user's journeys have different properties. So for example, click-through rate, clicks is a lot more, so users click on items a lot. So that means that clicks are very dense, feedback. However, click is not a very strong signal. So you might not have a lot of clicks, but like a user clicking on an item doesn't mean that the users realize that item. However, like for purchase, like buying item is a lot more sparse, because like it doesn't happen a lot. However, it's a very strong signal. So like companies will have to decide on like what kind of feedback that they want to actually monitor. And another thing when monitor business metrics is that you care about the fine-grained evaluations. Like one overall metrics like accuracy or F1 on own data is not going to be good enough. And you want to know like how a model is performing for like different subsets of data. So for example, like if so first of all, what we want to know whether the model is performing well, like equally well across owned demographics, or like if there's certain like, or if slightly change for a subgroup of users, then there might be something interesting happening there. It can be something very bad, like some biases in the pipeline. So because of the lack of labels and predictions, so a lot of monitoring tools turn to monitor proxies like predictions and features. So the assumption here is that shift in predictions and feature distributions will also lead to decreased business metrics. So in this case, monitoring now becomes a problem of detecting distribution shift. So that leads us to the next question, like how do we detect data distribution shift? So usually, like if we have like two populations, we want to determine whether these two populations come from the same distributions. Or the alternate question is like, how do we determine that the two distributions are different? So the two distributions might be, one of them might be the distributions of training data, and another distribution might be the prediction during production data. Or it can be like one distribution might be the distribution from yesterday, and another distribution is the distribution from today. So the base distributions that we compare the other distribution to is called the source distributions, and the distribution that we care about to see whether it has deviate from the source distribution is called the target distribution. So there are two main approaches to detect the data distribution shifts. One is to compare by comparing statistics, and another is by using two sample hypothesis testing, such as like case test or like MMT. So compare statistic means that so it would compare certain statistics of the source distributions like mean, variance, min, max, and you see this like, and you also compare compute the same statistics of the target distributions, and you see that if the statistics have diverged from the target distributions to the source distribution, then you can say that, oh, the distributions have shifted. Two sample hypothesis test is more involved. So the problem with statistic approach is that it's very distribution dependent. So so for example, like you should only compute statistics that are meaningful to your distributions. So for example, if your distribution is a normal distribution, then means and variance can be very helpful. But if the distribution is something like a long tail distribution, then it's probably not a very mean or variance. It's not going to be a good statistic. And another problem with statistic comparisons approach is that it's inconclusive. So like if the mean or variance or like statistics have shifted from the source distribution to the target distribution, then we can say that the distribution has shifted. However, if the statistics are still the same, then we can't really say that the distribution has not shifted. So I hope that makes sense. And the two sample hypothesis test is pretty common. However, like the vast majority of hypothesis tests today can only work with like low dimensional data. So usually like to compute the hypothesis test, so it doesn't work for high dimensional data like embeddings. So people usually tend to first perform dimensional reductions on high dimensional data before they switch, before they apply hypothesis test. So when talking about detecting shift, we have to, it's important to note that like not all shifts are equal. Some shifts are easier to detect than other. So for example, sudden shift are a lot easier to detect than gradual shift. So imagine we have a distribution that changes like this. So it's very gradual change. So like if you're comparing the data today to data yesterday, you might not see a lot of change and you might think that, oh, there's no shift. But over time, because the shifts are very continual, gradual, like after a week, the shift might have changed significantly, but you might not be able to detect it. Another difference is that spatial shift versus temporal shift. So spatial shift happens when you have like pretty much like new access point. For example, like the users may have new devices. So before they were using the applications on desktop, but now they use applications on mobile phone. And users' behavior on mobile phones are very different from user behaviors on desktop. Or another type of spatial shift is when you have new users. For example, you might launch a new marketing campaign and you suddenly get users from an entirely different demographics that you had before. So now you have like a lot of new users, a lot of users, so like a spatial shift. On the other hand, temporal shift is when you have the same users, same device, but behaviors that change over time. So so temporal shift are like really tricky to detect. So for temporal shift, is time window scale really matter a lot. So consider we have a distribution that looks like this, like across like 15 days, right? And we want to use a day 15 as a target distribution. So if we just look at the last, last 6 days as the source distribution, then we see that, oh, day 15 looks significantly different from day 9 to day 14, then it's a shift. However, if we use the day 1 to day 14 as a source distribution, then we can see that, oh, day 15 is the spike and day 15 is just like expected. So this is not a distribution shift. Yeah, so like time scale window is very, very important. And there are two things, is like choosing the right time window for distribution shift is very hard, because like if we have too short time window, we will have a lot of false alarm, like this case, when we think it's a shift, but it's not a shift, it's just a cyclic nature of your data. Whereas if you choose a time window that is too long, then it might take too long for us to detect the shift, which is not a good thing either. So so a lot of stream processing tools allow us to do something called a merge profile. So we can start with monitoring metrics, information, statistics at a small time window like hourly, and then we can merge 24 hours, 24 of the hourly windows into a bigger profile of like daily. So that is very, very convenient. It's great. And I have seen that some tools like Mona Labs, they have this root cause analysis when they automatically analyze various window size to have you determine exact point in time where the shift happens. So we talk about like TrueCut proxies that companies use to monitor their machining systems when they don't have enough labels, and feedback is that predictions and features. So I'm a huge fan of monitoring predictions. So example of monitoring predictions is that like you can have some conditions like if predictions are on false in the last 10 minutes and send an alert, or like if 3 is still the most popular class, like if it's now no longer the most popular class, then you might see that there's something shift that has happened. So predictions, I like predictions because predictions are pretty low dimensional. So they are like easy to visualize, easy to compute stat, and also easy to do two sample hypothesis tests on. And also like changes in prediction distributions generally means changes in the data input distributions. However, keep in mind that prediction distribution shift can also be caused by canary rollout. So I'm not sure you're familiar with canary rollout. It's a case when you might want to roll out. So you have an existing model and you have a new model, and you want to like slowly roll out your new model to more percentage of users. So you might first want to like serve the new model to 1% of users, and then 10%, and then to like 90%, and then before 100%. So this means that as you do carry roll out, you have the new model slowly replace the existing model. So you might see distribution shift. So in this case, you still might want to investigate because like if the new model produce significantly different predictions from the existing models, then there might be some problem with the new model, and you should definitely look into it. So for monitoring features, so monitoring features is very similar to prediction as well, but it's a lot harder and a lot more complex. So for a given features, you might want to compute expected statistics or schemas of that features. So usually like during training for each feature, you might want to get the mean or variance of that feature. And then you monitor the mean and variance of that feature in productions. And then if it changes, then you think that, oh, the distribution for that feature has shifted. So like you can have like, here are some of the examples of the expectations for a feature that you can generate during training. So for example, like take a big common sense feature, like if the task is NLP, you might want to make sure that there is the most common word. It's NLP for English, and you know that there is the most common word in English. So you see that like, oh, if there is no longer the most common word of the data in productions, then there might be a problem there. Another example is that you might want to compute the mean, max, or median value. You might expect that the means or max of features are within range like A and B, and A and B's are the values that can compute it from the sort distribution or the training data distribution. So merging features have a lot of challenges. So first is a compute and memory cost. So we don't have like just one model in production anymore, like any interesting. So companies now, like the number of model in productions is just increasing like crazy. So companies might have a lot of like models in productions, and each model might have a lot of features. So imagine you have 100 models, each model has like 100 features. So now we already have like 1,000 features. So imagine just like computing computing statistics for this 1,000 or 10,000 features, like constantly, can be very, very costly and slow. It can eat up like on our compute power. So another is like the alert fatigue. So when we have like a lot of features, like it's very likely like some features are gonna change. However, like most of the changes are just benign. But if we want to like send alerts to a data scientist every time a feature change, we can have a lot of false alarms. So like we can lead to something called like alert fatigue. And another is just like features usually like follow some expected schema. For example, like if you compute like, oh, the median has to be between A and B. So A and B are the schema of that features. And this might change as we update the model. Like if you train the model on new data, then the value A, B change. So we need to somehow keep track of all this schema feature status over time. And it can be like pretty hard for that. So the vast majority of the feature store of monitoring solutions nowadays focus on monitoring features, and so do feature store. So I think we see a lot of feature store that are also adding the functionality to monitor features, because feature store are already computing a lot of features values and persisting features values. So that could be a natural place to do monitoring as well. So the question is that like, okay, I don't think I'm going to make any statement here, but I do see that a lot of conversions between monitoring solutions and feature store. And okay, I think that I don't have time. Thank you, Dee, for reminding me. But yeah, I think there's some continual learning, but I don't think I'm going to go through this. And yeah, I have a book coming out, and I hope that it's just coming out this week. And I hope that if you already order it, I hope that this talk doesn't make you cancel the order. But also reach out, like email, Twitter to chat about any of the topics. Thank you.
Awesome stuff, Chip. Do you got a few minutes to answer some questions?
Yes, for you, cool. Anytime.
Oh, I love it. So we are asking questions in the Apply Conference channel, and there's a ton of them. I know we're not going to be able to get to all of them, but I picked out a few that I really liked. And the first one is, how do you, oh, sorry, wrong one. That was the wrong thread. It's, can streaming data sources be joined together, i.e. two separate entities with a join key?
It can be, but I think you need joining on streaming is actually pretty hard. So that's why we see, so like joining in SQL tables, we have a lot of like optimizations for batch joining, right? I think we see a lot of movement recently in like streaming SQL as well. So I think Snowflake has a team now working on streaming. We have materialized, decodable. So yes, it's possible. But the question is how optimized the streaming joins are. And that's why we see a lot of new tools coming in.
Excellent. What about a recommendation for a feature store for small teams? I see the value prop in enabling much faster iteration, but the fear, the maintenance and over-engineering as a team of 4.
That's a good question. So I think there are a lot of options for feature store. I would say that like depending on your needs, like whether the complexity of the features. So like if you don't, like if you mostly have like batch features loading into like online key value store, like Redis, DynamoDBs, and it can probably build something in-house. But if you have like, even if you have like streaming features, but it's like simple streaming features, like just computing the number of views a product has in the last 30 minutes. Then it can pretty get away with like Spark streaming or like some Lambda microservice. However, like we talk to companies, especially in fintech, when they have extremely complex streaming features, then you need a very good streaming computation engine. So I would say that's like, then that is harder. I don't see a lot of feature stores that can do complex streaming computations very well yet. And also, I think I heard some complaints about Future Store. I'm sorry, Mike. I know that you're the call. I know Tecton is incredible, and I think I have heard really good things about Tecton. One thing people do complain though is just like it's very integration heavy. So like the integrations. So like if you have a small team, 4 people, I'm not sure like whether well, what is the integration timeline gonna be for you?
So last one before we jump. How do you scale serving when the scale is not worth the number of requests the model gets, but it is with the number of models to serve?
I'm sorry, can you repeat the question?
Yeah,
Oh,
so I think there needs to be some context here. Large, over 10,000 models, all models use text as the only input. How do you scale serving when the scale is not with the number of requests the model gets, but it is with the number of models to serve? Also, how would you effectively monitor drift for a large number of models? Can it be done in near real time?
So you have a lot of models.
Yeah.
Are they
over 10,000?
Well, are they like so this is an NLP. So are you using some kind of embeddings, like pre-built, pre-trained model for the NLP model?
Vishal, this one's on you. Let's see what he says. I'm seeing something. Yes, he is.
So okay, so are you like deploying these models separately, or are you like having one container for like all of these 10,000 models?
Custom serving built to handle this, and he uses embeddings plus another model.
I think like this, we actually work with a few companies that have a similar patterns, like especially B2B companies. So we've seen that B2B companies, they might have like a separate model for each customer. So if you have like 10,000 customers, and you can easily have 10,000 models, and that actually require really interesting solutions. And the solution is not just in like scaling the precision service, but also in like managing all the features, retrain or model retraining, because you don't want to like manually retrain each of these models separately. But yeah, do reach out. And also I feel low-key bad about like, I hope that I didn't like badmouth any of the tool. I know like Databricks and Tecton, an incredible company. Like Mike and Matei are amazing, and I think they definitely like one of the best MLOps tools out there. And I only thing is said about like the limitations are not because of the companies themselves. It's just like the space is very complex right now, and a lot of problems don't have good solutions yet. But I know that they are working on it, and I'm very excited to see the solutions, like the future of these solutions.
Yes, me too. So a lot of people are asking if they can see the slides. Are you going to post them in Slack? I think you are. And there's a lot more questions from people. So you can keep talking with Chip right now in Slack. And Chip, last question I've got. When are you going to come on the MLOps Community Podcast? I know this has been something that we've been saying for ages.
Whenever you want me, D. Like whenever.
There we go. You're too kind. Awesome. Yeah. Thank you so much, Chip. This was really good. And we've gotten a ton of positive feedback. All these questions, keep the conversation going with Chip in Slack. And now we're going to keep moving to the next thing.
Thank you so much. Yeah, have a nice day. Bye-bye.
See you, Chip. Thanks. So next up is me. For just a minute, I'm going to talk about a few of the best things that have been happening in the MLOps community, some trends that we've seen, some of the highlights that we've seen, some of the companies that have been getting acquired or raising rounds. It's like your little news brief for the next minute or two. And then we're going to have a quick break before we jump into a few lightning talks. So I've got some things written down here that I wanted to mention about the greater MLOps community stuff and what has happened. I mean, news, there's been lots of things that are going on. Of course, the space is new, the space is evolving. And first thing that I want to mention is a few companies raised a lot of money in the last couple months. One of them being Hugging Face. I imagine lots of people heard about their $100 million raise.
That was huge. You've got Neptune AI. They raised 8 million. They are awesome sponsors of the community and of the MLOps community, I should say. And then you've got Quick Piece Aporia, another monitoring solution. They raised 25 million, and Labelbox raised 112 million. These numbers, I mean, they just baffle me. I don't even understand how these numbers can work, but now is the fun part where they got to actually produce products that we all can enjoy. So hopefully all this capital being deployed on there is going to be like lighter fluid to the fire, right? Another thing that I wanted to say, a quick news blurb, is that you've got Kserve. So a lot of people probably know about Kubeflow and may or may not have played around with Kubeflow, but Kserve has graduated from Kubeflow and it is doing its own thing. It is no longer called KF Serving. It is called Kserve, and it is definitely continuing on. They graduated. That was news fairly recently. Next up, what else do we have? Oh, everybody want to hear about some acquisitions? We had a few acquisitions in the space. I mean, first up, good old friends at Algorithmia. They sent me this nice, this good old water bottle that apparently is no longer being made now because they got bought by Data Robot. So congratulations to Diego and the team. That was a huge acquisition. We also saw Streamlit. They got bought by Snowflake. That was huge. That was a surprise. And it was for a lot of money. So congratulations to the Streamlit team. And last but not least, I just saw some come through from Cortex Labs got bought by Databricks. So those are 3. And there's a ton more, but I want to keep it brief. And I can add a few more here in the Slack so that we have it. But at the risk of taking up too much time right now, I just want to talk about a few things that I saw going off in the MLOps community. Again, if you're not in the MLOps community or you haven't listened to our podcast, go check that out. I'll leave a link to all of that in the Slack right now that you're in. But now, ML on Kubernetes has been a huge theme for the last 2 years since the ML Ops community started. And we are now doing bi-weekly meetups around it, roundtable discussions, so people can talk about the difficulties of running ML on Kubernetes. That's something that is a trend I do not think is going to go away anytime soon. And so everyone can get fluent at their YAML and ask all kinds of questions to different people with different backgrounds. I love seeing that. That is a huge trend. The other thing that blew up recently is, and I should have known it because the guy's got one hell of a mustache, but we interviewed the creator of Fast AI API. Sorry, not Fast AI. That's another person. We interviewed the creator of Fast API, Sebastian, and that very episode just went gangbusters. It was huge. So then I started a question. I had some polls going on. Who uses Fast API? Who uses Flask? It seems like a lot of people like Fast API. And so I would love to hear in Slack if you're using Fast API, why you like it. Is it more than just emojis in the Git commits that they do, or the releases, the code releases that they do? So that was one huge one. And the eternal battle still has not been figured out. Can you deploy Jupyter notebooks in production? So many people are trying to figure this one out, but it is still not clear. We do not know yet. A lot of people say, yes, you can, and they're trying to work very, very hard at making it a reality. And others say, don't even touch it with a 10-foot pole. That is your update from the MLOps community. And for the next 2 to 3 minutes, you're going to get a little bit of chill music before we jump into the lightning talks. All right, y'all. I'll be talking to everybody in Slack. Feel free to hit me with any questions you've got. And I see one, oh my God, except for that one that just came through asking if I'm high. thank you for asking that one. I'll see you all in just a minute. We'll leave the Slack link in the chat right now in case you're not in it. See you soon. And last but not least, I was about to leave without saying the most important thing, and I've got some funny stuff to show you. I totally forgot about this right here. We're giving away swag. Like, the best thing about this conference, maybe not the best, but one of the best things about this conference is that we've got like a ton of people participating to give their best costumes in the, like, can you all see this? This is hilarious to me. We told you will win some swag. Show either a funny picture of you in 80s gear, like myself right now, or something with your pet, or something like a vacation photo. And I'm going to give a few pieces of swag. Who is this person right here that has the 80s gear? This insane 80s gear. I'm giving you some swag. You get some swag. Please reach out to me and I will hit you up with the most amazing swag you've seen, because I love that. You one-upped me on my 80s gear. I also have some swag for whoever had this cute little cat that it looks like they stole their selfie. Somebody was trying to take a selfie and the cat got in the way. Reach out to me. I'll get you some swag. And then whoever this last person is with the plant, I mean, it's not an animal, but I like the creativity. So yes, please reach out to me. I'm getting you some swag too. That's it. We're taking a break, and I'll see you all in just a minute to start with some lightning talks.
Here we are, out in the wild. We're getting ready for our first lightning talk. Meanwhile, I'm with the emus. And this lightning talk is going to be from Tal from Snowflake. He's an ML architect, and he's going to talk to us all about what they've learned in the last 20 years at Snowflake. So enjoy it, and I'll be here with my emus.
Hi, everyone. I'm Tal Shaked. I work at Snowflake, and I'm the architect for machine learning at Snowflake. Before joining Snowflake, I was actually working at Google for close to 17 years, and I did a bunch of machine learning ranging from research, applications of machine learning to various products, and also building machine learning platforms that were used pretty much throughout all of Google. And today I kind of want to share some of my experiences in machine learning over that time, and give my perspective on why I feel machine learning is really hard to do well. And so I'm going to kind of break this up into 3 chapters. The first is going to talk about some of the experiences I had doing machine learning for ranking in web search at Google. After that, I'm going to talk about building sort of large-scale logistic regression for machine learning ads, and then later expanding that to the rest of Google. And then talk about sort of what happened when deep learning became really popular and sort of how a number of platforms adapted to that. One thing I want to kind of look at is also how the interest in machine learning has evolved over time, at least according to Google Trends. So as you can see here, from 2004 to 2016, the interest in machine learning has been relatively flat. Then deep learning became popular, breakthroughs in image processing, text processing, and so forth. And machine learning became much more popular during that time. However, one thing I actually found really interesting is that for many of the tech-first companies, people were doing machine learning, from 2004 onward. In fact, some of the biggest wins, companies like Amazon, Google, Netflix, was based on large-scale machine learning for recommendation systems, ranking, and really many other optimization problems.
Tal, just a heads up, we can't see your screen.
Oh, shoot, I'm sorry.
It's all good. You're very visual in your words, but we want to see the actual slide.
Okay. No, I got confused. Okay, so
there it is.
Does that work?
Yep.
Okay.
Yep. Now we see it.
All right.
Cool.
Well, so this is the slide I had before. This is the visualization of machine learning interest over time. All right. I will jump back to here. All right. So machine learning for ranking in web search, 2004, 2007. So, at that time, I was super excited. I had just graduated from grad school with a master's in machine learning, joined Google, got to work with, some of the world's best researchers in machine learning, like Yoram Singer. And my first task was, can you do something better in ranking using machine learning? Because right now they had basically, I think, around a 5,000 or 6,000 line if-else function that kind of did ranking. And at the time, we had roughly 1,000 queries that had labels. Those queries had maybe 40 results out of 4 billion that were labeled as relevant or not relevant. It's kind of an interesting skew there. And because it was a ranking problem, we looked at the relative ranking between different results. So it was around 1 million examples total. And I don't want to go into all the details of how the machine learning system worked, but I want to talk about sort of what made this problem really interesting. So here's an example from a query back in 2005, which was the query miserable failure. And as you can see here, the top result was the biography of George Bush. Now, this at first doesn't look really relevant to the query, but as it turns out, this was an example of what we called a Google bombing. A number of users found a way to sort of reverse engineer the ranking function at Google and then create signals that would lead to this result being the top result for this query. And so this kind of makes you wonder, is this a good result for the query miserable failure or not? I mean, as it turns out, Google later tried to address this by removing these kind of results. But on one hand, before the Google bombing happened, this looks like a pretty relevant result for the query. But since people sort of manipulated the results for this to happen, and the world was, people were searching for this result because they actually searching for this query because they expected this result to come to the top. One could, debate whether or not this is actually the right behavior for the system. Now I want to talk about sort of another example I think is much more representative of what makes ranking really difficult for web search. So consider the query credit cards. First of all, you'll probably notice that nowadays, half the page is ads. That wasn't the case back then. But on the right side, you can see that actually there's some interesting results. The first result is a query from the Bank of America for a specific credit card. And the second result is sort of an aggregation site that talks about the best credit cards out there. Which of these results do you think is better? So it turns out that there was a lot of debate here across the engineering team, the product teams, data science teams, even within those teams. Some people felt that the best results is a list of all the most popular credit cards, Discover, American Express, Visa, and so forth. And other people said, no, that's actually not what customers want or users want. The users want, if they have a generic query like credit cards, they want to understand how credit cards work. They want sites to talk about the differences between different credit cards and help those customers, find which credit cards are best for them. It turns out this wasn't a one-off use case. In fact, there were hundreds of cases like this where people couldn't actually agree on what the best results were. And what this meant is that it was actually really difficult to provide guidelines so that people could actually rank which results were best for given queries. Furthermore, people changed their mind about which results were best. And so that meant that people liked having the control of manually shaping and evolving the ranking function for web search. And so even though we ended up building a machine learning system that did really well on the metrics we could measure, we didn't actually really trust those metrics. And therefore, people didn't really trust machine learning. And so the main takeaway I had by doing machine learning for ranking in web search is that data and quality problems are really hard. It was extremely hard to create good data. We couldn't come up with the right labels. We changed our idea about what the right labels were. I didn't talk about it, but it was actually pretty difficult to generate training data at that time. We didn't have anything like feature stores. When you have examples, like for the query miserable failure, if the top result is the biography of George Bush, how do you understand what the system was doing? How can you debug it? And then how do you actually improve it? Do you have to change labels on the data? Do you have to change your signals? Do you have to provide different guidelines for data to be generated? The other thing I want to call out here is that it was actually, it was hard to build very accurate models, but in this case, it didn't really matter because we didn't have the right objective. And so we've probably been better off just kind of building simpler models and iterating from there. So that was actually kind of a frustrating experience for me at the time because I put a lot of effort into all the infrastructure to train the models. I was really proud of sort of building these high quality models on offline metrics. And yet we really I didn't feel we were able to get the full value because we didn't have the right objective and people weren't comfortable sort of handing over the ranking function to machine learning at that time at Google. And so I kind of looked around to see, well, where else could machine learning be useful? So this is around 2007 and ended up focusing on machine learning for ads. And the reasoning was that this should be much easier, right? Everything is measurable. We can measure whether users click on ads. We can measure the amount of value advertisers get. And we can also just measure the revenue to Google. There's not much debate to say, is this revenue higher or lower than the other experiment? And so that led to developing a system called Sybil. And this was kind of focused on large-scale logistic regression. Can we predict the click-through rate for ads? Can we, we had millions of ads to select from. And so this system was designed to train on 1 trillion examples with roughly 100 features per example and support about 5 billion parameters. Again, this was large scale at the time. Nowadays, this is, I think, more common. And there was a lot of innovation in the algorithms and infrastructure, but I'll save that maybe for another talk because I really want to kind of talk about what made this problem challenging and sort of surprisingly hard. So initially, when we focused on ads, we got the data, we built a bunch of infrastructure, we built new algorithms, and we did everything offline in a nice controlled environment. And it was pretty easy to get, roughly a 10% improvement, say over 3 months. Then, we were pretty excited. We had this really high performing model in offline metrics. And we, hacked things up and we managed to get this model into production to run a live experiment. Not surprisingly, at least surprising at the time, but in hindsight, it wasn't. This experiment was fairly negative. We had all kinds of problems. And so we had to figure out, well, how does this model interact with the 10 or so other models in ads? What happens when the predictions go into the auction? And ultimately, why is it that we were getting less clicks and less revenue and advertisers weren't just happy with the results? And so it took a lot of iteration, debugging, tuning, and so forth. And basically, we also had to re-implement the learning algorithm and change the infrastructure because we discovered there were actually problems with the algorithms we had. But eventually we got a 1.5% improvement and we thought this was great. We had a 1.5% improvement on roughly a $20 billion revenue stream at the time. So we said, oh, that's great. Now let's just talk to the rest of the ads folks and put this thing into production. And then the ads team said, well, hold on a second. How are we going to have 50 to 100 engineers training hundreds of models, running multiple experiments, monitoring these models, checking for outages, rolling things back when they're not working. And we realized that there was a whole bunch of production work we had to do. And that kind of led to this diagram that probably all of you have seen before. So we kind of focused on that little black box down there. That was the ML code. And we ended up having to build pretty much everything else around it to make the system usable. And that took about a year. And so after we did that, we realized that we actually had really powerful learning system. In fact, as it turns out, much more than was needed. But we had a nice kind of end-to-end platform. And although ads was doing well with machine learning, the rest of Google really hadn't discovered machine learning or felt comfortable using it. And so we went around the rest of Google saying, hey, we got this really great system. We talked to YouTube, we talked to Android and other places. And what we discovered is a lot of these teams, once they could easily develop models and put them into production really quickly, they were starting to see really large wins on the order of 10 to 100%. And that led to sort of Sybil being one of the most widely deployed systems at Google, with maybe hundreds of models, being trained at any given moment, around 2015 or so. And so the main takeaway or thing we learned from this is that productionizing machine learning is hard. You can't just build a model and then bolt it onto the software and products as an afterthought. Like we saw in web search, it turns out that actually pretty much every team we worked with struggled with getting good data and quality, and good data and had quality problems. We discovered that, Sybil was a really large-scale, fast training system focused on logistic regression, but it was kind of overkill for most teams. They didn't care if they got 90% or 100% of what was possible. They were seeing 10 to 100% improvements, so they just wanted to get something out as quickly as possible. So with that, I kind of want to switch and talk about what happened when deep learning became popular. From my perspective, I felt like I just saw history repeating itself. So, one of the reasons deep learning became really popular is the amazing results it had in terms of image processing, text processing, and as people started to sort of, develop, a more experience with deep learning, we realized that actually kind of works well on pretty much just about every problem. And with enough effort, it usually can work as well or better than just about any other learning algorithm. So that was great. Lots of teams got super excited. Everyone started using deep learning, and then they got a model pretty quickly, and then they ended up spending roughly 1 to 2 years trying to productionize it. And in fact, what they kind of did is they ended up building systems that looked like this. By the way, I'll apologize. I know this is a somewhat retro-looking kind of diagram. That's because I copied it from maybe 8 years ago, just to kind of show what this was like back when we were developing this. So what we realized is that everyone's rebuilding the same kind of production pipelines, but now they're doing this for deep learning. So we said, well, can we take what we did with Sybil? Can we just pull out the Sybil learner and replace it with deep learning, or TensorFlow in this case? And that's how we built TensorFlow Extended. And so we did this, but it turns out that we kind of needed to build another transformation system, another serving system, another way to represent the data. The way you analyze deep learning models can be different than the way you analyze Sybil models. So it turns out we kind of had to rewrite almost everything from scratch. And that actually took a few years. After we did that, though, we had a system that addressed many of the use cases people had, and we ended up having thousands of different models being trained at any given moment using TensorFlow Extended. And what often took a year or two for people to productionize, they were able to kind of use the systems we had for serving and continuous training and so forth. And that really accelerated the adoption of deep learning across Google. And one of the, I think, key things we did differently in TensorFlow Extended versus Sybil is Sybil was actually pretty rigid. It was really great for large-scale logistic regression. If it solved your problem, that was great. But if you kind of needed to modify it, to customize it a bit, it wasn't that easy. And so we wanted TensorFlow Extended to be much more modular. And so we kind of thought of it in terms of multiple layers. Like at the bottom layer, there were very common Google building blocks, Borg, Flume, and so forth. And what we did is we constantly improved those systems so that they were designed to run the ML workloads that we had, continuous training, complex data pipelines using Flume, and so forth. Then in the middle, we kind of had all the TensorFlow Extended components. Again, probably you're all familiar with these. Now it's pretty common in the MLOps community. And on top of that, we built even easier systems to use, such as hosted services for serving. And certain teams, like in the ads and YouTube spaces, might have their own custom platforms built on top of TensorFlow Extended, because they themselves had to train 10 to 100 models customized for their use cases. And so we found that having these multiple layers from basic building blocks all the way up to sort of really easy to use services was super useful. And people could kind of pick and choose which pieces they wanted. And since this was all done inside Google, every engineer knew how to pick and use these pieces. So what was the main takeaway from that experience? So what I found out is I really kind of internalized that, ML engineering as a discipline is a superset of software engineering. And what I mean by that is when you build production systems, you really need to bring in all the best practices of software engineering. I think that's really what ML ops is about. But you also have to deal with the peculiarities of data and quality problems, as I highlighted in the web search use case. And I think this is really different than software engineering. And that's what really makes ML engineering kind of unique and really hard to do well. The other takeaway is that, after doing Sybil and TFX and seeing all these other ML platforms out there, I don't think a single ML platform works well for all use cases. And that's why I think you need multiple, you need a very modular system and multiple players. So with that, I just want to summarize quickly what I learned. So the first is that data is the most important part for ML, and that's why I'm at Snowflake. Second, productionizing ML requires well-integrated components. That's why I'm super excited by the partnership we have, between Snowflake and Tacton, and more generally, many partnerships between these ML companies. Because the better integrated these components are, the easier it will be for our joint partners, our joint customers to do ML. And finally, ML engineering as a discipline is a superset of software engineering. I'm going to conclude by saying that it's much better to quickly get good models into production than to get great models that never leave your laptop. And for that, I just make one call out to the Snowflake Summit that is happening middle of next month. Thank you.
Dude, awesome way to end it. I love that quote right there. That needs to go in on a shirt. I may steal it if it's all right and put it on a shirt and I'll send it to you.
Thank you.
All right, so we're going to keep cruising. We've got Joao. And where you at, man? While Joao is getting ready, if you have any questions for Tal, throw them in Slack. He'll be there answering them. Oh, here he is. What's going on, Joao? How you doing, man?
What's up? And kudos for saying my name correctly.
I try. I'm going to just jump into it because we're a little behind and I'm going to try and make up a little time. So here you go, man. It's all you.
Cool. So classical, share my screen first. Hope you're all seeing it.
Yep.
So that's me, John Santiago, and this is Do-It-Yourself Feature Store, a minimalist guide. So I'm a team lead at Billy. We are a startup in Berlin in the buy now, pay later space for B2B. And because we deal a lot with handing money to other people, fraud is a very big concern. And we want to give our customers the best possible experience, which means all of these models need to be real time. And so since the beginning, we had the need to have something that we later figured out was called the feature store. At the time when we had to decide if we were going to build or buy, there was nothing in the market that we could actually buy. So we decided to build our own. And these are some of the results. So I'm going to show you two things today. The first one is just the minimal possible thing we built to help us share features and start going. I will not die on this hill by calling it a feature store. I think other people won't call this it, but this is how we call it. And then finally show you exactly what we did and we have in production running today. These are some of the points that we wanted to achieve. So like have past data in the real-time models. That's really obvious for fraud because we want to look at behavioral patterns. We wanted to implement a feature only once so that we can share features between projects. And the most critical one of all was that it had to be maintainable by a team of two. So that's me and Bogdan, I think, is in the meeting here today. So cheers. And so we had to build something that was very, very simple, but still achieve business goals. And also the reason why this had to be simple was because it was unproven tech at the time. So we were not given like 100% time to work on this. And we had to decide where do we go to make something we can ship to production as fast as possible. And so the first thing we built was a feature store as an R package, and R here because that's how we build and deploy models in production at Billy for fraud. And the result was this package called Beamter, in which you can build what we call the feature registry. And this is just a list where you include features as steps. This is just steps, and then later you can see here recipes. These are all just our lingo, But in essence, what this means is that we are making steps in a pre-processing pipeline, right? So these are very, very basic examples. We have obviously something that's more complicated, but just to show you, if you want to have a feature called hour, which extracts the hour or extracts the email name, for example, from some string, you can create a feature called email name. It's dependent on something called email, and then just write your code. Now, the cool thing here is that this is just very simple R code. Anyone that knows R can write it. And then we just wrap this into a package, put it on GitHub. And now anyone that has access to our GitHub can just go here and get features that they need. To actually get the features, you just have a vector or a list of strings with the names of the features you need. So if you need the hour, for example, this will fetch this feature here. You just provide this to Beamter and say, here's the feature registry with all the features we have. These are the features I need. And then Beamter just prepares this pre-processing pipeline, which is called a recipe in R. And we ship this together with our model to production. Now, this is really cool. It ticks some of the boxes that I showed you before. So we have the same implementation in 2 places. We only implement it once. There's a kind of a low entry bar for others, because if you know R, like you can do this immediately. There's no extra abstraction that you have to learn, but it's obviously not a full-fledged feature store. There's no possibility to cache data. You have to keep versions synced between projects, and that's a bit annoying sometimes. And then obviously not everyone will know the libraries needed. So I cannot expect just a general backend engineer to review my features on GitHub, because maybe they don't know either R or they don't know the specific libraries we use in data science. And so we had to move up a bit from this, and we actually built our own feature store. And again, this is super simple because, like we said, there had to be no Kafka, no Spark, as declarative as possible, and almost nothing new to learn, so that anyone in the company, at least in the engineering and tech side, could just come in and contribute from the outset. And the too long, didn't read version of this talk is we just use Snowflake. We use Snowflake streams and tasks, and all the features are defined as SQL functions, because SQL is kind of the unifying language that anyone should know, at least in data science space and also in the data engineering space. So this means me as a data scientist can just build a couple of features and have data engineers review them, or I can actually offload these tasks, for example, into BI and ask them to research something. They create a feature from the research, and then I can review their work because we all speak the same language. In practice, this kind of looks like this. We have 2 paths in terms of how the information flows. We have a synchronous path that goes into our models. So this is when you submit an order and you're waiting for the order to be approved. But at the same time, we have other data going into a Fivetran pipeline and into Snowflake. So we do use only 3. If you see, this is our feature store is pretty much just this here on the bottom. 3 components. We have Snowflake, we have a Lambda that pretty much just puts stuff from Snowflake into Redis, and we have Redis. And all Snowflake is doing is creating a stream that detects if there's an insert in a target table, and then running our features or our SQL transformations on that data. How we actually configure this, it looks like this. It's just a YAML file. We have a bunch of configuration on top. There's obviously more options, but to simplify it, this is what you have. You say which feature you want, which entities you need, and then you just write SQL. This is just run-of-the-mill SQL code wrapped in a function, so that we can run this both for batch and offline training, and then during backfilling. So it's exactly the same code, no matter what we do. This is also very, very cool to have in production, because it's quite hard to beat Redis in terms of simplicity. So with an redis.mget and a vector of all the features that we need, we get immediately everything and we can go to production. To keep this link between the model versions, because we have multiple models depending on which customer we are using, each model may use different features, so we just keep a link between what we need in a DynamoDB table, and then we go get it into from Redis. So this is very simple. It runs super smoothly. The only issue is, like I was showing here, right now we are locked into this Fivetran delay. but we will replace this at some point with actual events, possibly using Kafka, which means that we will push this forward, and you can keep having Snowflake in there anyways. So in summary, if you're just starting out and you don't have that much real-time data going on, package your features in some package, share it across your teams. It's not ideal as a long-term solution, but it will definitely reduce the amount of code everyone is writing. And yeah, you can just build a feature store with 3 components like we did. There's a link to the full story where we show a lot more details on how to do this, a lot more examples. And I would just love to hear other people if you try it out and you experiment with this. And that's what I have for you guys today. Thank you very much.
Amazing. Thank you, João. We're going to keep cruising. We've got Felix coming up next. Felix, where you at? Anybody that's got questions for João, throw them into the Slack chat and keep the conversation going there. Felix, you're fast, man. All right, I like it. I'm going right to you now.
All right, we're going to keep you moving. Hey, folks, my name is Felix Brown. I'm head of data science at Vital. We are deploying online machine learning in the healthcare space, and I thought it'd be interesting to sort of actually talk about our use case a little bit. Hope you find that's interesting, and rather than just shameless company self-promotion, I'll let you decide in the chat. And then I'm going to talk about an ML problem that we face and sort of how we go about resolving it. Okay, so we're a company deploying modern UI and ML into hospitals. Hospitals tend to have these legacy IT systems that just don't have the kind of ML capabilities, and more than that, just don't have the kind of user experience that you'd expect out of modern consumer software. And it means that doctors and nurses are spending, upwards of 60% of their time just typing notes into note-taking systems. I've seen somebody click 5 different plus boxes to try and get to the right option before in a busy ER department. And so we're trying to sort of solve some of the problems that they face. I'll quickly rattle through this. This is just our product suite. We've got this product for patients in the emergency department, product for patients in the hospital, and then this is our clinician app where we're doing some clinical decision support stuff. I want to talk about wait times. So 50% of patients who come into the emergency department, they've actually never been to that ED before. They're often in pain, they're frightened, they don't know what to expect. And the only way for them to get any of that information is actually for them to grab a nurse on the floor or a doctor and try and get that kind of understanding of what's going to happen to them out of that provider. And right now, I don't know if you know this, but in the healthcare setting, there's an enormous staffing problem, as a result of all of the world events that I'm sure you're all well aware of. And that means that patients coming in and asking how long it's going to be until they see X means that providers aren't able to provide critical care to people who need it. So we're trying to take, this is sort of one slice of our product suite. We're trying to take the wait time problem and automate it, take it out of provider hands and sort of give patients an understanding of what their stay is going to look like. And the key component of this that I want to talk to you folks about is our ED wait time product. So we're trying to produce for the different stages of an ED visit. Hopefully you've never been to the ED. If you have, I'm sure you're aware that you sort of come in, you register, and then you're going to be waiting to be triaged. And then once a nurse has sort of had the time to see you, take some basic information about you, you stick around in the waiting room until someone has a bed for you. And this is the part that people find the most stressful, not knowing how long they're going to be waiting in the emergency room, particularly in the waiting room, until they can see a doctor. They're probably pretty concerned about whatever reason that they've turned up to the ED to talk to somebody about. And we're trying to provide personalized wait times in obviously a streaming case, updating live based on conditions that we're experiencing in the ED. Okay, let's actually talk machine learning. So one of our key problems is the cold start problem. We're going live at new facilities every month. Integrating with these facilities is pretty painful. One of the innovations that we're trying to bring is rather than integrating a new software system in a matter of multiple years, which is the real case with the HRs, we're trying to get in there in a matter of weeks or even days. But what that means is when we go live, we actually have very little data. And our hospital partners understandably expect us to be providing accurate machine learning from the day of go live. We don't want to just take this little slice of data that we have from this hospital and try and do everything on that. We want to learn dynamics from all of the hospitals where we're live and bring those dynamics into whichever this new facility is. But there's a couple of key problems there. The first of them is that wait times can actually range from 30 minutes to over 10 hours. I've seen people waiting 10 hours in the emergency room just to see a doctor. And also in the healthcare setting, data regime changes are really common and they're a real problem. Here's an example of sort of regime change that I'm sure you'll all be aware of. This is on the x-axis, the year of 2020, and on the y-axis, the number of people who were admitted to 4 different emergency rooms on the East Coast. And with the pandemic coming in, actually, you might be surprised to know that there was this precipitous drop in ED admissions. And actually, a lot of hospitals, suddenly the concern that they had was less around, are we going to be able to handle the surge of COVID patients? And it was more around, are we going to be able to financially survive, given that everybody else is too afraid to come into the emergency room? So in this time, you know, we had this situation where you wanted to have as little contact between patients and doctors as possible. Every time a doctor has to speak to a patient, they have to put on full PPE. Patients had to be kept separated. We had these tents outside, sometimes in places that were pretty cold, holding patients. And what we were trying to do is deploy the solution and enable patients to kind of have an understanding of what was going to happen in a particularly scary time. And this is sort of the resulting wait times from that period. And you can see, you know, it sort of follows the regime change pattern, but there are some key differences, especially in this red facility here. And that means that we need to be pretty careful about aggregating together information from facilities and using that information at a facility where we don't have a lot of information about the dynamics at the moment. Okay, so our solution, as you might have anticipated, is to normalize. So what we do is we gather features that you might expect to be useful when predicting the number of minutes that someone's going to wait before they see a bed. Like, for example, how many patients have recently been admitted in the last hour. But we also gather summary statistics on those features. So for that feature, we're taking the mean and standard deviation here and feeding them into the model. And then on the outside, on the output side, we're not predicting in minutes, we're actually predicting in the percentile space. So just to be clear, the feature summaries that we're taking, they're obviously aggregated on a per facility level, and they're a rolling window. So they sort of allow us to keep an understanding of, in this situation, if you have 20 patients arriving at this facility today, the model can understand, oh, well, that's, you know, 2 standard deviations away from what's normal here, or that's perfectly standard. And then it can do this, what I described, this prediction in the percentile space. So when we're making these model predictions, instead of predicting in minutes, the number of minutes that you're going to be waiting for a bed or to see a doctor, we predict the percentile of the historical weight cumulative distribution function. What does that actually mean? It means, okay, so we've got 2 facilities here. We've got the orange one and the blue one. What we're doing is we're taking from the last 2 weeks, all of the wait steps for those facilities. So let's say we're sitting in the triage room, we're sitting in the waiting room after triage and we're waiting for a bed. We take all of the resulting weights and their real wait times, we order them. And if we are outputting 0.8 in our model here, we take the 80th out of 100th weight, right? So this allows us, our model, to sort of, you know, predict into this latent space, and then we can project back using the recent rolling history of the facility. And if our model is outputting 0.8 for the orange facility, you can see with the red arrows that that results in a real prediction for the user of 60 minutes. But if the model is predicting 0.8 for the blue facility, that's resulting in 280 minutes. Okay, so it's Tekton conference. I thought we'd talk a little bit how we use Tekton to solve this problem. So we want to calculate this admitted count concept. We also want to calculate this mean and standard deviation of that feature. So what we've done is we've built a feature service for all of the features that we would like to normalize per facility, keyed by facility ID. We have, I mean, this is a little bit more involved in this picture, but simplified, we have a Lambda, which is periodically extracting those features, and it's putting them into Redshift for us. We're connecting Redshift as a data source in Tekton, and in our little Ouroboros here, it eats its tail and produces the normalized statistics on top of those features because it's treating the feature values as raw data source values. Right, at 9 minutes, that's everything that I had. Shameless promotion, we are hiring. If you'd like to come and work on a use case, a real streaming ML use case where it has tangible impact to people's lives, come and find us at vitally.com. Thanks, folks.
You are awesome. Don't forget that. You're doing great work. Keep it up.
What's up, guys? You got some stuff to tell us?
Yes, so let's see. Let me see this one right. Yeah, let's go. All right, very cool. Hi guys, my name is Joost. I'm here with Thijs, and we're here to speak a little bit about feature stores and the work we did for that at Adyen. As you can see from the slide, I'm no longer part of Adyen, but I guess we left on such good terms that they still agreed to let me do this talk. I'm doing this talk with Thijs. It will consist of two parts. So in the first bit, I'm basically going to give a whole bunch of context. I found this quite useful from previous iterations of the Apply conference that we watched while doing the work. So we're returning the favor here. Thijs will do the second part, in which we will discuss the plugin that we developed in order to make sure that we can run Feast on our infrastructure at Adyen. Yeah, so in the next slide, there's a bit of introduction about Adyen. We are a payment company. Basically, if you're a business and you want to accept money from shoppers, Adyen can help you do that. You can see a bunch of colorful logos of companies that already trust us. And as you can see from the numbers, it's quite a big company. So we process big amounts of money. So yeah, in the next slide, we listed a few of the use cases that Adyen uses machine learning for. I think many people can predict that credit card fraud is something that we want to prevent, and we use definitely we use ML for that. Another use case that is a bit maybe more new is like the fact that payments fail. Of course, it's not new, but payments do fail. And a common case for payments failing is that people don't have money in their account. Later in the month, they might have their salary. So you can use ML to predict when is a good time to retry the payments. And like that, there are many use cases. So in order to support all these use cases, at Adyen, we built an in-house machine learning platform. So in the next slide. Important to know about this platform that everything is hosted on premise. So early on in the history of the company, Adyen made the decision to not use public cloud. So we have to host everything ourselves. Some other facts and figures of our ML platform. We release a couple model versions every week. Process quite a large volume. And many of these machine learning models are also part of the real-time payment flow, right? So we have some low latency and reliability constraints to that. And as you can see, over the last years, the ML team has grown quite a bit to a sizable organization. So it was very fun to be able to work on all this. On the next slide, we're getting near to feature stores. So this is a basic timeline of the last year and the major milestones we had in implementing a feature store based on Feast. So a bit more than a year and a half ago, there was no general purpose feature store at Adyen, which was a very sad time. It was very difficult for data scientists to reuse the feature engineering efforts they did. And that's why we decided to implement one actually based on Feast. 0.8 was the first version we used, so a long time ago. We saw quite some adoption. People liked it, and that's why we kept developing. And then at the end of last year, we were able to upgrade to a recent version of Feast, 0.14, and at the same time develop a plugin to make sure that we can run Feast on Spark, which is the main data processing tool that we use. And then quite a few months ago, this plugin was moved into the main Feast project, which is also a main reason we're here today. And then the next slide is sort of a mandatory feature store diagram slide. I always appreciated this a lot. This gave us a lot of confirmation that we were building something sensible. Basically on the right side, you see the part where Feast is really living again in our big data / machine learning platform. It's an Hadoop platform, not an infrastructure engineer, so I'm probably forgetting a bunch of important technologies. We use HVS for storage and Python and Spark for processing. And we use Feast basically only here. So on the left side, you see the real-time payment processing platform with the online feature store. You can see there everything is based on Java and Postgres, and we built a very custom solution. So this is definitely a part where we see some future improvement, and also something that Adyen is still working on. I think that the rest of the presentation will focus mainly on the right side and the component called the Spark offline store. So Thijs.
Thanks, Joost. The Feast Spark offline store, in-house built package, because I'll explain a bit why we really needed to build this. But of course, it's for Feast, the open source feature store. In earlier versions, Spark was supported in Feast, but later they decided to move it out of the main repo. And then other repos became incompatible that were focusing on Spark and Feast combination. So we really needed something to interface with it. And the reason for it was that at Adyen we have there was the most wanted offline features were like aggregations over day ranges, larger calculations that like every feature store has facilitates. And a lot of our internal ETL pipelines were of course calculating these features using PySpark. And of course, Feast interfaces nicely with Python, and we were using Spark internally as well. So we needed some consistency, and we wanted to promote feature reuse within the company. So we wanted a familiar looking interface to, instead of having like adapters that we built customly. So we wanted to have consistency with the actual Feast repo and set up a custom plugin. So we decided to build this first in-house and then see if it got adopted, and then maybe later open source it. So then we started building the Spark offline store, basically followed the templates, and we followed the templates of BigQuery and Redshift. We could really see these nice examples and focus on the consistency between these. And it was really easy to develop this way. So here's an example of what it looks like. Basically, you can use Spark to read your different, your files or tables that you have in maybe your Hive meta store, or put an SQL query directly in it, the usual way. But it uses the data source objects that Feast uses to interface with. You can also configure your Spark session, your Spark configuration. You can add it to your feature store YAML. It's not necessary though. You can also just, if you have already a Spark session running, that's also fine. So we got some buy-ins on adoption within the company. Then we were like, okay, we need to open source this. We need to give back to the community because we're using Feast a lot. And that was great. We got like some comments, some pull requests from other people. And then at a certain point, we got a contact by the main contributors of Feast if we wanted to add this to the main repo, which was recently done. So big thanks to Kevin and Danny, who are, I think, also giving a talk at this conference. It's currently in the alpha status, so beware still a little bit, but it will continue to be worked on. And so the conclusion for us is like we've seen, the feature store is a valuable part of an ML platform. We've seen a lot of buy-in within Adyen. We built a lot of custom logic, but Feast is valuable to provide good abstractions and guide the engineering thinking. And over time, the custom logic became less and less needed with new Feast upgrades. And yeah, Feast is extensible to fit diverse tech and infra constraints. So we like the new direction. And to conclude that our experience in creating a custom plugin was very smooth. So yeah, that's it. Thanks.
Amazing. Thank you, guys. I appreciate that. Let's keep moving on. We have got Justin Young coming up from Abnormal Security. And I will give a quick plug that in 3 talks or 4 talks, sorry, I don't do public math, we're going to have a little bit of yoga. So if you all have been sitting too much, we're going to be doing some yoga at the break that's coming up after the next 4 talks. All right, Justin, where you at, man? How you doing?
Hey, good. How are you?
I'm good. I'm excited to hear what you got for us.
Awesome. I'll jump right in. Hey, so I'm Justin Young. I'm a software engineer at Abnormal Security. And today I'm going to be talking about some common challenges that you're likely to face when building a feature platform and a system called Compass that we built to tackle these. So I'm going to go pretty fast, but I'll share these slides out after. So let's start with the real world problem that we're trying to solve. So at Abnormal Security, our goal is to stop all email-based cyber attacks. So as an ML problem, we have some pretty stringent requirements for this. For one, we need really high recall because it can be devastating if an attack makes it through to an end user's inbox. At the same time, we need really high precision because we don't want to be flagging safe, normal messages. And finally, we need really rapid iteration cycles because attackers are constantly changing their techniques and actively trying to evade a system like ours. So we have this mantra of move fast and don't break things. And so for me, as someone who's working on the ML platform, I'm thinking about how we can, implement this kind of user story where we want to make it really easy to add and remove signals, hard to break existing signals, and we also want this pipeline to run really well online and offline. So for today, I'm going to be talking about 2 challenges that you might run into when trying to do this. The first is entanglement, which is what happens when a certain change to the system has a really wide blast radius. The second is online-offline skew, which is what happens when the data or the logic that you're serving online is very different from what's being served offline. So let's start with this entanglement problem. So entanglement, like I said, is this blast radius problem. A succinct way of saying it is that changing anything changes everything. And so let's look at a common approach to a feature pipeline that you might see in example code that shows how this might come about. So we might have a predict function like this. In our case, we're taking in an email and we want to return a model prediction. So you can imagine we start by extracting some heuristic signals, we encode that into a feature vector, and then we return a model prediction based on that feature vector. So totally fine. This seems very reasonable. It'll definitely work. But we said that we want to be adding signals to the pipeline very often. And so maybe at a later time, we add some feature store signals where we go and use the heuristics, look up something in a feature store, and add those to our feature vector. And maybe we keep doing this. We want to add some heuristics based on what we looked up in the feature store. And eventually this pipeline gets so complex that it's really hard to understand. And as a result of that, it's going to be hard to add signals, basically impossible to remove signals. And the reason that we can't remove or change signals is that if we make a change at the beginning of this pipeline, it could have an effect anywhere later on. And so we're going to have to do a lot of custom work to make sure that what we're doing is safe. And it's going to become infeasible. And this is exactly this entanglement problem. The reason that this is such a big problem is that changing anything changes everything. Like I said, changing something at the beginning of the pipeline can cause the whole thing to break later on. And our machine learning pipeline will start to look kind of like this Jenga tower, where a small disturbance at the base can cause anything later on to break, and the whole thing can fall over. And the reason this happens is that a block at the top of the tower depends on all the blocks below it, which is actually a really bad characteristic for this system. So let's take a quick aside and talk about function composition. Abstracting a bit, this function that you see here is basically the same structure as what we saw in the function that we wrote before. If we ignore the side effects that are happening, when we write imperative code like this, we're basically just iteratively taking in some input, returning outputs, and this is really just function composition. And so just to hammer home this point, we can rewrite our original function in this composed form and do exactly the same thing. I would even go further and say that function composition is the primary responsibility of a machine learning pipeline. Side effects are definitely important, but they should be happening, elsewhere before or after this function. And within this function, we really only care about the inputs and outputs. And what we want to do is iteratively transform our input data until we get some model prediction. And we don't care if any of the intermediate functions are simple Python logic, remote RPC to a service, or even running a model. All of it just has some inputs and it has some outputs in this model. And so this is the whole reason why we're doing this. We have an input, we want an output, but our data model is actually too flexible. So we have this really unconstrained function composition. And we definitely have dependencies between stages, but even within stages, you can see that if we drill down into something like a heuristic function, we're getting like an inner web of dependencies. And what this looks like is this graph of dependencies that you see here on the right. We have dependencies within stages and across stages. And in the end, we just get this really tangled mess of dependencies. And so if we think about how this is going to scale out using the total number of dependencies as one proxy for the complexity of the pipeline, it's going to be this n squared relationship as we're adding more signals. And it's actually a massive problem. If you look at the y-axis here, if we're extracting hundreds of signals, we're already into the hundreds of thousands of dependencies, and it'll even just explode beyond that. And definitely it's going to be more than, you know, a single person can comprehend and make changes to, you know, with really understanding what they're doing to the system. Okay, so this sounds like a major problem. So how do we avoid it? Well, the key insight is that we actually only need a small number of inputs on average for every function. Our model right now is too constrained, and we can probably rein it in. And if we were to do that, our graph of dependencies will look a lot more like what we see here on the right. This is probably more like what you'd expect rather than this tangled mess. And if we simulate, you know, a pipeline that looks like this, in this case, the orange line shows if we had 2 inputs to every function on average, it would still be O of n squared in the worst case, but the growth is going to be a lot more slow on average. Okay, so this is a nice idea, but how do we actually make this work? Well, one way would be to just explicitly model the inputs and outputs of every function. If we did that, then we wouldn't have to make this really wide assumption that something at the top can change something at the bottom. We know exactly what the dependencies are in the graph. If we did that, we would get this kind of graph that you see here. And just to be explicit, there are functions that are transforming the inputs and returning these outputs, but we can just think about the graph of signals. Okay, so this is a bit abstract. It's a nice idea about how it will work in production. Well, quick shout out to the Stitch Fix team and their Hamilton system from last year's Apply conference. Definitely a similar problem there, but out of normal, we're not very data frame centric, so we have a bit different constraints and our design will look a bit different. But one challenge that we'll face right off the bat is that we're going to have some ugly data classes to model these dependencies. But all I want to show here is that syntactic sugar can do a lot of the heavy lifting and allow the ML engineer to have a UX of basically just defining a normal Python function with this decorator. And then in terms of actually executing this pipeline, again, details aren't super important, but I just want to show that it's a pretty simple algorithm. All you have to do is topologically sort the graph of signals, make sure that you have an append-only data structure and that every function is just appending to it. And then if you just transform all your functions in order, or rather execute them all in order, it'll basically look like this. We start with our input signals, execute the first transformation, append to our collection. And if we keep doing this at the end, we'll get our fully realized collection of signals, including any model predictions that we might want at the end. And so this will work. We also get some nice utilities in addition if we do this dependency modeling. Really easy to understand the pipeline. We know what all the dependencies are, so we can do something like visualize a graph or list dependencies of a signal. We can also validate things like the graph having no cycles, no unused branches, and wasted computation. And finally, we can platformize some common operations like propagating a missing signal down so that we can skip transformations that can't properly work on missing signals, or we can do parallel execution of parallel paths in the DAG. So this works. We have a composable pipeline. We said that this is the whole reason that we want a machine learning pipeline. And it's basically minimally entangled. We should have the minimum set of dependencies, but it's not necessarily scalable. So how do we execute this offline? Obviously, this is a really important part of a machine learning system. So let's take an example of a lookup to a online store and a feature store. That might be our online transformation. If we try to execute that in the same way offline, we know that that's not going to work. That's the whole reason that a feature store has an offline store. And so we chose to just model that reality and try to reflect it in our code by allowing a user to optionally override with special offline logic. So again, detail is not super important, but the key insight here is that most of the time we won't need to do this. Most of the time we can just map our online function, if it's simple Python logic, for example, over the data set. In special cases where we're not able to do that, like a feature store lookup, we can override it with something like a join. But most of the time we won't need to do that. So this also has the really nice property that our pipeline is going to look exactly the same online and offline. We're even in most cases going to be able to use the same code, and any differences are going to be isolated to these individual functions. And so this should be scalable. We have a pipeline that can be executed offline. So we accomplish both our goals for this system. And if you'll pardon the buzzword for a second, I say this a bit, this is a bit of a silly buzzword, but I just want to pull apart two conflated ideas in a feature platform. One is a feature store, which we hear a lot about, which is really good at registering data sources, serving it on and offline, and making sure that the data is as close as possible. I want to just propose the idea that a function store doing the same thing, but for the logic that's transforming the data is equally important. And you should definitely have a feature platform that does both of these in a really nice way. That's my main takeaway. Make sure that your feature platform is doing both. There's some really nice managed feature platforms that do both in a really nice way, but there's also some out there that only really handle the data. So yeah, that's all I have, but thanks so much for listening, and thanks to the team who worked on this system. And yeah, we're also hiring. So thanks so much.
All right. Oh man, another store we got to keep track of. I appreciate the talk. Arjun, you around? Arjun's coming. Yeah, there you are, man. How you doing? I'm going to kick it off to you because I spoke too much and we're low on time. So go for it.
All right. Thanks so much for the intro. I've got a bit of a provocatively titled talk here about how streaming is just an implementation detail and how I'm hoping for a future where we actually stop talking about streaming. So before I get into that, let's just start. Okay, what's even streaming and why is it even useful, right? So streaming is about taking action on data points as they appear without waiting for a batch process to happen once a day or every few hours at best. And modern streaming systems are mature and performant. You can process large amounts of data with millisecond level latencies. But stream processing isn't just about going fast, right? It's customers have been trained to expect immediate feedback. And it's considered antiquated when it takes more than a moment for, say, money to transfer between two accounts, or food delivery apps today require up-to-the-minute tracking as it sort of you watch your food get to your door as you're hungrier and hungrier. Streaming is what makes all these products possible. That sounds pretty great, right? Let's see how it actually turns out in practice. And I'm going to use a fun running example here. Thought it would be appropriate today. Let's build a feature store together, right? Now, suppose our team is building a model serving application to detect credit card fraud, right? We're going to keep the most simple, basic example here. Like there's a customer, they go to a store, they swipe their credit card, and we're going to need to determine in real time whether to approve or deny that transaction. In our demo system, we just have a very toy schema. Each account is associated with a single owner, but each owner might have multiple accounts, right? And each transaction, we're going to give it a fraud score in real time. And when given an account ID, we're simply going to count the number of verified fraudulent transactions against the account owner over the last 30 days. So what does this look like in practice? So it's an e-commerce store, so there's probably a transactional database at the center of everything. And we're going to put a little web server on top of it to act as our API. So far, so good. We're going to use a data processing framework to compute our transformations. The transformation from raw data into a feature is too costly to perform from scratch every time on demand. So we're going to process the data as it comes in and write the results somewhere else. Now, to write this transformation, you're going to have to learn some specific framework or programming language. We're also going to need some external data sources to compute additional features. That computation might take some periodic rescheduling. So as we pull in the data throughout the day, so we're going to need to use a framework for that. And then finally, if our features are coming from multiple sources, we might still require online processing for things like joins. Now, some of these stream processing frameworks are notoriously poor at joining streams. So you're going to need some additional services to do that, and we're going to use a stateful store like Redis. Good news is a system like that is going to be very helpful for caching answers as well for low latency reads. When you sort of step back at all this is a lot of infrastructure, right? Let's admit it. The stream processor was like one tiny part of the solution. And to actually build what we needed, we walked ourselves into accidentally building an entire database around it. Let's look at three sort of classic database problems that we had to solve. First, we had to think about consistency. What happens in the failure scenario? One service is working, another one doesn't process a request. Second, efficiency, right? Like our queries change, our schemas evolve over time, we build new features, we're running multiple queries side by side. We have to do essentially query planning. Third, we have to build and maintain indexes and caches. Keeping our cache valid and updating it and invalidating it is one of the hardest problems in computer science. Don't get me wrong. In our architecture, we got a lot of value out of the stream processor. It did the heavy lifting on the computation, but it wasn't sufficient on its own. Stream processors are part of a solution, but they aren't the entire solution. Ultimately, today's streaming systems don't meet users where they are. They require developers to write a lot of complex code. Put another way, in other parts of your day, when you need to persist some data to a disk, you don't implement a B tree and consider the subtle behavior of fsync. You use a database. You pick a tool that takes your expressed intent and takes care of the hard problems. I believe that streaming today is a great tool, but it's more like a B tree storage engine or like a push-based query execution framework. These are all amazing things, and I'm really grateful for them, but developers don't think about them every day. Right? They get to harness their power in an easy-to-use, familiar experience. That's what databases give you. So at Materialize, we've been hard at work building a new database, one powered by a modern stream processor at its core. But one thing we strongly believe in is that none of our users need to know, and users shouldn't have to care about the stream processor. Now, of course, some people might because it's cool. And for those that care, the timely data flow stream processor at the heart of Materialize is open source. But for the developer, it looks and feels like a fully featured database so you can get your job done. So as a result of this, users can think about computation the same way they have for decades and even migrate existing workloads from data warehouses because they express their computations in standard SQL. Materialize allows you to run these complex analytics workloads in real time. And it supports the full breadth of SQL, which means you can run those data warehouse grade queries on it. And the added bonus is it doesn't really care if you're doing batch or streaming. It's all just one kind of computation, so you can mix and match. For example, you might need to backfill a streaming pipeline with some historical data on S3. It's Postgres wire compatible, so it looks and feels like a regular database. It incrementally materializes, hence the name, the result of your views, and they can be efficiently queried from memory or pushed out to your application using a standard Postgres driver. And most importantly, it fits in your data stack, so you can orchestrate your computations using a tool like dbt. So let's start all over, right? What does building a feature store look like in a world with a streaming database system, right? There's no job scheduling. We stream our data directly into Materialize. Materialize pulls the data in from a message broker like Apache Kafka for your raw events, or directly from your relational database like Postgres. Instead of a zoo of tools, Materialize just defines all the transformations in just SQL, right? The same SQL that you're probably using across your organization. So you have the added bonus of consistent business logic definition in your production tools as you do in your analytics tools. We'll dig into exactly what this looks like just in a little bit. And finally, there's no need for a separate caching layer, right? Materialize is continuously materializing the results in memory, so your reads are fast and up to date. So let's look at the actual SQL. First things first, we need to connect to the data sources and get in the data. We'll connect to Postgres using change data capture. There's a table in our Postgres OLTP database correlating accounts to account owners. So it makes sense to just, anytime there's any change, say someone gets issued a new card, we instantly replicate that change into Materialize. We'll also have Materialize consume these messages from the confirmed fraud topic from a message broker. And that could be sort of any Kafka API compatible message broker like Red Panda. Each message is a JSON payload containing an account ID and timestamp for a transaction confirmed to be fraudulent. Now we're in place to define our features. We're simply going to write SQL and not worry about streaming. We start by creating a view. We'll mark it as materialized, so the system will continuously consume eagerly from our sources and update the results of this view definition. Users of the view can then read the pre-computed answers from memory with minimal latency. And from here, it's all SQL that you already know. You can do some projections to pull the right columns, perform some aggregations, join across the various streams, and even filter out rows when they become too old. Over here, as records become more than 30 days old, they're automatically filtered out so that the in-memory materialization is super efficient on read. And finally, from the client's perspective, when it's time to read the result for our production service, our feature is already available in memory, ready to serve with a simple select query, right? Now, I believe that streaming is the future of data processing, But I also believe that streaming will only become mainstream when it like disappears into the background as a boring implementation detail. And developers experience the ease of just writing SQL the way they now write batch SQL on data warehouses. Thanks so much. I'm on the Tecton Slack if you have any questions. And if you go to materialize.com/apply, it'll take you to a GitHub repo where we have the code for building a toy feature store with just SQL. You can try it yourself on your laptop right now. Thank you very much.
Heyo, Arjun, thanks, man. I appreciate that. Good stuff. We're keeping it cruising. We've got Leonard coming up. Leonard, how you doing, bro?
I'm doing good, thank you. Happy to be here.
Yeah, I'm excited to hear what you got. I mean, it's been a while since we chatted. You've been all over Europe since I saw you last, I think. And now you back at work finally? Or are you still on parental leave?
Yeah.
All right, cool.
Yeah.
I'm going to give it over to you, man. Share your screen and let's get into it. What you got for us?
Cool. I kind of just realized by hearing all of these other talks that I might be preaching to the choir. But anyways, I have 10 minutes to go, and I was planning to talk about effective ML system development. Sorry, just give me a second. Right there. Yeah. So first and foremost, I think some people might forget this. Machine learning is actually software. It's data-intensive software. I see it as usually being implemented as data-intensive distributed systems. Anyways, it's also, as stated, dependent on data. If you want to build good machine learning systems or reliable ones, you need to figure out how you're managing your data. Uncertainty is a feature of machine learning, but also sometimes a bug. It's harder to test for those reasons that we mentioned. You need to also test your model, and you need to test your data. And that's also why it's harder to debug, since the search space for a potential bug is much larger, has additional dimensions to it. So here are some, by my opinion, low-hanging fruits. Basically, you should care about system design. This is something that I see in practice not being done properly. Furthermore, you should adopt a branching strategy. Many machine learning teams or data science teams don't really do that. Another aspect is have a clear review process where you review your code and your analysis. I think this is very obvious for many of you. This ensures quality, and you distribute knowledge across the team. And yeah, anyways, another thing that is important is that you should write tests. As mentioned above, they're harder to write, and they're not just standard assertions. You might need to write some statistical tests as well. You should adopt practices where you, for failure modes that you have identified in production, you should build that into the mindset or the way of working for the team to automatically start working on a regression test and add that to your system to make sure that further releases does not regress over time. Documentation is very important. You should document your analysis, your approach, your code base in general. This is something that, yeah, in standard software development also is something that we should care more about. Given that you can have silent failures, as in your model and your system can be up and running, but you won't really see it from standard monitoring for just seeing that your system is up and running and providing predictions. You need to actually make sure that their predictions are within the sort of scope of requirements. Another part is obviously automation. And if you don't have a release process and a well-defined path towards production, and you don't utilize Git properly, it's hard to build CI/CD into your daily work to effectivize your development process. You should plan for disaster because disaster will happen, and you should probably have a disaster recovery plan in place from the early stages. That said, you should start simple and gradually iterate. I guess those were my slides. I don't know how I am on time. Those were really quick, but I guess we can have a discussion around it.
I love it, man. I appreciate that. And yeah, we had a lot of people mentioning that your slides are very effective and the simplicity is key. It is crucial. So if there are any questions that you have for Leonard, throw them in the chat right now. Otherwise, throw them into Slack and he will be over there. I already saw that you introduced yourself.
Yeah, one thing is why I'm stating it this way is that I don't see our challenges as being mainly technical in this case. It's about practices being in place, and I see this adaptation as being very much low-hanging fruit.
Ooh, I like that. So we've got one question that came through, and since we actually are a little bit early right now, I'm going to ask it to you real quick. Could you elaborate on branching strategy and review process?
Well, I mean, if you're doing experimentation and working on a machine learning system, or any type of software development, you should have a branching strategy in place. Like either Git flow is quite simple. We have adopted that mainly because going with more complicated approaches is usually something that, shows to be a challenge for machine learning practitioners, in particular data scientists. Like we need to build it like a solid foundation for them to collaborate. And that's how you build automation around your development process, and you can't really get up running integration tests or automatic deployments and stuff like that. So the way we build our CI systems is based on having a particular branching strategy. So that's why that is important. And when it comes to having a review process, you should take different perspectives, right? So you can invite some that are, say, more software centric to have a look at the code base, but also maybe some senior ML engineers or data scientists to review the analysis. And I think we can try to make that easier for the practitioner. So, for example, like being able to review in the sense in a more interactive fashion to look at plots, distributions, and whatnot. And but yeah, it just ensures quality in a sense. And you should not merge a new feature or in any way, shape, or form unless it's been reviewed.
Mm-hmm. Makes complete sense. I mean,
yeah,
it's kind of obvious, but I know it's not as easy said than or done rather than said. So
yeah, sorry.
No, go ahead.
No, it's just I feel like right now the wind is blowing this way in the machine learning community, which is great, but I've worked in this space for quite a while, and I think we haven't cared about these things at all, like in a broader setting for a long period of time, and we need to shape up.
Yes. So, well, kind of in that same vein, there's a great question that just came through that's talking about what disaster management techniques have ML practitioners used in general? Usually these are not discussed during the design process. Curious to learn your view.
Well, I think they might and should be discussed during the design process, when you try to iterate towards setting up well-defined requirements for your system and like which scope it should function. And then you should run some type of stress testing to understand like really think about what are the worst case scenarios that might happen in production, or things that might be exposed to the user And I think that's something worth taking up in the early stages, and make sure that you have tests to ensure that your system does not behave in that way. And I previously in other talks talked about a red team, which I think should definitely be sort of taking care of these things and auditing systems.
Incredible. All right, there's more questions coming through, but sadly, we're going to have to cut it off there. Please chat with Leonard. Keep this amazing conversation going in Slack. I've got another question for you, but I'm going to go to Slack. I'm going to follow my own advice and take it to Slack, because I want to know how you structure your files and your repos and all of that. But I'll ask it in Slack. So I ask that everyone else go to Slack, ask the questions for Leonard. Thank you, man. And awesome slides. Very, very nice and clear. So it is now back to me. And I promised you all some yoga. We've got that coming, but I want to give out some swag first. I also promised that we were going to be giving out quite a bit of swag. And so, I mean, let's just look at some of these pictures that are coming through, because they are amazing. Look at these pictures. Whoever has these little, I don't know if those are gerbils or what those little creatures are, reach out to me, because you're going to win some swag. That is awesome. And we've also got, there was one that, oh, right here, whoever took this picture of the beach, it looks like a beach and a little birdie with some sunglasses on, reach out to me. You get some swag too. This is super cool. Remember, if you would like to participate in this, please just take a selfie, style yourself up. If you want to do it 80 style, you get extra credit. If you want to put your pet, also extra credit. And you'll probably get some swag from me by the end of the day. I'm going to be giving out a lot. Reach out to me if you are a winner, if you're that birdie photo, or if you are the gerbils or whatever they are, the little mice. Reach out. I'll get you some swag. Now we've got some yoga. I hope y'all are excited. We're about to make it happen. Let's get into this yoga. I know I'm ready to stretch, and we've got a special guest for us that's going to come and take us through some nice postures.
All right, we'll get started in a comfortable seated position today. And as you come to your seat, you can rock left to right, move the flesh out from underneath your body, start to lengthen up through your spine, take a big shoulder roll, and then just soften your shoulders down your back. You can rest your hands on your knees or in your lap, whatever feels more comfortable. Palms up if you'd like to take a little energy in today, or palms down for some grounding. And wherever you find yourself in your practice, either close your eyes or just soften your gaze and start to go inward. Just notice how you feel in your body. Let go of any other thoughts that might be going, and start to bring your awareness to your breath. As you inhale, feel your belly expand, your chest rise. And as you exhale, soften, chest falls, belly deflates. Inhale, breathe into both side bodies, the front and the back body. Exhale, draw your navel up and in towards your spine. Couple more deep breaths. Maybe you'd like to set an intention for your practice right now. And then on your next inhale, gently sweep your arms overhead, reach up, gaze up, exhale, hands through heart center. Inhale, arms overhead, reach up, gaze up. Exhale, hands through heart center. Last time, inhale, sweep the arms overhead, reach up. This time, interlace your fingers, extend your palms up towards the sky. Deep breath in, feel the spine extend. And then as you exhale, twist open to your right. Take your right hand behind you, left hand to thigh or to knee. Inhale, find length. Exhale, draw your navel in, twist. Inhale, lengthen up. Exhale, twist a little deeper. Last breath, inhale, lengthen up. Exhale, twist. Release through center. Take your left hand to the side, palm faces down. Right hand takes your head. Start to stretch your head away from your left shoulder. Getting a nice stretch down the neck, into the shoulder. And from here, you can play with dropping your chin in closer to your chest. Notice how that changes sensation. And then maybe gaze up towards the sky. And as you feel ready, you can gently release back to center. Inhale, sweep your arms overhead, reach up, gaze up. Exhale, hands through right center, twist open to your left. Take your left hand behind you, right hand to thigh or to knee. Inhale to find length. Exhale to draw your navel in, twist. Inhale, lengthen up. Exhale and twist. Last breath. Release back through center. Take your right hand to the side, palm faces down. Left hand takes your head. Start to stretch your head away from your right shoulder. Again, just breathing into sensation. And from here, we'll drop the chin in closer to the chest. And then gently gaze up towards the sky. And as you feel ready, you can release back to center. We'll take our left hand under, right arm over, crossing at the elbows. As you inhale, take a little back bend, arch your spine, lift up, gaze up. Exhale to round, C-curve your spine, chin in towards your chest. Inhale, deep breath in, arch the back, gaze up. Exhale, draw it in. Last time, inhale for a little back bend, a heart opener. Exhale, round the spine. Then come back to a neutral spine. We'll come to eagle arms. So a few options for eagle arms. You can touch opposite shoulder. You can take the backs of the hands to touch, crossing at the elbows, or you can take the full variation, wrapping it around, palms touch, thumbs point back towards face. And then we'll take that same movement through spinal extension and flexion. As you inhale, arch your spine, reach up, gaze up. Exhale, round. Inhale, lift up. Exhale, round. Nice shoulder opening. Last breath. Inhale, up. Exhale, draw it in. And then unwind the arms and we'll reverse the cross of our ankles here. And then we'll take our right arm under, left arm over. As you inhale, arch your spine, take a little back bend. Exhale and round. Inhale forward. Exhale, draw it in. Inhale, reach up. Exhale, back. And then come back to a neutral spine, crossing at the elbows. We'll take eagle arms, opposite side. Thank you so much for joining me in this short hello. I hope you have a wonderful rest of your conference and day.
All right, y'all. We are going to keep it cruising. And I've got some cool stuff set up. Hopefully you can see me. Not sure if you can see me, but I'm going to tell you about a little journey I took in the woods, because in the next break, there is a live meditation that's happening. And so if you enjoyed the yoga, then I imagine you're really going to enjoy the live meditation. Now, let's get back to ourselves. I hope you all are come back to your bodies, have a moment, and then I'm going to take you on this journey through the forest right now, because there is someone that I want to introduce. Okay, so we're looking for a meditation spot right now, but before we jump into the meditation during the break, we've got one next talk. And that talk is from Sarah Cantizaro. She's going to talk to us about the dominant designs in machine learning and challenges that machine learning engineers struggle with. So, enjoy the talk, and oh God, look at that. There's an owl over there. You see that? Oh, you see that over there? Look at that owl. That's a good omen. That is a very good omen. I've got big hopes for this talk coming up. Sarah, it's all you.
Thank you for the intro. It's awesome to be here today. I think there's just such a clear need for conferences like this that'll bring together data ML practitioners so that we can have conversations about meditation and ML. But anyway, if you give me 1 second, I will share my slides. Okay, there we go. So thanks again for the introduction and the walk through the woods. As you mentioned, I'm a general partner at Amplify Partners. My name's also Sarah Catanzaro. And Amplify is an early stage venture capital firm. We focus primarily on investing in technical tools and platforms, and I focus specifically on investing in data and ML tools and platforms. So you might be wondering why the Tecton team invited an investor to critique the design of ML stacks. The fact of the matter is probably that I say some kind of spicy things on Twitter from time to time, but it's actually a problem that I think a lot about. So before I went into investing, I used to be a data scientist. I had most recently led the data team at a company called Mattermark. We were collecting data on other startups and selling it to investors. But when I reflect upon kind of my time at Mattermark and the experience leading the data and ML team there, I think the thing that really stands out to me is that like it's not significantly easier 7 years later to build and deploy ML-driven applications. So that's something that I spend a lot of time thinking about, and it's something that I've been discussing with former colleagues, with friends, with other ML practitioners. But before we kind of get into what I've learned from those conversations, I'll tell you a bit about a meme that became popular back in 2010. So the meme was basically about like how to draw this beautifully illustrated owl. There were 2 steps. First step, you draw 2 circles. One circle represents the head, one circle represents the body. Second step, like draw the damn owl. Now it's 12 years later, and there's just a plethora of ML tools and platforms for like every step of the ML development cycle. But frankly, I feel like a lot of these vendors are basically telling their users to like draw the damn owl. They're saying like, here's a distributed training library, here's a data science framework. Now like build your damn ML stack. And it's frustrating and challenging because I think, firstly, like it's hard to understand what specific problem any of these vendors solve. It's hard to kind of like cut through that marketing jargon. It's also hard to understand how the components of the stack, how these various tools might like fit together. And even if you have some ideas about like how they ought to fit together, it can still be really tough to implement. And so like this is a phenomena that I want to really get into today. But I think before we can start to kind of diagnose like why this is the case, we need to establish kind of more of a common vocabulary, a common language for talking about the ML stack. I think one of the things that I see is that frankly, like there's a lot of like needlessly spirited debate that is happening in the ML ops community because we don't have common definitions. So like when I say feature store and Demetrios says feature store, like we may not actually be talking about the same thing. And so like we may disagree about like the utility of feature stores because we don't have this kind of common set of definitions. So I'm going to present a bit about like how I think about the design and the organization of ML stacks. But I'd really kind of urge the ML community to come up with your own language for describing the ML stack, its components, and associated workflows in more of a uniform way. Okay, so I tend to think about the ML stack as having 3 different layers. There's the data management layer, modeling and deployment layer, and model operations layer. The data management layer is really focused on tools and platforms that will enable you to collect and query and evaluate training data sets, labels, predictions. The modeling and deployment layer would include tools to build and train and tune and optimize and deploy models. Model operations I think of as being kind of primarily focused on enabling users to either meet or potentially even exceed their performance requirements, but also to kind of conform with regulatory or policy standards. So we can double click on the data management layer first. In this category, we have data labeling tools. I think that's pretty self-explanatory, like data labeling tools. They enable users to label data either by providing kind of access to and tools to manage human labelers or more programmatically using techniques like weak supervision. We're also starting to see more and more tools that are really focused on enabling users to evaluate label quality and improve label quality. Databases in this context would mean tools really to like collect and query labels, training data sets and predictions. And I tend to see like two different approaches here. So there are some companies that are primarily using their data warehouse. The data warehouse, it's really optimized for structured data. And so it's commonly used by a lot of analytics teams. And I think one of the real benefits of this approach is actually that ML teams can kind of cut down on some data prep by using the data models that analytics engineers are preparing. Those also tend to be like monitored and tested and possibly even documented. So certainly that can provide some leverage. The other approach that I see though is building a ML platform or an ML stack on top of the data lake. The data lake is optimized for storing and managing raw data, both structured and unstructured. And certainly I think in many respects can be kind of a more flexible approach than the data warehouse. In my opinion, the data lake also tends to provide like a better Python native experience, although perhaps that's changing. The last thing that I'd include within this category is vector databases. These seem to be becoming more and more common for search and recommendation systems and other types of applications that rely upon embeddings. So I don't really need to spend that much time talking about feature management since we're at a conference that's hosted by Tecton. I tend to think about feature stores as being the tools and platforms that are going to enable you to transform data into features, not just features that can be used more reliably during training and inference. They're going to solve some of these like kind of gnarlier technical problems, whether it's enabling accurate backfill, resolving online-offline inconsistencies. I also see some companies that are just using feature proxies. The feature proxy approach can be well suited for enabling low latency feature serving. That may also be a capability that the feature store provides. Oops. Okay, so modeling and deployment. Frankly, I think like there's a lot of like brand confusion in this category, and even I had like difficulty like coming up with names. So like the way that I think about it though is that like deep learning frameworks generally help their users build and train models, whereas data science frameworks tend to help their users create data science projects. I think the real utility of the data science frameworks is that they enable you to schedule and run and log ML pipelines, typically as like DAGs and workflows, and in more of a uniform way. Some of the data science frameworks also provide lightweight experiment tracking and version control capabilities, although for some companies, including those that are iterating on their models fairly frequently, they may choose to adopt an experimentation tracking application, something that is like really purpose-built for that use case. Often it will include kind of more robust visualization capabilities. It might also make it easier for users to like reproduce and package and share models. Next is deployment and optimization. So these tools typically enable their users to deploy models as prediction services, usually containerized prediction services. Some of them and some of the newer deployment tools are also designed to run on the data warehouse. I'm also seeing kind of an increasing number of deployment tools that are focused not only on enabling you to containerize your models, but also that provide some optimization capabilities such that you can achieve certain like production SLAs, whether it's low latency, meeting certain memory requirements, et cetera. And then the last thing in this category is distributed training. So these tools accelerate training, typically by leveraging parallel processing. Okay, only one more of these layers, and then we can get into like what is wrong with all of this. So model operations. Okay. So frankly, like I've been debating whether or not like model operations is even the right name for this category. Luis Seze, I think, had an interview not too long ago where he basically argued that like what we're doing when we do ML is not like building models, where we're building ML driven applications. And so like model operations isn't really a thing. It's more like a specific flavor of DevOps. And I think like there's a lot of merit to that argument. So perhaps like this should really be called like DevOps dash ML or something along those lines. Anyway, I do think that there are some aspects of monitoring and managing ML-driven applications that are unique, that make many of the tools that were designed for DevOps with traditional software applications kind of like ill-suited to that task. Model monitoring is probably a really good example. Many of the tools listed here, they're really focused on enabling their users to detect distribution shifts, things like that. Model analytics is actually a category I've been thinking about a lot lately. So one of the other things I notice is that like product engineering teams, they tend not to iterate on the same feature that frequently. So if you're like building a navigation panel, you're going to release that, but you're not going to like turn around and then iterate on the next version of the navigation panel. You might like revisit in like 2 to 3 years. In contrast, a lot of ML and ML engineering teams will constantly iterate on the same ML-driven feature, whether it's a pricing model or a recommendation carousel. And as such, my expectation is that we're going to kind of need like more mixed panel or amplitude for ML type products. Model compliance, most of these tools generally ensure that like protected attributes are not used to make predictions, help users mitigate algorithmic risk. And in the category of continuous learning, I typically bucket tools that either like automate retraining or enable active learning. So now I've kind of expounded upon like how I think about the ML stack. I think you have a pretty good understanding of my mental models for each of the components. So we can start to talk about, what happens when these components don't work so well together. So the first thing that I'll discuss is like, what happens when the components of the data management layer don't really connect clearly together? One other thing maybe to add before we get into like the specific problems associated with this anti-pattern is that like, I think all of this is going to become much more acute, particularly as companies adopt like the paradigm of data-driven programming, wherein they're iterating on their data sets to improve model performance. But just to go into kind of some specific like symptoms of this problem, obviously, like when you have data stored across multiple systems and those systems are not well integrated, it's going to be much harder to find and access and evaluate data sets. Some companies like kind of resolve this problem by tasking data or ML engineers with making data available to data scientists or whomever is building the model. But then you have ML and data engineers like spending all of their time just moving data to and from S3 buckets. And given some of the other challenges associated with building ML-driven applications, I really find it hard to believe that like that is the best use of their time. The other thing that I notice here is that like, frankly, there's like a lot of duplicative work that's being done, both across ML teams, where the data preparation or feature engineering work done by one team cannot easily be repurposed by other teams, but also kind of across the entire organization. Like I suspect that like a lot of the work that is being done to prepare data for other use cases like experimentation or financial reporting could really be repurposed for ML, but it's hard to kind of like uncover that work. And as such, I think there's a lot of wasted effort. Now, another thing that I think more and more people are talking about nowadays is kind of the challenge of working with unstructured data. Like obviously transformers are like all the rage in the research community, but I don't actually see them getting widespread adoption in industry. I think part of the reason is that like it's really hard for companies today to reason about the unstructured data that they actually have. But I think this could be a lot easier if we had better tools that enabled you to link your structured data to your unstructured data so that you could kind of easily develop a profile of like what might be contained within your unstructured data sets. It was interesting. I actually talked to somebody at NVIDIA recently about how they were solving this problem. So they have developed more of an abstraction such that data scientists can write one query as if they were querying a single database and easily collect data about like LiDAR, CV, like weather data, accelerometer data, all associated with a single drive. So I think tools like that ought to become more commonplace, such that like we can at least obfuscate the problems that occur when you've got data silos. Which may exist for like valid reasons, and we'll go into that in a second too. Okay, so now we can talk about the issues that occur at the modeling and deployment layer when the components of that layer are not elegantly integrated. I think like one example that always comes to mind in describing this problem is kind of the problem of going from notebooks into like production. Most data scientists, or at least many data scientists, are going to start the model development process with a deep learning or machine learning framework in a notebook. But when they're ready to operationalize their work, they are often going to restructure their data as a DAG. And like at a minimum, that's super tedious to have to like go through all of your notebook code and kind of like extract the DAG from your notebook code. This is not to say that like the right approach is running notebooks in production. I tend to be like pretty skeptical about that too. But the whole like notebook to DAG thing, like that's got to get easier. The other thing that I see too is that like the kind of more advanced ML teams, they typically don't treat modeling and deployment as like discrete and sequential stages. So for example, at Stripe, like they'll often like actually deploy a randomly weighted model before engaging in any further fine tuning. And what that enables them to do is to get a sense of kind of the performance profile of the model. I think that type of behavior will make communications and interactions between data scientists and ML engineers much easier. But many of the tools that have been adopted today, they don't really like align with that pattern of working. Okay, so now we can talk about like some of the problems that kind of occur between the layers. So, one of the problems that I see that exists is one that arises when the data management layer and the modeling and deployment layer is not coupled. Like most teams will train their models offline in a batch setting, and like that can still be difficult due to some of the pain points associated with like finding and accessing data that I described before. When you transition to batch inference, like that can actually also be difficult because now you need to reason about like schedules and data freshness and the impact on model performance. But connecting to like batch runtimes is still like a little bit easier. Batch data sets is still a little bit easier. When you start to work with like online inference and online and nearline data sets, like things get pretty gnarly. Like now you've got to reason about like the interplay between model complexity and data volume and client application SLAs. You need to make sure that like your data sets are available in online stores. And in thinking about kind of the various backends underlying your ML pipeline, you need to consider things like query complexity and like read-write latency and transaction consistency. And those like types of like systems engineering problems, like they're very different than algorithms problems or like modeling problems. And frankly, I don't think like a lot of the tools that we use for modeling and deployment are really well designed to help us think about kind of the interplay between like data systems and model performance. Which leads me to just like one thing that I think we need to be talking about more from kind of a philosophical perspective. So like the diagram that is like on my left, which might be your right, that's a schematic about Netflix's recommendation system from like 2013. So like ML-driven applications, they've only become more complex. But when we talk about like ML ops and model ops, we really only talk about like deploying models or deploying algorithms. And as you see here, like an algorithm is just like one small component in an ML-driven application. Those who are productionizing ML, like they need to build all this. They need to think about like connections with UI services and various data stores, and potentially even like authorization services. I hope that in the future, like more ML tools will be oriented towards helping teams build ML-driven applications and like not take this model-centric approach. So, the last thing that I'll go into is just the challenges that I think exist when all of the components of the ML stack are not explicitly or transparently connected. Frankly, like even the best ML-driven applications are still very, they're very brittle today. Including because like the dependencies between these components are so opaque. And for that reason, I find like many companies, many teams are actually like reluctant to iterate on their ML-driven applications, even when they know that like they're potentially leaving value on the table. So one of the things that was like fairly shocking to me was hearing that, companies like Amazon and Stitch Fix, like they only iterate on their embedding models. I think Spotify too, like only once every 2 years. And frankly, I think like the reason is just that like their ML stacks, like they're this gnarly web of different components that is so difficult to unpack. And so like there's an extreme reluctance to change any one component without understanding how it's going to impact the entire system. So it's really easy to like sit in a venture office and talk about like all of the problems, and none of these problems are actually like easy to solve. But I do think that there are like a few things that the ML community, including those who are using tools and those who are building tools, can do better. So for like those who are using tools, I think first and foremost, like think about not just the model that you want to deploy, think about like the architecture of the ML-driven application and what set of tools you're going to need to both build and maintain that application, and like demand that your vendors address the set of integrations that you need to build that reliably and iterate upon it flexibly. one of my kind of hypotheses about like why ML tools and platforms are not where they ought to be is just that like the behavior of data scientists and ML engineers is still pretty heterogeneous. So I think like once we start to establish more best practices and standards, like it's going to be much easier to build great tools because those tools can align with user behaviors. I also think about like, why hasn't this happened? Like it's been 10 years, I think, since like AlexNet. Like, why don't we have clear ways of doing things? I don't actually have an answer to that question, but I do think like both community members as well as vendors ought to be opinionated. You ought to, have a view about how people should work. And once we're able to establish that, and it'll be a dialogue, I think it'll be a lot easier to design tools that enable that type of work, but also to think about like how these various components ought to be coupled to enable that workflow. Like if you know what somebody's workflow is, you can kind of follow that workflow to think about like, what is the set of integrations I need to support? So there are a couple of other things that I've been thinking about, recently, like what role will collaboration play in the future of ML? Like how will the adoption of pre-trained models impact the architecture of the ML stack? But if I had to share like one major takeaway, it's just that like we need to stop thinking about ML ops as model ops and really focus on a stack that is going to allow us to build reliable ML-driven applications and a unified stack that is designed to achieve that end. So that's all I've got.
Excellent stuff,
I will
Sarah.
stop sharing.
I love it. And I want to ask you, do you have a few minutes to stick around and
I
do some live
do.
Q&A?
Sure.
Awesome. So first of all, everybody loved your slides and they want to know if you are going to share them in Slack.
Sure, I'm more than happy to.
They want to share some memes with everyone that will understand where you're coming from.
Of course. I've learned one thing about making slides. It's like, just put as many memes on there as possible. And like, it almost always works. I had done this for like a college lecture and I'm like, I wonder if like, when I'm presenting to like professionals, like they're still going to be like, as interested or excited by the memes. And I was like, well, I kind of like memes, so we'll see.
You can't lose with memes. I think, especially in stuff like this, where it can get really deep and technical really fast, you're always going to have people appreciate the memes. So I'm going to jump into one of the first questions. Let's see. I'm going to go over to Slack. I'm not sure if everyone can see my screen. Hopefully you can. What would be the best approach for coupling back data and ML layers in a mature organization? I kind of see that it's really hard step and it is really less about tools, frameworks, etc., and more about vision. I'm not sure though. Would love to know more about it.
Yeah, so I mean, I do think, as I had said before, like the first step is actually to have like more explicit standards and best practices for thinking about like the design and development of ML applications, and then tools can more effectively like align with those. I would actually debate that it's not just about tools. I think like vendors actually ought to be thinking more about how they integrate with some of the database companies. I was really encouraged like during an earlier conversation with GC earlier this year, we were talking about kind of the importance of like partnerships and integrations for those building products like Tecton. And he had mentioned to me that like they're partnering with companies like Confluent, who makes Kafka, and Databricks, who has their Delta Lake products. And like, that is exactly, I think, like the set of priorities that we need. Like we need those who are focused on enabling modeling and the development of ML-driven applications to be thinking about like, okay, I know this is hard, like how do I make it a little bit easier on my users? And for what it's worth, like we're not even an investor in Tecton. I wish we were, but I think like they're doing the right thing there.
Oh, that's awesome. I mean, I kind of had a bit of a hot question, but I'll get to it after everybody else's because I'm a selfless kind of guy. So how do you see unstructured data processing, images, LiDAR, video, etc., versus structured data processing in terms of market sizing and pains of development?
Yeah. So I mean, I kind of touched upon this a bit earlier. I think one of the things that makes structured data processing and kind of classical ML slightly easier than unstructured data processing and use cases like computer vision and NLP is that like we have very clear ways of profiling structured data sets. Like we know how to come up with summary statistics that will make it easier for us to like get a sense of the data. We could just write SQL queries or like wrangle data in data frames. The other thing that is also, I think, worth mentioning is that like it's a lot easier for humans to just scan a table than it is to like scan a corpus of 2 million legal documents. So I think one of the issues that a lot of companies face is they're like, yeah, there's probably some value in that set of 1 million images that our users have submitted over the past 10 years, but like we have no idea what we would do with it because we don't know it's there. So I think like that's a problem that needs to be solved before we even get into like building applications or building ML-driven applications.
Excellent answer. All right. Is there an MLOps tool or service that most tackles these issues in your eyes? And I mean, yeah, I'll leave it at that. ML-driven application, something like that. Jeff Gross is asking.
Yeah. So I mean, I am not actually a big believer in end-to-end platforms. I think like most end-to-end platforms will not deliver like an optimal experience for everything. And frankly, like they're much harder to future-proof. So I'm much more bullish on tools that are like not narrowly scoped, but like somewhat moderately scoped, but that integrate with other tools well. So I had mentioned earlier that like I cover for Amplify like both analytics and ML. And I think a lot about like the comparisons between like the quote unquote modern data stack and the ML stack. If you look at like the modern data stack, like there are tools for moving data into a data warehouse like Fivetran, there are data warehouse tools like Snowflake, there are data transformation tools like dbt, and those tools work exceptionally well together. Like they don't put the burden on the user to figure out how they ought to fit together. And I think we're just starting to get there with ML. But like, I don't think we're going to see great tools until we have great tools that work well together. Uh-oh.
I think I had a little technical difficulty. I'm not sure if I'm totally frozen on your screen, just like I am on mine, but we'll keep it going. And I'll pretend like that posture is my good side. So hopefully it doesn't matter. Yeah, I lost camera feed. And I'll keep the last question, I think, that I wanted to ask you, and let's see if this will help.
You disappeared.
I know. Now I'm not here.
This is so disappointing.
So, let me see if this works. If I get the backup camera. No. All right. So the question that I have for you, I mean, talking about the ML stack and the data stack, like I'd really love to hear how you think about those two playing nice together. And what, like, you're talking about integrations. Do you feel like there should be two different stacks, or do they integrate nicely? What does that look like in your eyes?
Yeah, you know, it's a tough question to answer. I think at the very least, ML tools should integrate with the analytics stack. Like if you're not working with structured data, if you're not working with features that look like metrics, then like leveraging your DBT data models is probably just not necessary. But I think there are opportunities to use those data sets when building ML applications. And again, like the tools ought to afford that possibility. I also think that like for those who are kind of starting off on their ML journey, thinking about like what is the work that is like being done with like relatively simple models, or with spreadsheet exports from the data warehouse, where we could use machine learning to outperform like our current results. And in doing so, like repurpose a lot of the work that had been done to create the kind of like toy model. So like forecasting might be a good example. I'm sure that like there are plenty of forecasting models that are really Excel spreadsheets that contain data that was exceptionally well prepared within the data warehouse. Now, if it was easier to like build forecasting models on top of Snowflake, then perhaps we could replace those spreadsheets with like something that doesn't lead to like the 2021 supply chain crisis. But now I'm getting a little dark.
We'll keep it light, and we will thank you for this. I see in the chat that somebody's saying they want your email because they want to send you their pitch deck. I guess you're getting a little deal flow from this. Hopefully this is a good day.
I'm just Sarah at amplifypartners.com.
There you go. There you go. Everybody who has something that can ease the pain that Sarah was talking about in her presentation, hit her up. And Sarah, it's always a pleasure. I really enjoyed when you came on the MLOps Community Podcast. I enjoyed your presentation now. Hope to have you back on the MLOps Community Podcast. And we'll see you later. Feel free, everyone, to continue the conversation with Sarah. Keep asking her questions in Slack. And now we're going to move on because we've got a panel coming up. Woo, we're throwing a little bit of an audible right now into the mix. See you, Sarah.
Bye.
So the panel that we've got, wow, this is an all-star panel. Let's just say it that way. And I know that, so I'm going to introduce everyone that we have coming on the panel, and then I'm going to start asking some questions. First up, we've got Maria, and forgive me because I butcher names, but it's Maria Ciparroni. No, not even close. It wasn't Maria. All right. She's a user researcher at Spotify. And we've also got Mark Freeman, founder of On the Mark Data, also a huge LinkedIn influencer. And we've got Kate Kuzanikova, data scientist at the OLX group. And then last but not least, Alice Jacques, head of data science and machine learning at Depop. Thank you all for joining, and thank you for sitting through my horrible pronunciations of your names. How you all doing? How's it going? Hopefully everything is good. Can I get a thumbs up or a shakiness? Y'all been enjoying the conference so far? That's what I like to hear. Okay, cool. So I'm going to kick it off with some things because the point of this panel is really to think about and to walk through some things that engineers should know when they're building for data scientists. And I find this fascinating because we're starting to see that there is certain things that you want to keep in mind, and maybe a data scientist, it's second nature to them, but for an engineer, they don't even realize it. So the goal for this panel is to highlight some of the most common challenges when engineers and data scientists interact with each other, especially the surprising ones. We want to share solutions with the audience that they can implement on their own, right? Some actionable insights, and share problem areas that still persist and we need to figure out. So let's start off this first question, and I'm going to kick it over to you first, Kate. How are data scientists and engineers different and similar in how they approach problem solving?
Good question. Yeah, I think first off, I would like to say that data scientist is such an umbrella term that is very polluted with different flavors right now. So one data scientist is not going to do the same work as another one. It's very hard to find two people who approach either their work or stack or problem solving the same way. And it's starting to change, as we saw in the last year. Some analytics engineers or ML engineers roles started popping up, which make it a little bit easier. But overall, I think it really depends also on the scale of the company and domain that you're working in. How much of engineering will there be in your data science role? And how different are you going to be from what we perceive as a standard software engineer or a data engineer?
I love it. Mark, you got any take on this?
I mean, Kate did an excellent job. I think one way I like to think about is like, where in the data lifecycle do people sit? And one of the key things where I see software engineers fitting is they are data creators. This is coming from a product side, but they're data creators. They're creating the surfaces in which our data is going to be collected within a product. And also they're data surfacers. So, we build these insights, and then they take this amazing data and they show it in the product to the end user. So those are very two important parts that data science itself doesn't really touch often. And so there's a key partnership with that, and thinking about that implementation and ingestion of data. And so it really is a team effort. And so it behooves us to really work with each other.
I love it. Maria, you've got a bit of a different take. Coming from the user experience side, I'd love to hear what you have to say.
Sure. And let me just say that at Spotify, my role is actually to serve as a user researcher for machine learning engineers. So I work with data scientists. I think one thing I want to say, and I'm finding this, I'm hosting a conference this year for quantitative user research, and it's like, is that a thing actually, or is it a competency? And I think those are the questions with data science and machine learning that we're asking a lot. I do think that the scale and the resources of the organization impact a lot what's available. At Spotify in general, I do see data scientists mostly functioning as insight generators. We've talked about potentially, there are data scientists that fill different business contexts, so they might be doing more on the engineering side, but I tend to interact with most data scientists in the context that they're generating insight. I think my take is that at the size and sort of scale of the company that I'm working at now, you can kind of afford to have people specialize maybe more in an area, whereas maybe if you're in a scrappier situation, you need to do what you need to do to get it done.
Great point. Now, let's keep moving. And I want to hear from you, Alice. And I want to know, if you can give us a brief summary of how engineers and data scientists are collaborating at your company, Depop.
Sure. I've just realized that my background is back to front. I hope that's not too off-putting for anyone.
No, it's cool. It's good. You're a new trendsetter.
So our teams are all pretty cross-functional. So most teams will have a handful of engineers, a couple of data scientists, maybe some front end, some back end, and a PM. And I think, just going back to the previous question briefly, because it relates to how they work together, I think something that's really hard for software engineers to understand about data scientists is our experimental approach. And it's very frustrating, I think, if you're used to being a PM or an engineer somewhere that can like plan quite cleanly far ahead. It's a real expectation of adaptation that they can then tolerate me being like, I don't know what my final solution is going to be. I'm going to try these things though. But we've found working really closely and just communicating a lot really helps. So if you say this experiment is looking better, this experiment is looking worse, kind of can help with that interface.
Yeah, makes sense. So Kate, I'm going to throw it over to you. And how are engineers and data scientists collaborating where you're at? Are there that cross functionality like Alice was saying, or do you stay in your lane per se?
Well, I mean, again, it depends. So like if a project has enough resources and it's a fully complected team, we have pretty clear boundaries of where my work ends and where your work starts. So I can really focus, as Maria was mentioning, on like my swim lane and like go really deep into it. However, sometimes there would be some kind of a moonshot 20% project that you just want to explore a topic and it feels more like a hacking thing together. And so whatever you can offer to it, you're going to go for it. Be it starting to create a podcast about this project because you want to get more interest. So like it can even step outside of the engineering world, absolutely, entirely. But overall, like in a perfect scenario, if the resources are there, we would have like an SRE supporting us, data engineers supporting us to like, again, to get the access to the right things and the data in the right place. And then also maybe a bunch of data scientists, right? Or ML engineers.
I get the feeling, Maria, this is pretty day-to-day for you. You've thought a lot about it. Can I hear your thoughts?
Yeah, I mean, I think, you know, and just to clarify, it's how there's partnership with engineering.
Yeah. So,
okay.
Yeah.
So in a sense, the way that, you know, I partner with engineering or also data scientists partner with engineering is really helping to define needs and exploring spaces, really problem space definition. I think I spend the most time on because I find that, you know, other populations, like we talk about engineers, certainly product managers are solution oriented, right? So really to contribute a well-designed solution, I think our engineers get the luxury of us helping them really become experts on the problem.
Oh, that's awesome. That's super cool to hear. And
oh yes, everything's perfect.
All right then, you took us there. Let's hear it. Where's the pain? Where's the pain? Tell us. You can't just say that and expect for me to gloss over it.
I think that one of the challenges I see in terms of like working in a more insight generation role versus, you know, and not that everything's so clean. Certainly I work on solutions as well, but timeline differences and cultural practices that are just different. You know, I am sort of really more interested in knowing the problem. And a lot of times that's seen as like a time suck. You know, like, oh, I don't know how that fits into the sprint, how that fits into the cycle, you know, and certainly I'm probably the most qualitative person here. I need some deep heads down time alone, or I can't help you know the nature of the problem. So there's often a mismatch of sort of time sequencing and the ways people work operationally.
So I actually have a follow-up question for you, Maria, because that kind of brought up this kind of pain point I had as a data scientist when I first started off, is that many times the requests you get for data science are very vague and often the wrong ask first, whether it's from stakeholders or from engineers. And so I work in startups, so I don't have the luxury of having all these specialized teams, but I'm curious your role in doing UX and being this bridge between these different teams. What have you found to be really successful translators between these different teams?
So do you mean like techniques or ways of working that really help?
So it's not necessarily techniques, but like, say for instance, like a business stakeholder might ask, like, can I get the numbers for XYZ, you know, into this dashboard? And many times like the XYZ like ask is actually completely wrong. And the real ask is like deeper in there. And so as a data scientist, I have to like dig through that a lot. Do you find with your role, you're able to really just cut to what's really important to really translate between these technical teams?
So I think that and I'm actually a quantitative researcher by training, but having skills in the qualitative skill set really help, because as user researcher, one of your crucial like kickoff things that you do as a stakeholder interview, and you learn how to do information gathering first, because typically it's similar to your scenario. Someone will come with me with a methodology. They already have it picked out. They're going to tell me how to do the study, which is fine. I'm not saying they're often correct, but I actually often help my data scientists find out what they are going to kind of need, because I am given a little more space and leeway to parse in the more nuanced area, because of UX research normally gets associated with qualitative research. So I tend to be that bridge. And unfortunately, I do think that data scientists do get associated with more of the engineering culture and analytics. And it's like, oh, just go find this thing. Whereas data scientists, many of them are interested in user stories as well, right? They're trying to know the nature of the problem as well, and they need time to do that. So I often run interference that way. I don't know if that answers the question, but it's been one of the ways I do it. I don't think there are a lot of allies for data scientists that way, to be honest with you. I think user research could serve as one of the greatest allies to data science in terms of insight generation, because we've been working in that business for a while. So good. So I'm gonna switch it up, and Alice, I'm gonna throw this one at you. It's a little bit spicier of a question. What's some of the main friction or frustrations that you've seen between data scientists and data engineers, or just engineering in general?
Yeah, it's a very pertinent one to our company at the moment. So the way that data science was initially integrated into the company, they were sort of second-class engineering citizens. So none of the DevX was set up for them. I think there's a difference where things are blocked by default if you're an engineer, like they protect you by not letting you accidentally break things. Whereas if you're a data scientist, you'd need to like install a load of packages and all this sort of thing. So it was essentially, well, no, I was going to be a bit rude. It's not the worst way you could set up an environment for a data scientist, but it was kind of close. So I think one of the things that we've been working through with the engineering team is like, how can we change from like a blocked by default to like an experimental by default approach that lets the data scientist kind of iterate and be a bit freer?
Okay, I like that. And I was hoping for the rudeness, but you're very polite, and I appreciate you keeping your posture or your politeness in this. Kate, what about you? You got stuff and you want to be a bit more raw?
Well, I mean, one of the things that comes up in my day-to-day work is that if you're really mad at how something is done, propose a better way, reach out to that person. If you really hate how your data scientist codes something and it breaks every time, or vice versa, just sit down with them, do a knowledge sharing session, and show them how it's done better, because maybe it's like the 500th tool that they had to use to do their job to adjust to the company stack. And they're not going to be like straight away the best at it. And it takes so little effort to fix and find a common bridge and make everyone happy. But like usually people are too busy to even consider that. And it's just a shame, it could have been so simple.
Could have, and be the change you want to see in the world, huh? So Mark, I know you got some thoughts. I also want to spotlight what you said. I don't think you put it for everyone in here, but you mentioned that UX folks basically give you the cheat code on the insights. I think that's hilarious. But what are some frictions that you've seen? What are some challenges that you've faced?
Definitely. I think one of the main challenges is that engineers and data scientists think differently. I can't remember who presented this in this group, but it's basically that experimentation phase is very frustrating, I think, for engineers, because many times for engineers, you have your like technical spec, and you're like, here's our end goal. You write the code, and like you see, does it work in the product? Yes or no? Are there any bugs, right? And that's a huge simplification engineering. So take that for what it is. There's a lot more complexity to it. But on the data science side, we have this additional step of iterating of like, cool, we did all the right things, just the data sucks or our insight was wrong. And we have to try something new and not be biased. And so a lot of our stuff is like, yeah, we want to try new things over and over again, but we're going to be very intentional of not just throwing all the data and slicing and dicing it in a way to make our desired output. And so I think the challenge is working with engineering is like communicating that iterative part. And that's a big reason why whenever I work on projects, like I add like an extra week to say when I'm gonna have something done, because there's this iterative part, and I put in time for understanding the constraints of what I'm working on and what's gonna blow up potentially. And so getting that across to engineering, and it goes back to what I was saying earlier, like they're like data generators. If you can communicate, that's like the thing you have to iterate on, and we need those clues to figure out what's the best thing to move forward with. Getting that embedded within the engineering kind of culture of like, oh yeah, this is why we collect this data. We're not just doing it for extra work. Helps out a lot in that friction point.
I love that. Now, let's move on to a new question, and I'll throw it over to you, Kate, first. I want to know at OLX, who is responsible for the model in production? Are data scientists getting put on pager duty, or are they getting woken up at 3 a.m. when things go haywire?
Well, personally, I wouldn't be 100% sure because I don't have any mission critical ML models in production. From what I've observed so far, I'm not sure again about the pager duty, but every project has their own kind of distribution of ownership. And again, we also have the SREs that kind of are the main guards of everything working on the spot. So it really depends. I wouldn't say there would be like one single person that is always there to monitor everything. And again, we're also not doing any, it's not like we're doing cancer screenings or something that is like very impactful to people's lives. So that I don't think if something breaks, it would be such a massive impact that you would have to constantly look for people to like fix it and blame right away, like the second it happens.
Great point. How about you, Alice? Have you gotten woken up in the middle of the night because a model gone rogue?
Oh, realistically, we're getting there, and we're all putting it off as much as we can. Our current pager duty is like daytime hours. So you know who's responsible for it if it breaks, but you don't have to fix it until the morning. But ask me again in a month, and I think it'll be middle of the night stuff. Yeah.
Ooh, interesting. And who is the one that's responsible? Is it you? Are the engineers? Are the data scientists? Is it a collaboration between the two?
It's nearly always a collaboration. I tend to be notified, but I don't go and fix it so much these days. It's the data scientists that built it often, or they're in small groups. So just someone in that group that understands it and an engineer together.
Makes sense. Mark, how about yourself?
So I've been thinking about this a lot. Thankfully, I don't have pager duty, but as Alice kind of noticed, like as you increase complexity and stuff, that's going to become very necessary. And I'm increasing complexity at the jobs I work at, startups I work at, and so eventually we're going to get to that point. And I've been asking a lot of mentors and people who work at these larger companies, what are you doing to manage this? And over the years, something that keeps on popping up over and over again are RACI matrices. And RACI stands for responsible, accountable, not confounded, consulted, and then informed. Had the data science hat on right there. But essentially, you create this matrix for all these different tasks. It can be very high level or low level, and it makes it very clear to delineate responsibilities. And when I did this exercise with my team, we went through the whole data lifecycle, and then like the various engineering subdomain teams, the data science subdomain teams, and the leadership. And we went through this matrix and became very clear where the bottlenecks are or where the gaps are for these things. And we're able to get on board, still implementing it. So still early, but it was such a like eye-opening experience of like, why haven't we done this before? It makes this very clear delineation early before conflict to solve things.
Ooh, Yeah, that seems like a best practice. I mean, for everyone that does not know, one thing that I have learned from talking to you a few times, Mark, is that you've got so many acronyms and frameworks, and I love it, man. Please write a blog post sometime with all of your frameworks and acronyms, please, because I just want to hear them all.
Super appreciate it. It's the only way I remember things. So I talk to a lot of mentors, a lot of people who are way more experienced than me, and I condense it in the way I can remember it.
Yeah. What was that acronym you just said? Because I didn't quite catch it.
RACI matrix, so RACI.
Okay.
And a lot of project management people have figured out way better than I ever could. So you'll probably see a lot of great project management folks really detail it to a great degree.
Excellent. All right. We've got another one. I want to know, Kate, how do you feel about productionizing machine learning versus productionizing software? Are they different? What is different? What is shared? I know there's a lot of people that ask in the MLOps community, like, oh, but MLOps is just DevOps, right? But what parts can we say, yes, those are fundamental software productionizing procedures? And then where do we go a little off track?
As a disclaimer, I have not productionized software as a first step, but I think the major difference is the data, right? The data that's coming in, the data that you've trained the model on, and the output. So like that is the largest chunk that makes it so different, and that can also act very unpredictably, that you cannot always control, but you can monitor. So that would be the focus, I would guess.
Excellent.
And that's where everybody has hiccups and problems of how to better, what to look at, when to know, how do you know when the problem is coming, like soon enough before it's completely out of whack, right? So still working on it.
Yeah, things get a little dicey when you add data to the mix, don't they? So Alice, what about you? Do you have thoughts on how they differ, how they're the same?
Yes, I think there's like two specific things that stand out in addition, which would be kind of a regular deployment process. I think for people that deploy software, you do it as a one-off typically, maybe twice off if you've got a bug, but building into the process, the regular deployment, I think is quite tricky. And then the other thing is probably like expectation of testing and coverage. Like I think if you're building software, you can test things thoroughly, because it's not that experimental approach. Whereas for us, like testing a whole model end to end is really hard. And so if you have some sort of CI/CD process that's expecting coverage like software, you're going to really struggle to get stuff into production.
Great point. Let's keep moving. I want to throw this one out there, and Mark, I'll throw this at you first. Can or should data scientists evolve into engineers? I know this is something that you've thought about and you potentially are looking at doing. I know that you like engineering much more these days, but is that the path for most? Should we say that eventually data scientists should learn these best practices for coding just to make systems more reliable? Or should data scientists focus on building the models and spending their time where they can add the most value?
That's a $1 million question right there. That's a lot to unpack. But I think it really comes down to data maturity. What's the data maturity of your org and what's the use case for it? And so for me, like I'm always in startups. I love startups. So having the extra engineering skills, especially the data engineering skills, which I'm like heavily picking up now, is like a superpower now, because I have this understanding what the end product is should be for data science. And I go back and build all the infrastructure to like empower that, which is really fun to do at a startup. But if I was working at a large company, like say, Spotify, that has like all these different things, they're gonna be asking like, Mark, why are you working on all these different things? We have all these people who are hired who are way better at this. Focus on your main thing that can drive value. And I think that's where it really comes down to is, what stage is your company going to be at and what stage you want to help take your company to the next level. And that should define whether or not you should focus on those engineering skills. So for me, being in startups, I heavily focus on engineering skills because it gives me a leg up to really move fast and not wait on engineering to build really cool things. As compared to a larger company, I would have to switch that tactic because they're more so focused on expanding their market share and like optimizing on what's really important. And so I need to focus more so on optimizing rather than like broad kind of skill set.
Yeah, I think I've been called on for the follow-up, but it seems natural anyway. I think we talk about that a lot. We talk about T-shapedness in all domains. I hate to hear data scientists being forced into engineering spaces, but of course I'm in a much more comfortable space. When you like startup culture, that's one of the things you love about it. And of course, I think we do foster and engender that at Spotify too. In hack culture, there are certainly data scientists that I talk to that are doing full-scale advanced machine learning applications, and they're really happy with it. And there's others who are really doing insight generation and staying within sort of a deeper lane as opposed to a broad lane. I think you maybe get the luxury of time and resource. You don't have to do it necessarily. You don't have to be the one who's paged at night. But of course, we know there's drawbacks to that big ship as well. I think, from a user experience perspective, and I'm going to wrap up this comment soon, we are trying to design systems and interfaces in the platform that house both of those types of exploration. Can you engage with machine learning at a level that is more sort of the top part of the T and also be that person who is really deep? Can you engage as someone who's more oriented towards knowledge production and research science, but also productionizing a model? So our platform offerings really try and focus on as much of that experience as we can. Yeah.
Can we double click on that real fast? Because when you're building or when you're thinking about what you're going to build, and I imagine simplicity plays a huge role in that, because you want anybody, or you want people that are, it's maybe a little bit outside of their comfort zone, to start being able to leverage that. How does that play into it?
Sure. So I think awareness is actually one of the biggest problems. We find a lot of data scientists who could benefit from machine learning, but don't know they're having compute resource problems, or don't know that that's an issue. That's why it's interesting for us to talk about these less so as jobs and more so as competencies that you sort of pick up. I think we really try and orient ourselves towards, making efficient and seamless the experiences that we can. Where do you not need to have deep engineering knowledge to engage in this? Where can we kind of make it more seamless for you and have things done behind the scenes that you don't need to necessarily know about? And then where does the experience need to be more interactive so that you can look under the hood and learn? Because I find with data scientists and machine learning engineers, if they're looking at, the way a parameter behaves, they need to go under the hood in that experience. But there's also things, the efficiencies and things that can be automated for them that they don't need to sort of waste time in. It requires really deep contextual looking at the scenario that each individual finds themselves in. I think in the last talk, I heard the speaker say that they're not really a big fan of platformizing everything. And I would almost have to agree. It's really difficult, given the amount of context switching that we do, to make an end-to-end experience that every user can really engage with. So I'm just, as a qualitative researcher, trying to find those common spaces where someone needs to be able to learn and it will help them to learn, and then where they don't necessarily need to be bothered. Does that make sense?
Yeah, completely. And it brings up this point in my mind that I've been thinking about a lot lately. And I know a few people have mentioned it to me in the community too, is looking at, when you're building systems, what parts do you automate and what parts do you feel like you need to be involved in? Because you don't want to automate something that's potentially wrong. And so maybe Alice, could you talk to me about how you think about automating versus bringing that human touch?
Sure. So I think we have different use cases for different products. So our recommendations, which we know really well, and if they go a bit wrong, it's just someone has a bit of a bad experience for a day, they're all auto retrained and fully automated. And we feel quite comfortable with that. But we have some products that are trust and safety based. So like, if you think chats are getting abusive, or if you think someone's uploading fakes or trying to be fraudulent, and those, like, we would never consider automating the retraining of, because if it went wrong, it would have such a negative impact. So yeah, I think impact is just a big part of it for us.
Mark, you got some. I saw you nodding your head yes when I was talking about that.
My computer was actually about to crash, so I was actually nodding to try to get my my charger to work, so I can stay on this lovely panel. But if you repeat the question, I'm happy to go forward with it, or you can just skip me because we have some amazing other panelists.
Well, I think we can actually take that as a sign and wrap it up, because this has been incredible, and I don't want your computer to die on us, Mark. I want to thank all of you, Kate, Alice, Maria, Mark. These insights were just superb, and it's cool to get these kind of diverse viewpoints, and hopefully some of the engineers that are watching have learned a little bit from what we talked about here. Thank you all. I appreciate it.
Thank you, Dee. Thank you.
Thank you. So much fun.
Thanks for having us.
And there's all kinds of great stuff that's happening in Slack. So if you want to keep talking to these folks, feel free to hit them up in Slack. I appreciate all of the questions that everyone put. Sadly, I couldn't get to them all. I had a list of like 50 other questions that I wanted to ask them. It's not every day that I get to have such a buffet of a panel of like incredible minds, but we'll keep that conversation happening in Slack. Now, we're going to move ahead. Before we do, I'm going to come back to a little bit of a guy that you may all be familiar with by now. And we're going to introduce our next speaker with this lovely guy.
All right. I know I told you we were about to have the meditation, but we hit a bit of a snag. We're deep in the wilderness here, and what you can see is that there's a family of wild hogs that we've run into just up there. You probably can't see them on the camera because, it's they're hiding. But they don't take kindly to our folk around these parts. So we're trying to stay low, stay quiet, so they don't hear us. Meanwhile, while we're trying to wait this one out, we've got Dr. Waleed from Anyscale. He's the lead engineer, and he's going to give us the next talk. Hopefully, by the time the talk's over, we'll be finished with all this nonsense, and I'll have found the perfect meditation spot. Dr. Waleed, take it over, man, and we may need your help as a doctor in case these boars find us.
Wow, I don't know where to take that intro from there. It's an absolute pleasure to be with you folks again. I had such a blast last time with Dee at the last year's Applied conference, and I'm really grateful for the introduction. I had engineering at Anyscale, and with that, let me just present my slides, and then we'll take it from there. Cool. So hopefully everybody can see that, and yeah. Today I'm going to talk to you about something that I really feel passionately about, but is also kind of a controversial topic, which is, are we on the verge of production reinforcement learning getting to a tipping point where everybody wants to use it and everybody is using it? We all know that, often there's a very standardized ML, way of doing ML, which is training, modeling, monitoring. Reinforcement learning challenges of that, but the results and the potential are very huge. And I specifically chose a controversial topic, and I look forward to your questions during the discussion. So here's the overall view of what I'm trying to say. Basically, research is showing that reinforcement learning is doing amazingly well. All of the superhuman performance systems that we've seen, like AlphaGo, AlphaStar, Dota 2, all of those are basically reinforcement learning based.
And even as recently as yesterday with the release of Gato, which is this new system from Google that can handle 600 different tasks or more, at the heart of it is a little bit of reinforcement learning, especially for the robotics tasks. But yet, we very rarely see in production, RL, reinforcement learning in production. And why is that? So as we try to explore this question, I'm gonna, I think sometimes we get freaked out by RL a little bit because it's something new, but I want to show how it's a very natural extension of things that probably many of us do already. I'm going to come back to that question about is RL at a tipping point or not? And then based on our experiences, I want to share some tips for finding successful patterns of RL applications and some traps to watch out for. And so I'm going to give you my conclusion, which is basically it's not yet off the shelf for a lot of problems, but there's kind of little bits of problems and areas and patterns where it's starting to become incredibly promising. And these stories are based on our experiences at Anyscale working with people using RLib. RLib is an open source distributed reinforcement learning system. There aren't many of those around, especially ones that are production ready. So these are stories from our customers and ones that we've observed as people have used RLib. So I want to go back to this thing of just explaining RL in terms of a complexity spectrum. And really, I'm hoping that by doing this, we can build a mental model of what is easy to do with RL and what isn't, and also provide kind of a map. You know, we're starting off with some things that all of us may have used, like bandits, and then hopefully this will give us an idea of like how to escalate as we start to dip our feet in the water of reinforcement learning and take it further. And especially as we talk about deployment, we're gonna move on. So first, we're gonna start with bandits. Now, I'm curious. I was actually going to ask you folks, and maybe Dee can summarize it. You know what the people's comments are. But who has used bandits in production? I mean, they're a fairly straightforward, well understood technology now that we've been around for a while. But just to introduce the problem to you, if you haven't seen it before, imagine you have 4 slot machines, and each of the slot machines gives you a payout based on a probability that you don't know yet. The state is basic. There's not a lot of state, but your choice is which of the levers do I pull. So one of the machines might pay out $10 if you pull the right one, and it might charge you $1 if you don't. So a good example of a practical example is UI treatments. Imagine you have 5 different ways of presenting your UI. You're not sure which is the best. It's kind of like the same type of problem, right? One of them is better, but you don't want to test them all uniformly, right? And so this is a great example of one of the problems. So I'm just going to ask a question and maybe we can get back to it. But who here has used bandits or experienced bandits and used them in production type scenarios? I'd love like just a yes, no type answer just to see how folks use them. Yeah, so everybody, you know, I'm getting a lot of yeses and nos. But the real challenge with bandits compared to conventional machine learning, to move on. So I'm seeing a lot of people, yes, no, maybe 50% yes. Is the explore-exploit trade-off, right? Like you always have this problem at the heart of it, which is how do I balance between executing on what I already know to be true in terms of the probability distribution and learning what the ground truth is. So to give you an example, a very typical algorithm is what's called epsilon greedy algorithm. And what you do there is if it's less than epsilon, you do some random thing, but say it's epsilon is 5%. So 5% of the time you do something random just to see what happens. And 95% of the time, you're executing on the policy you already learned to really maximize the rewards. So let's take the next stage, right? So some of you may have used bandits. The next thing after bandits are what are called contextual bandits. And again, going back to our analogy of machines that are slot machines, contextual bandits are just like bandits, but there's these variables that affect the performance that may not be visible to you. So for example, imagine now that, you know, they do some pretty dodgy things at casinos sometimes. And imagine that they wanted to change the payout depending on whether it was sunny outside or not. Then the sunniness state would be the contextual variable, and that would affect the payouts from all of the different machines. You know, that's kind of like a very natural extension of bandits. And actually that's seen a huge amount of uptake in recommender systems. The usual configuration is the context is something about the user's profile, and the actual state is like a set of TV shows that you're presenting for them. So they watched TV show 1, and now they're trying to choose what to choose next. and you use a contextual bandit to kind of say, well, based on this user profile and that they watched this episode last, I'm going to suggest that they watch this or give them some options. And this is being very extensively used at places like Netflix and beyond. So that's kind of stage 2. Now, this is where we get to the really interesting part. This is what most people would think of as reinforcement learning, which is going back to our contextual bandits. You can think of reinforcement learning as nothing more than contextual bandits with state. In other words, imagine that I have to pull the levers in a certain particular order to get a payout. So say I have to pull 3 first, and then 4, and then 1, and only when I pull the sequence 3, 4, 1 do I get a $100 payout, right? And a very practical example of that is chess, right? Moves do not lead to a payout in the short term always, right? Like I move forward a pawn, nothing really happens. I don't catch a piece, I don't do anything like that. But those early moves can make the game, there are very long chains of connections of states within the game. And so that's the new problem that reinforcement learning introduces, which is really this idea of temporal credit assignment. If I have to go through a sequence of steps to get a payout, how do I work out how to distribute the reward over the last few moves so I can work that out? And of course, there are ways that you can unroll state, but you kind of have to do some kind of temporal credit assignment. That gets hard. The state space gets very large. So there are approximately 10 to the 80 possible chess games. And then just as there's assigning things to the past, there's also a delay problem. So what happens if your reward is delayed? We gave the example before of 3, 4, 1 gives you a $100 payout. What if it's 3, 4, 1, and then after that, you can 2 moves after that you get the $100 payout, but you don't know that it was 3, 4, 1. So when there's a delay in reward, that makes it even more complicated. And a good example is a sacrifice move in chess, right? Like early on in the game, you might give up a piece for advantage, which has actually got negative reward in the short term, but the reward is like 15 moves later, right? And so this is the type of problems that occur once you move into what many of us call reinforcement learning, right? But one way, all I'm saying is that you can see reinforcement learning as a very natural extension of contextual bandits. The next thing, so far we've gone bandits, contextual bandits, typical reinforcement learning. Now it starts to get interesting, right? We start to expand what's called the state space. Where am I in the game? What's the state of the board? And the action spaces. What are the stages that I can move? So let's go back to that contextual bandit. And now instead of 4 machines, I have 32 machines. Suddenly my space has expanded very hugely. And imagine now, instead of having to pull one lever, I basically have to put a bet on the levers, or I have to pull some of them hard and some of them soft. Suddenly my action space is now 32 dimensional, right? And of course that dimensionality grows and it makes it really, really hard. So the first way, once we get to those standard reinforcement learning problems, is machine learning gets hard, is through that state space growing very large. Now, another problem is with reinforcement learning is what we've talked about before is kind of this, a very sequential process. I have a probability distribution, I make a choice, I observe the output, and then I see what happens again. But for so many of our problems, especially in the real world, I don't get that luxury. I just get a log. I just get, here's what people clicked on yesterday. I don't get a chance to iteratively build it. I don't get a chance to do that. So again, going back to the bandit example, this is, imagine that you go to the casino and they say, go play. And here were the payouts yesterday. Here's what people did. Go and try and learn a reinforcement learning policy from this. And a good practical example is learning from historical stock purchases. I can't really test ideas as around unless I build like a kind of a stock market simulator, which you can do. And but it is really, really starting to become a very common model. And there's been a lot of research in this space recently on offline reinforcement learning. In other words, how do I build a reinforcement learning model when I can't actually run the experiments that I want to run? And just like these other stages, like when we did RL, it introduced temporal credit assignment. When we talked about large state spaces, we talked about the cursive dimensionality. When you move to offline RL, you kind of stuck with whatever experiences the robots or the agent has gone through. So what if you trained your stock market agent and there was never a recession in your data, right? You might end up with the agent kind of going, I'm just going to keep buying stuff because the prices are so cheap. Or again, thinking about those contextual bandits, there might be like a bankrupt thing. So if you pull 3 times in a row, it just says, sorry, I'm going to take all of your money. And if you haven't seen that in the training data, if you haven't seen that in the offline, you can end up in some very weird situations where you shoot yourself in the foot. So we've talked about like how we got, from very basic types of from bandits all the way through to these very complex offline RL applications. The last model of RL that is applicable in many cases is what's called multi-agent RL. And so far we've been talking about you as a single person pulling the levers. What if there's 2 of you? How would you do then? How would you share probabilities? How would you share information? Do we set it up as a competitive situation where the goal is to earn the most money? Do we set it up as a cooperative situation where the goal, like whatever you guys get together, we cut it in half and share it between you? All of these particular types of things take us into a very, very complex and rich realm, which is the realm of multi-agent reinforcement learning. And one way to think about that is, the stock market, there's an assumption of a lot of very small players. But imagine if you're, I don't know, to think of an old joke, frozen concentrated orange juice, right? There might only be 5 or 10 people that are involved in that. And then you can model, what are their motivations and everything else. So the problem with multi-agent RL is it gets way more complicated. What happens to your reward function? How do you define your reward function? And how do you model the different agents? Do they each have kind of a different model? Do they share models? All of those kinds of questions. So just to kind of summarize this and kind of bring us back to kind of where we started, which is this discussion about, is machine learning, is RL at a tipping point? What we see is that there are these set of problems as we go from simple to complex when you try to use reinforcement learning. At the same time, though, we have to come back and ask ourselves that question, is it at a tipping point? And the things that would suggest that it is at a tipping point is, again, this huge victory in competitive environments that, like I remember playing in AAAI 98, a Go machine, and everyone thought it was a joke. It was just so bad. And nobody thought we would ever be able to beat the game of Go using computers. And yet that happened 3 or 4 years ago. The same thing with StarCraft, right? This was thought to be an unachievable thing. And it's seen this huge success. And there's also a huge number of companies that are not just using RL, but using RL in production. All of these companies we know use RL for some kind of production application, for real, for suggestions or recommender systems or for modeling agents, all of these types of things. So we know that that's starting to cross the boundary. But why isn't it becoming more popular? I think, just reflecting on those levels of complexity that we saw earlier, there's really 4 factors in my mind that have stopped it from becoming production ready. And those, we'll go through each of these. And the good news is that for each of these problems, we are seeing really good progress on techniques to deal with them. So I'm going to go through each of them now, and we can discuss each of them. So here's the thing that they don't say when they tell you that AlphaGo 0 beat human players. And then on one level, it's amazing. On the other hand, you start to realize that AlphaGo 0 played 5 million games against itself. That's way beyond what the power that a human can do. But at the same time, that's, it's only a company like Google that knows how to play 5 million games of Go in an efficient way, right? If each game takes a couple of hours, you can do the maths. It doesn't, 10 million hours is a lot of hours, right? And the same thing for AlphaStar. Each of the agents was trained for 200 years. That's way more than a human would train. So this is clearly beyond the capabilities of a simple machine. The good news is we're starting to see progress. One is, again, to plug my own company, we're seeing a lot of improvement in algorithms for training, so you're not stuck to a single computer. We're starting to see transfer learning happen, so you don't have to start from scratch every time. As I mentioned earlier on Gato, which is this new system that Google announced just literally days ago. And it, as I mentioned, performs on 600 domains, not all of them reinforcement learning, but you don't always have to start from scratch. There are techniques called behavioral cloning or imitation learning, where you can start with a human expert and copy them. And there are also ways you can do that by reducing parameterized state spaces, limiting actions, and a few other techniques. My point here is, these are huge. And I see someone saying games have unlimited data, RL agents winning those often need absolutely huge amounts of data and sampling. So you're absolutely right. I think, Jonathan, you asked an absolutely brilliant question, and I 100% agree with you. But let's talk about that. Okay. So the second challenge, talked about, one was lots of training data. The second one was naive implementation of RL is online. In other words, like I said, it's designed to run live. And the idea of running anything live with a changing dynamic model in production should be pretty scary to most of you. Or if it isn't scary, believe me, when you try to do things in production, it's hard enough to get a model that's locked in, working, right? Imagine a model that's actually changing in real time. And the second thing is, it's really hard to get data to train it on. You basically have to run all of those simulations that you ran before again, right? And so there has been a lot of progress here, right? The first one is offline training algorithms that can learn to benefit from that data. And what you can also do is start to add counterfactuals, things that you check that are not broken in the system, and dealing with that. A question, yeah, so we'll come back to the questions at the end, and we can discuss some more. The third problem is temporal credit assignment, right? Like, so we talked about this very, very complicated issue where, you don't know exactly which action is the one that led to you winning or getting a reward. And of course, that also makes things much harder. And the answer to that is, you'd be surprised how many problems the temporal aspects don't always make a big difference. But there's been a few advances in what's called the deep queue networks and a few other techniques that have helped a huge amount. And then the fourth one is large action and state spaces, right? And it's obviously very, very hard to do this. This is kind of related to the first issue that we talked about, which is high training requirements. And the implication is, there's just too many things to learn in real life. And the progress here is, really on high fidelity simulators. And we'll talk about that a little bit later. But for example, for robots, there are really good simulator systems now available, like ROS and even Unity for simulating robots. You can train many simulations at once and kind of hybridize the results. You can also use techniques like embeddings, and they've actually turned out to be critical. So you could do this in 2 steps. Or if you continue with that offline learning path, maybe you don't have to start from scratch every time relearning your model. So as we've discussed, there's those things that are real constraints. There is progress on them, but we have to kind of realize that those constraints, the large state spaces, the high amount of training that you need to do, the offline nature, those things are real. But is there spaces? Are there parts of machine learning problems that we think, or types of problems where we've seen good success despite those constraints? And the answer is, in our work, we've seen 3 of them. Really, one is, if you have a good simulator, you're halfway done, right? And then other situations is, we talked about temporal credit assignment. Do you really, really need temporal credit assignment is a good question. And then the final pattern is problems that people have solved before as optimization techniques. So some of you may have, some of you may remember the field of operations research. They were already working on optimization problems long ago. That shape of problem, things that people would previously use things like linear programming for, sometimes you can just take out that and plug in a reinforcement learning algorithm. Right, so let's go through each of these, and I'll give you some examples of where we have seen this approach work. So we talked about simulated environments, and like we said, it takes a lot of data to train them. But if your problem is virtual in its nature already, or your simulation is a faithful representation of reality, then rather than training your reinforcement learning in the real world, you just train it in a simulator. And you can run all of those simulators at once, and all of the different simulations update the model simultaneously. And so you can batch models together. Another variant of this is getting close with a simulator and then doing the final stages and refinements in the real world. So let's say you have a robot what you do with the robot is you basically train it in the simulator for 90% of its journey, and the last 10% is done in real life. I think that there's a lot of really good opportunities there. This simulator thing is so important that some people are solving machine learning problems like the offline learning problem by building a simulator first, having the robot learn the policy from the simulator. So sometimes we're actually seeing the problem being inverted and turned on its head. So a good example of this is a company called Riot Games. I think some of you may have heard of the game League of Legends. They had a card game, like this is the one where you have decks and the different cards have different properties. And so they turned that into a reinforcement learning problem. And the way they did that is, the state is like the state of the game, who's winning, what are the remaining cards. The action is which card to play, and you get a reward for one win. Now, the problem with, in games like this is game balance. So what this team did is that they basically created 10 typical decks. And so you have 45 combinations of games, and you just play them over and over and over again in a simulator. And then you see if any of the decks has like unusually large victory percentages. And so this allowed Riot to fine tune a commercial game. And I think this is like a very, very interesting application of reinforcement learning. But we're starting to see people use reinforcement learning in other aspects of game, notably QA testing. So you build a reinforcement learning agent that breaks your game, that plays your game, trying to find bugs in it. It doesn't have to be multiple players. It can be just straight against the environment. A second customer is like the simulations don't have to be perfect. But one of the people who talked, we had an RL conference a few months ago, is JP Morgan, and they were modeling foreign exchange transactions. And often it's what I described earlier. There's a few big players in the market. And so the state is just the holdings of each party. And then the action is buying and selling. And then the reward is just like the profit minus the leftover stock. And so you can now run a simulator of the market, which is basically a market where you model the flow of finances. And then you can use that to test like automated trading systems in real life before you release them into production. So we talked about class one, which is if you have a simulated environment, you can create simulations. But there's another set of problems, right? Which, remember where we started this journey? We started with bandits, then contextual bandits, and then sequentiality. So the question is, how many problems are there that are, so one way to think about it is a contextual bandit is just a reinforcement learning problem where the reward only depends on the current state and the future reward only depends on the current state, right? And, it's a gray area then, like how much does it depend on the current state? So imagine that your state can be simplified or unrolled or any of these types of things to kind of represent the state in a way that you can actually apply it. And this is kind of really taken off. So right now for recommender systems, so for example, one person who's done this work is Wildlife Studios, another games company. And they basically look at the last few games that you've played and your user profile. So it feels like that contextual bandit. And then they basically present, here are the 5 games you might want to play next, and you click on one of them. So one problem that occurs when you think about this is, wait a second, there's got to be like millions of users and thousands of games. How do they know which is which? And this is where techniques to deal with large action and state spaces come in. And the big hero here is really embedding. And that's why there's been a lot of success in this space to deal with that. In fact, this particular problem is so successful that you can now go to Microsoft or Google and say, I want to recommend a system based on reinforcement learning. And they will give it to you and you can pay dollars for it. Now, there is a little bit of an asterisk there, which is that, you have to have these constraints. You have to have quite a lot of data before you can use it, but you can do it. And then finally, the last patent is, one take is that on RL is it's a way of doing optimization problems, but in a data-driven way. So, and so you can take over from companies that used to tackle this, like in industrial and manufacturing, and just apply reinforcement learning as another way to solve the same problems. And the great thing is, optimization problems have the same shape as reinforcement learning. It's just you're yanking one algorithm out and putting another algorithm in. And so one example is Dow Chemical. And so they were using reinforcement learning for scheduling different production lines. And what they could do is, you basically have to work out, all the different systems. and what you do when and when you build it. So the state is like how you schedule it, and then the reward is just the money saved. Now, historically, they did this using traditional operations research approaches like mixed integer linear programming. And but now they could actually compare the performance of reinforcement learning agents against it. And so what you can see here is like the improving in time. And in the end, they were actually very competitive with the mixed integer linear programming, and in many ways were more robust to things that were outside of the usual state space. So we're almost at the end here. I just want to leave you with a couple of tips, and we'll take it from there. But the first tip is just to keep it simple, right? So you can start with stateless and then transition to contextual and then fully stateless. The same thing with on policy to off offline. So start simple and work your way up. And the second thing is, we talk a lot about MLOps. No one's really started to think about RLOps. And the reinforcement learning development workflow is some ways different. So you need to make sure to give that room. So how do you validate the models? How do you update the models? Do you run with a live model in production? How do you monitor for situations where the reinforcement learning algorithm is well out of its comfort zone? How do you retrain when really, log data is actually a type of offline data? So it's not the ideal way to train a reinforcement learning model. These are real problems that you have to deal with when you deploy RL in production. So, to just kind of conclude and leave you with some departing thoughts, I think we've seen a tipping point in some areas, but by no means universal. There are a few early adopters that are succeeding. We see three patterns. So things that there are simulators for, things that are like on the edge between contextual bandits and reinforcement learning, and optimization problems. This is where we're really seeing things take off. And the two practical tips are, you don't have to start, with the most complicated multi-agent offline, blah, blah, blah type learning model. Start at the basics with bandits and work your way up to reinforcement learning. And then finally, really think about the deployment workflow. We really need to start to engineer RLOps essentially and create this new field. And finally, we have a library that can help. So I'll just leave it there. Here's a link if you want to find out more about RLib. There's my email address if you want to reach out to me. Please don't hesitate. And I'd especially like to thank the team behind RLib. Thanks all.
I'm going to reach out to you, Waleed. I got to get you on the MLOps Community Podcast, and we'll rebrand it as the MLOps Community Podcast just for you when you come.
Oh, that's so sweet of you, D.
Thanks, man. This was super cool. I see there's a ton of questions coming through, and I'm going to invite everyone to ask Waleed in Slack. I will ask one question because it's just, we got you here, and I want to take advantage of that.
Yeah.
So, Dr. Waleed, you mentioned reinforcement learning being deployed for recommender systems at Netflix, Google, and others. Mm-hmm. What about the rest of us? How much data and training time do simple reinforcement recommender systems need?
Yeah, so they are sensitive. They do need a fair amount of data. But again, you don't have to solve the whole problem. So think about embeddings, right? You don't need reinforcement learning to build embeddings. If you can front load things like embeddings so that you're basically dealing with a small amount of data, like products you can embed, movies you can embed, right? Like there are common features. Then really we're talking about tens of thousands of examples, ideally hundreds of thousands or millions, but even at tens of thousands of examples, which is within the reach of many of our businesses, especially over time. It turns into a competition between concept drift, like how much data do you have between where the concept is stable and the amount of data that you have. But contextual bandits are basically off the shelf now. What's the harm in trying it if you're already using some other recommender system? It's really easy to plug them in. And I'll be on Slack if anybody has any more questions for me.
There we go. There's a ton more questions for you. So you're going to be busy for a little bit.
Sure. I look forward to it.
Yeah, I'm stoked at how you explain things. I really appreciate it. It's a super complex topic and you distill it down. You bring some real life examples. And speaking of real life examples, when you were asking about if anyone has used bandits before, there was somebody in the chat that said that they used they used slot machines before, that person gets some swag. And so whoever it was, I'm going to try and find it real fast. I'm giving you some swag because that was funny. It made me laugh, and I appreciate the humor in there.
You should flip a coin to see if he gets the swag or not.
Yeah, exactly. That's what we should do. Oh, to really like bring it home. This is getting a little meta right now, but Waleed, thank you, man. Hope you liked my intro for you. I'm going to have to do it up even better when you come on the podcast.
Yeah, I look forward to it.
Yeah. Cheers.
All right. Catch you around day.
So we've got a little bit of a break. As I mentioned before, we are going to do a meditation, and me from the past is going to guide it for you, but I want to highlight a few things before we jump into this blissful state. If you have not filled out the event survey, we're dropping a link to that in Slack right now. Feel free. We would really appreciate it. What can we do better? What did you like? What did you not like? The only way that we can bring this high quality, high caliber event to you is by getting your feedback, staying in contact with you. So we would love it if you filled it out. It would mean a ton to me. I want to know, how can we get better? I'm continuously thinking about improving this event to make it the best out there. And so when people think about MLOps events, they cannot help but say this. So that is that. Check out the link. It's in Slack. And we've got an 8-minute break right now for you to either meditate or chill or go get some food, a snack, have a bathroom break, and we'll be back real fast. Before you know it, especially if you're meditating, it's going to be a little bit blissful here. So without further ado, I'm going to take you to me from the past, and we're going to have a little serenity. Okay, so now we're going to do a meditation. I would like to invite you all to find a comfortable place. Try and sit with your back nice and straight. And if you would like, you can put your hands on your knees. You can rest them in your lap if it feels more comfortable. Whatever is the best for you. As we begin this meditation, I find it's easier for myself to do it with my eyes closed. You, however, can do you, however you feel like you want to do it right now. So we'll start taking a few deep breaths in and just letting our exhale be free, releasing any tension that we may have. If you need to make any sounds or noises when you let your exhale out, that also is fine. The good thing is nobody's around to judge you. And as we begin to focus in on our breath, start to notice what kind of thoughts are going through your mind. And start to focus more and more with each breath on the breath itself. Recognizing how your body moves when you inhale, noticing your chest, your rib cage, the lungs filling up. And then as you exhale, all that air out of you, seeing how it manifests in your body. We're letting ourselves become one with our breath, letting all our attention fall onto our breath.
If at any point you recognize that your mind is no longer focusing on your breath, you can just gently nudge it towards the breath, coming back to the sensations in your body. Continue to let yourself be breathed. Let yourself experience the inhale and the exhale. You don't need to force anything. Just experience. Feel whatever it is. As we come to the last part of our meditation, I invite you to put your hands over your chest, the center of your chest, if it feels right for you, and begin to think about one thing that you're grateful for. Think about something that you can feel grateful for right now in this moment, and let yourself dive into that feeling of gratitude. Feel that appreciation, feel that gratitude, and let it engulf your whole body until every cell in your body is grateful. Let that feeling grow just a little bit stronger. arms relax if they were up. Let your gaze down and you can blink your eyes open. I want to thank you all for participating in this meditation with me. Hopefully you found a moment of peace there. Now let's get back into the conference.
I know what you're thinking. Did I participate in the meditation? Yes, I did. So hopefully that gave you a minute to take your eyes and move it away from the screen. We're back with more conference now. We've got some last round of lightning talks before we finish out day one. This is super exciting. I want to just let everybody know, thanks for being with us. Thanks for enjoying this. And as we mentioned before, please fill out that feedback because that will help us get better. Now that I am totally relaxed and breathing deeper, I would like to introduce on our next guests. But before I do, one last final announcement. If you would like to sign up for the workshops that we have after these lightning talks, there's still time. You can find the link to the workshops in Slack. We're going to throw it in there. And we've got 2 workshops going on. 2 right here. Forgot how to count. So 2 workshops are happening after these lightning talks. Go get after it. Get your hands dirty with some code. And now let's hear our lightning talks. Next up, we've got Pietro and Travis. And Pietro, it's funny timing, huh, man? I mean, we said that we were going to have you on the MLOps community podcast soon. But I don't, where is he here? Colin Pietro, there he is. So we said we were going to have you on the MLOps community podcast. Just so happens that this week I interview you, right? So, but today we've got Travis. It's tag team, double the fun. I'm going to let you all get started because lightning talks are going to be fast. I'll throw 10 minutes on the clock and we'll get cracking. See y'all.
Perfect. Thank you very much, Adi. And yes, timing is absolutely perfect. We're going to chat later this week, but right now, me and Travis are going to tell you a little bit more about declarative machine learning systems, in particular Ludwig in the open source and Predibase, which is the company that we started and the product that we're building to bring this concept to market. The basic concept is that we believe that in the machine learning space today, there is a false dichotomy. On one hand, there is like a do-it-yourself approach. We have low-level APIs. And on the other hand, you have AutoML that automates the process. But we believe that it's a problem. These 2 solutions don't solve the underlying problem. The underlying problem is the inefficiency of the machine learning development process. And this is my personal experience when I was working at Uber specifically, where I was working on a number of machine learning projects. The first one was an intent classification system that contained many lines of code, TensorFlow code, took 5 months to develop and 7 months to deploy. And then I worked on a fraud prediction problem with 900 lines of PyTorch code, 5 months to develop and 4 to deploy. And then there was a product recommender system and a few more. And the observation from this process is that machine learning projects basically have too long time to value. Each of these projects took basically a year to deploy. And every single time you implement a new bespoke solution, and that creates technical debt, and it's really low reproducibility. And finally, organizations have difficulty hiring machine learning data scientist experts. And so they need a more efficient way to develop machine learning systems. And so that dichotomy that we were talking about before, we believe that with a declarative machine learning system, you can get both the flexibility of a low-level API do-it-yourself approach with the simplicity of an AutoML solution in the same place, because you have a higher abstraction that keeps both the flexibility, the automation, and the ease of use. And also non-experts now with a declarative approach can be empowered to actually use and do machine learning. And we pioneered these concepts with Ludwig in the open source and Overton since 2017 really, but more recently with 2019 release of open source. And so how does Ludwig work? Ludwig is an open source declarative deep learning approach. And basically the idea behind it is that you can use a configuration system, a declarative configuration system, instead of writing your own code for doing your machine learning projects. And you can see on the left-hand side, there's an example of the configuration, only 6 lines of YAML that are needed to basically replicate exactly what was the first intent classification model that I developed when I was at Uber, and it took me more than a year. So this makes development much faster. Also, you don't need to write low-level machine learning code for doing that, and it's also readable and reproducible. At the same time, it keeps the flexibility of an expert level of control. So for instance, you can change all the pieces and all the details of your model and your pipeline through changing parts of the configuration. For instance, you can change how the data is encoded, or what the training parameters are, or the details of like how many layers, or basically every single aspect of the model. And this makes it really easy to iterate and improve the models. And it's also extensible because you can add your own pieces of code that then are referenced through the configuration system. So you can extend it to whatever you want. And finally, it already contains advanced capabilities like hyperparameter optimization, already state-of-the-art models available for you, and also distributed training. The basic architecture of Ludwig is this encoder, combiner, decoder architecture, where you have the input part, where you have many different data types that can represent the columns of your data, and they are preprocessed and encoded to a common vector representation. It is combined by the combiner, and then you have a decoder that predicts, depending on, again, the data type of the data that you're training on, predicts the output of the model. And so this is an end-to-end deep learning architecture that can be instantiated for different tasks. And so it's really flexible and can address many different tasks. For instance, if you want to train a regression model, you have to set it up so that, one input is category, one input is numerical, one input is binary, and you're predicting a numerical output. And so you obtain a regression system. Or if you want to do text classification, you have one text as input, one text feature as input, and one category feature as output, and you have a text classification system. For image captioning, you have an image as input and text as output. And the same is true for speaker verification, forecasting, binary classification. You can imagine that by combining the different types of inputs with different types of outputs, you can solve many, many machine learning problems with this architecture right out of the box. And now Travis is going to tell you how we are scaling this concept up to work with bigger amounts of data, and how we are bringing it to the market as an enterprise solution.
Thanks, Piero. So one of the powerful things about declarative machine learning in our view is that because you're specifying the what and not the how, we can do quite a lot of sophisticated things in terms of how we go about training the models that you specify in your configurations. And so we've done a lot of work over the past year or so on building out a very scalable backend for Ludwig built on top of Ray that allows you to scale up to arbitrarily large data sets and perform distributed data pre-processing using Dask, do distributed training, data parallel distributed training of the model using Horovod, and orchestrate the whole thing end to end by using Ray. And so the nice thing about this abstraction is that it doesn't require you to have to provision very sophisticated heavyweight infrastructure like a separate Spark cluster, a separate MPI cluster, et cetera. Everything runs in a common layer. And so the same code that executes normally on your laptop can be made to run in a distributed manner by just running it using Ray submit and then your existing Ludwig script or your Ludwig command line tool. So this is what we've been doing on the open source to make Ludwig not just a tool for research, but a tool really for production as well. But of course, there's more to productionization of machine learning than the model training aspect in isolation. And that's why we decided to put together the company Predabase that we're now working on. And so what we see as the value proposition of Predabase on top of Ludwig is that we take care of not just the kind of individual user training models problem, but we take a look at the end-to-end problem of how organizations and enterprises actually think about data flowing through machine learning models and getting into production and actually driving value. So that consists of primarily three distinct parts, which is connecting data from a database or data lake, using declarative model training with a Ludwig-like interface, and then productionizing / deploying that model for both batch and real-time prediction using a variety of interfaces, including REST and a SQL-like interface. So what we like to say about Predabase is that it's a low-code machine learning platform that provides high performance and high flexibility. And so one of the really unique things about the platform is because we have this declarative system that's very tightly bound between the model and the data schema, we have built this layer on top of the models that come out of Ludwig that we call PQL, which is a predictive query language that allows you to do very scalable batch prediction using a very simple predict the target variable given some data from your database or data warehouse, which allows you to really bring the machine learning to the data and put this capability in the hands of people who wouldn't traditionally be interacting with machine learning systems like analysts and engineers. It uses the same powerful and flexible Ludwig configuration that people in the open source community are familiar with, but with a lot of extra features built on top, and provides you state-of-the-art machine learning infrastructure without the need to build out an entire advanced machine learning infrastructure team. This is a serverless layer that we've built on top of the Ludwig on Ray open source product that completely abstracts away the complexity of operationalizing and productionizing machine learning. So the way that you can think about this fitting together is that you take your structured or unstructured data, which could be in a data lake or any structured data source like Snowflake or Feast and Tecton for a lot of the folks here, I imagine. You just connect to any particular data set, table-like structure that you have in those data sources. Predabase will allow you to build the models using our declarative interface, and then you operationalize those models using PQL on kind of the analyst side for batch prediction, as well as supporting full REST deployments that allow you to do very low latency real-time prediction. And then things kind of circle back and allow you to then iterate on the models over time and evolve them as things drift or as model performance degrades. So the whole platform provides an observability layer as well that gives you that MLOps experience end to end. So thank you very much for coming to our talk today. Please check us out on Twitter, our Medium posts as well, our website, and of course you can find the GitHub for the Ludwig project here as well. Thanks everyone.
Thank you very much.
Super cool, guys. And for anyone that has not read it, I highly recommend the paper that you put out about declarative machine learning. It is legendary in the field. So look forward to chatting with you on Friday and getting out the MLOps Community Podcast. Thank you, fellas. Appreciate it. Let's keep moving. Let's keep it cracking. Right now, we've got a very special guest. I mean, another MLOps community veteran and an author of an incredible book that you all should go out right now on Amazon and buy. Emmanuel, how you doing, bro?
Doing okay. I'm doing okay.
All right,
Well,
you
happy to
got a
be here.
lot for us. I'm going to hand it off to you. I'm going to put the link to Emmanuel's book in the chat right now. So in case anyone wants to continue their learning from him, you can.
Thank you. All right, let's get started. No time to waste. Okay, I think this should be the screen. Please unmute and let me know if you can't see. But yeah, today I wanted to talk about kind of something that's often forgotten in the kind of art of operationalizing machine learning, and that's kind of speeding up, making safe, and making regular the art of model deployment. This is related to some work that we did recently over the past year on my team at Stripe. And so I just wanted to kind of, quickly run through why deploying models often is valuable, and kind of the skills needed to do so, and a few tips that we learned along the way. All right. So we'll break it down into these three parts. One, I think there's a few things that are obvious about why you would want to redeploy models regularly, and some that are less obvious. So we'll talk about those. Two, I think it's kind of interesting because like the field of ML, as probably most of you know at this conference, is just like keeps eating other fields. So like, it used to be like just statistics, and then just modeling, and then data engineering, and then like ops. And so I'll talk about that a little bit. And then, last but not least, kind of just a few lessons learned from our journey of improving our process of releasing models. It's definitely not the answers to the question of how do you make model releases amazing, but there's a few pointers. All right. So what's the value of regularly deploying ML models? I think, traditionally, I would say, at least as like a data scientist, you often think about like, okay, I'm going to build this model, and then eventually I'm going to ship it. And those tasks are sort of like the large tasks, both the modeling, but then also all the engineering required to ship it. And often what gets left by the wayside is, okay, but what happens when we need to update the model? What happens when we have new features? What happens when we notice some drift? Like, how do we correct it? And so there's basically like 3/4 big reasons I would say you need to regularly redeploy your ML models. The most obvious one is drift. So for many use cases where you could continuously learn from the world, where you're learning something that changes, an example is what my team does at Stripe, which is fraud prevention, where people that commit fraud are always looking for new ways to commit fraud. Then any model that you train today will be obsolete tomorrow. The question is only like by how much will it be obsolete? And so here's an example kind of like on the right of a toy example. Of course, like, if you don't retrain, you're just slowly degrade in performance once you release your models. But if you retrain regularly, you can kind of recapture that level of performance. We talk a little bit about it on our blog, which I'll link at the end. But for us, we've realized that like for fraud prevention, for example, 1 month of staleness translates to roughly 0.5% performance drop. So every month that we don't release a model, we just lose 0.5% of performance. And conversely, if you just re-release a model a month later, you just got a 0.5% performance gain with kind of no effort. So that's one reason. The other one is sort of similar but more subtle. Even if it's not a slow drift of the world shifting under your feet, companies change, your users change. And so regularly you'll see that they change in subtle ways. Maybe if you launch in a whole new country, you'll think, oh, well, I guess I should retrain like our fraud models or our customer prediction models or, any other models. But, if like one of your users slowly has started like onboarding more people or like they expanded to a different geo or some subtle things can happen, which can cause your models to, slowly become out of date and eventually just become basically trained on a completely different distribution from what your inference is today. So here I have countries as an example. And finally, I think the last reason is kind of like the bottleneck. We'd realized that we'd optimized our experimentation enough that we could like make a simple change to like our data feature or our like data filtering, see that, oh, that's great, this change gives us like a 2% boost in performance, let's say, but then shipping it was weeks and weeks of work. And so in the end, like even though we had optimized like one of the iteration loops that you care about as an ML team, the other one was so much bigger that's why we chose to focus on that one. So if you can experiment quickly, it's great, but then you have to be able to ship quickly. And the sub part to that is if the model you're working on is important, you should be able to fix it really quickly if it breaks. And so deploying models should be something that you're able to do kind of quickly and safely. So what skill sets do you need to, regularly deploy models? We already said that, like to be like I guess a 10x ML engineer, you need to like know stats and like modeling and be a really good software engineer and be a good data engineer. So what else are we adding onto the pile? This is my mental model of it. Starting from the left, like to get a good model, you kind of need 90% data generation and cleaning and 10% modeling. And then once you have a good model, moving on to the middle, if you want to ship this model, 10% of the work was getting the good model. 90% that remains is now, relying on software engineering best practices. But once you've shipped the model, if you want to be able to reliably serve it and kind of update it, then all of that work that we're kind of going to talk about is mostly on the operational side. This is basically kind of getting to a level where you excel at running your training and evaluation pipelines and your deployment pipelines. So it's very operational work, but it has huge value. So, as I said, this is kind of a fuzzy problem, a problem that's clearly worth solving, but one where there's, I don't think, kind of clear best practices. So I'll share 3 or 4 tips, depending on how you count, that helped us along the route of sort of tripling the speed at which we release models and kind of capturing those gains I had mentioned, where our models are now always fresh. So one is, usually when people think about model training, they think about this box at the top right. They think, okay, well, I train my model. But really, if you think about the process of producing a model, it is a much more complicated and, in fact, almost a cyclical process where, first you kind of generate data, you filter it, you generate your features, you generate your training sets and your evaluation sets, you train your model, you evaluate it on said sets, you evaluate it usually for more than just kind of is loss going down, you evaluate it for business metrics. So you might have particular data sets that you want to measure performance on, then you deploy it, then you monitor it. And then usually you measure your model's performance in production, and very often that will feed into the data that you use to train your models, right? Maybe you'll notice that some examples are particularly hard or particularly easy for your current model, and you don't want to select them. So when we say reliably train models, really you should be able to reliably do all of this and do it regularly. And so our solution for this is to basically automate almost all of it. And so basically, what you kind of want here is can you have every single one of these tasks be a job that can be automated and that you can kind of kick off so that all of this runs without a single human in the loop? In our particular use case, we actually keep a human in the loop at kind of 2 spots, which is for deployment as a way to sanity check, yes, this look good, let's deploy this new model, and then to sanity check that we are indeed happy with production performance later on to make sure that we're not missing out on something. But essentially, the first step in kind of being able to retrain and redeploy models is for that whole process, to not have let's say a data scientist that does the feature generation themselves and goes in a notebook and codes a thing a one-off job, but to have all of this be automated. There's one more trick that we use to de-risk this automated pipeline, because once it's automated, you might be concerned about what could go wrong, and that's leveraging shadow mode. So shadow mode, there's a few blog posts that talk about it, but essentially the idea of shadow mode is that we also basically deploy not only just our production model to our production environment, but we deploy models that we're thinking about deploying in something called shadow. And so these models make predictions just like the production model, but we just store these predictions for later. And that allows us to really test models at the end of that pipeline, going back here before we deploy it. We deploy this model to shadow for a little bit, and then we observe how it behaves in production and verify that we're happy with it. So in summary, once you have this whole pipeline, once you have shadow scores, then you just automate it, or then you just schedule it. And so that's basically kind of putting it all together. The thing that's, I think, the most useful insight here is you can basically have this pipeline that creates models starting from data generation and does it automatically for you, let's say every week. And so let's say week 1, the first week it'll run. Then the second week, maybe you'll realize a bug. Maybe some other team changes some code, and all of a sudden you can't produce models anymore. And you'll immediately know to fix your pipeline so you can guarantee that you can continuously produce models, and that at any point you're ready to redeploy your models, to fix your models if they break, or to just kind of ship your newest changes to production. That's most of it. As I said, there's a technical guide with a lot more information. You can Google these 4 words, you'll find it, or we can paste the link as well. But yeah, that's it. Thanks, everyone.
Super cool, man. So continue the conversation with Emmanuel in Slack. And he also speaks French in case you want to just ask him the question in French because it's your native language. There we go. We're going to keep rocking. Drew, I see you. What's going on, man?
Hey, how are you? Happy to be here.
Doing well, dude. I am excited to have you on. For those who do not know who Drew is, he's a co-founder of DBT Labs. And actually, I'm going to let you go so I don't take up too much time talking. And then if we have a minute, I'll chat with you after your presentation.
Okay, groovy. Let me share screen. We'll jump into it.
Nice.
Hope that's coming through okay.
Yep.
Oh, great. So yeah, my name's Drew Bannon. I'm one of the co-founders at DBT Labs. You can find me on Twitter at Drew Bannon. And just one point of clarification, I think the agenda says that I'm the CPO here. I'm actually the former CPO here, which is great because as CPO, I could never join events like this and give talks about things like semantic layers and feature stores. So really excited to be here and looking forward to the chat after in Slack. Let's start with the question. What's a feature store? Seriously, what's a feature store? Please help me. I don't know. I'm mostly kidding. I did do my research. I read up on feature stores ahead of time. But the thing I want to come clean about really at the front is machine learning engineering is not my background. It's not my domain. I come from the sort of data analytics, data warehousing, BI reporting kind of domain. And the thing I want to kind of dig into today is the rise of the feature store and the rise of sort of a similar, I think, technological innovation kind of in the BI and analytics realm that we call a semantic layer. So semantic layers are really like in right now. People in the BI and analytics sphere are talking about them. And the big ideas at play are that you want to define your data sets and metrics. You want to map out how they can relate to each other. And then you want to translate like high level semantic queries into SQL for execution. So some examples of metrics that you might want to define once and use everywhere is revenue by country or average revenue per customer. These metrics should be like very precisely defined, that they will probably change infrequently, though they do change sometimes, as we'll see. And so managing these metrics is kind of deserving of sort of these new technology innovations. So like, why is this important? Like, why is it hard to calculate revenue? This is sort of the canonical example. You might think revenue is easy to calculate. You just sum up, order totals in your orders table and you get revenue. But in practice, you need to make sure to exclude orders that are returned. You need to make sure that you subtract out tax paid on the order because that's revenue for the IRS, not revenue for your company. And then invariably you get quirks like this where, up until today, you recorded order totals in pennies and cents, but now it's dollar values or vice versa, whatever it is. And so you sometimes see quirks like this where the source data isn't actually representative of kind of the reality on the ground. You need to apply like business logic to sort of convert that data into information. So I don't want to like belabor DBT here, but just to show you what this looks like to make it concrete. Basically, when you write a query, you could write out this thing, or you could say select star from this metric called revenue by day, and DBT can compile a much bigger SQL query for you. So in terms of like visualizing this thing, I think about it kind of like an iceberg. This pink thing, like this is a real view of our DAG at DBT Labs and how we track our objectives and key results. So this pink thing is a metric. It's weekly active projects for us, which is a metric we care a lot about. And that's like the actual aggregation. It's like the sum of users that had activity in the previous week, whatever it is. But that actually misses a lot of the logic that feeds into calculating this metric correctly. So all these blue nodes here in this DAG are sort of logic that we apply to source data to like join data sets together from different data sources, like aggregations, filtering, whatever it might be. And so it's this whole chain of all the logic applied to source data, plus the actual metric definition that kind of composes the final metric. So like, I'm sort of wondering if this sounds familiar to you, right? Like I'm talking about business metrics and BI and reporting, but from reading about feature stores, it seems like kind of a similar concept, right? Like there's only one way to define revenue. And in a similar way, it's like, there's only one way to define if someone is active or not. That might change over time as your product evolves or new product capabilities roll out. But if you have many people on many different teams that are all kind of accessing the same like features or metrics, you want to make sure that these things are consistent, that work isn't being repeated, because if you're repeating work or like copying and pasting code, things like that, then inconsistencies can arise and you can get sort of invalid, incorrect data. So the theme here that I think links together the semantic layer concept in BI and analytics with like feature stores and sort of ML engineering is this idea of standardization, right? Like whether you're creating inputs for ML training and serving or outputs for analytics and data science, you want to make sure that when you invest the energy to define these constructs, features, metrics, whatever they are, that you're kind of doing that once, that you're doing it correctly, and that you have a good way of evolving this logic over time as sort of requirements and the product experience invariably changes. So I would argue that sort of features in ML are akin to sort of what we call dimensions or maybe metrics in the BI world. This is sometimes true. I don't think it's always true for reasons that I've read about recently, but I'm kind of curious to hear everyone's take on. So this is kind of my view of how to bridge these two worlds. And this is like more of a mental model than an architecture diagram. I'm not advocating for any technology in particular, but it's sort of how I think about it, right? The fact that the data warehouse is front and center here, or it could be a data lakehouse, of course, is sort of a signal that this is very much my background. But the idea is you're going to have all these sort of transformations in business logic to apply to your data to sort of make sense of it. From that point, you have this like shared logic, and then you can use that to make dashboards and reports that like business users kind of consume and understand. You could also take these like bits of logic and use them to power like features that you use for machine learning. And the really cool thing about sort of having a shared parent between these two use cases is that you get consistency and you get reuse. And so investments that your BI or analytics team has made to model revenue or product usage activity, like they could be leveraged for feature engineering and machine learning and kind of vice versa. So that's kind of what DBT is all about at its core, is helping get data engineers and data analysts collaborating with shared tools. And I just can't help but wonder if there's an opportunity for us to do this with machine learning engineering and BI, and if there isn't like a common use case kind of that could be shared here. I want to talk about when this might not work well, and I think it's one of the big kinks in my plan, and it's something I'm interested in learning a lot more about. So I was reading about data leakage, and the funny thing to me reading about data leakage is like, in my world, we call that analytics, right? It's like take all the data that you have and mush it all together and show the most accurate information you have, like now at this point in time. There are cases in analytics where you want to know, like, what did we report as revenue a month ago? Sort of excluding new information that's come after the fact. But I think this is one of the places where feature stores and semantic layers kind of diverge. And I am wondering if there's a sort of model that we could employ to help kind of bridge this gap. So I thought that was interesting. I think that's one of the problems that we have to kind of figure out together. But I think that if we can solve this problem and figure out how to unify machine learning with analytics and BI, it'll actually help people become a lot more collaborative. It'll help teams work together. And again, just create like more precision and consistency for our reporting or machine learning or whatever it is. So here are kind of the questions that I have at this point. I regret that I don't actually have answers for you. But sort of at the outset of this, I asked the question to myself, like, are semantic layers and feature stores like the same thing? Are they going to collide? I think the answer is like, no, not really. There's like different audiences for these two types of tools, different use cases, different constraints, of course. So I don't think there should be any worry about these two things crashing into each other. But can we learn from each other? Like, yeah, definitely. I think we really can. I think that the sort of analytics engineering community has learned a lot about how to be collaborative around creating these shared dimensions and metrics and understanding how to work with the business to make sure that we understand sort of these definitions precisely. And I think the machine learning engineering community has gone really deep on like registries and sort of defining things once, using them in many places and leveraging that engineering background. So in terms of like, where do we start? Like, how do we answer these questions? I'm going to pop into the Apply conference channel on Slack, and I'm excited to talk to you about if any of this is resonant or if you think I'm way off base here. So I just want to say thanks to everyone for letting me come talk to you today. I'm excited to chat.
Dude, great. I love the vision. It's super cool stuff. I just have one question for you. did you like purposely set out? I mean, you created a bit of a cult with DBT.
Oh,
People are diehard fans when it comes to DBT. And if you don't believe me, somebody just create a fake Twitter account and just start talking about how you don't like DBT and watch how many people attack you on Twitter.
No, it's not like that. In fact, quite the opposite. I think the thing that's so cool about the analytics engineering community and DBT's place in it is that everyone has like great intentions and is full of love and experience, and they're generous with it. So it's actually a great community, and we'd love to have more folks in it. So
yes,
if you're interested,
I will second that. I didn't mean to come off as like, no, people are super toxic. I just think you've done a great job creating a community that is very helpful, and they love the product so much. And that is a feat unto itself. So congratulations. Everybody that wants to continue talking to Drew, head on over to Slack, ask him questions, and we're going to keep it moving. So I see Yushen. Are you here with us? What you got?
Hey.
Yes, there you are. So you're the VP of engineering at Instacart, and you've got a lot to talk about. We're just going to get right into it. I'll let you share your screen, and then I'll ask you maybe a few questions in those seconds in the overlap between you and Donnie, the next talk.
Perfect. Sounds great. Hello, everyone. Pleasure to be here to discuss engineering for applied machine learning. Before you all start to look for the presentation screen, I actually don't have slides. We just have a chat. And I also start by saying it's my first time joining this conference. It's super cool to hear all the great work that were done by other presenters. It's humbling to hear those ideas, a lot to discuss. So my name is Yu Chen. I work for Instacart and support our fulfillment marketplace organization. My teams are responsible for developing technologies to power a balanced, sustainable, and resilient marketplace. And what that means is we want to efficiently meet consumer demand and make sure that your grocery gets delivered quickly and efficiently. We want to empower our shoppers and make sure they get meaningful work and earnings opportunities on the Instacart platform. So machine learning, along with technology innovations across system engineering and operations research, are the mainstay of the work we do. We use machine learning to drive a wide range of marketplace opportunities. For example, predictive modeling is used extensively in our systems. It is super important that we know, for example, how long it's going to take to fulfill an order by modeling how fast can someone drive to the store, pick up all the items in the order from the store and get those delivered. That way, we can promise the fastest and reliable ETAs to our consumers when they check out, and also dispatch orders to our shoppers at the right moment to make sure that they will arrive on time. Forecasting is another critical component of our system to ensure our users can order whenever they want to at the speed they desire. It is important to estimate how many orders we will receive at what time, and also at which store, so we can plan ahead with shoppers on the platform. So Instacart is a continuation of my long-time passion for applied machine learning, which actually started in a very, very different domain. It was in 2009 when I was a PhD student collaborating with Google Research in the area of speech recognition. So unlike I think I'm, as I mentioned, I didn't have slides, so it would just be chatting, with my screen. So unlike today's speech recognition products in 2009 were a little frustrating to use because the recognition accuracy was far from perfect at the time. So there were lots of efforts put into improving speech recognition at the time. One of those efforts was to evaluate the use of deep neural networks. I did not participate in that effort directly, but was very fortunate to witness the tremendous excitement when deep neural networks saw a huge improvement in accuracy compared to state of the art at the time. It was acclaimed by the team as 10 years of speech recognition R&D launched at once. It was fascinating to see how machine learning algorithms, data, and engineering really came together at that time to advance boundaries of technology and enable transformative product improvements. Clearly, this improvement in speech recognition would not have been possible without the core innovations in deep learning algorithms. The amount of speech data was also critical. As we all know, machine learning isn't very helpful without data. But the part I was fascinated most about was the innovations in engineering system that made it possible to train such large-scale neural networks. And in fact, an entire array of engineering tools and systems have been invented since then to make ML development across many applications like those we heard today. So personally, I have worked on ads, search, recommendation, and now marketplace at Instacart. And in every single one of these applications, I've seen the success formula of algorithm, data, and engineering to drive business impact. The algorithm and data often vary across these applications, but I've found that the engineering challenges are often very, very similar across these domains. So today I'd love to just share one aspect of engineering problems for applied machine learning, which I call idea to result. So what is idea to result? It is the time it takes between you wake up in the morning with an idea to improve your machine learning model to the time when you know that the idea is good. So clearly, we want idea to result to be as fast as possible. So what gets in the way of us getting results quickly? For example, say you work on a recommendation and wake up with an idea of a new user feature that you think will improve your recommendation results. However, that feature may not be available in your feature store, and perhaps it's not even logged in the production system. You end up spending time writing feature extraction pipelines, or even worse, sometimes having to wait for the production logs to gradually accumulate through logging, which would take months, before you can even start to train your model and test the ideas in experiments. Or imagine you read a paper about a cool new ML technique that claims to be effective in your type of ML application. However, the ability to train and evaluate this kind of ML model may not be supported by the current ML workflow you have. So you may have to file a request to have that implemented, and the ML infrastructure team may have to prioritize that in some way, which causes further delay. Sometimes the bottleneck is neither in feature engineering nor ML workflow, but the fact that you need to run live experiments to gauge success of your idea, which requires you to go through a full productionization cycle of a test model and wait for experiments to come in, and this would take at least a couple of weeks before you can get the results. So this list can go on and on because every application and system are different. But in my experience, they all tend to be things we can improve through analyzing the engineering systems that work between your idea and getting your results and make them work faster. So why does idea to results matter? Well, all engineering problems become easier to solve if we can move faster. For most applied machine learning problems, we take an iterative approach by constantly testing new ideas. So the speed at which we can iterate on our ideas, really governs how fast we can learn and how much impact the team can generate. Faster idea to result also means we can catch bugs earlier. Have you had experience working through weeks to train an ML model, and then more weeks to get the experiment data, only to realize that there's a bug in your feature extraction code that made all the results invalid? While we don't have many MLOps tools to catch these issues automatically and minimize them, it is still much better if we can catch them sooner. Also, depending on your ML applications and your business environment, sometimes there are cases where you have to make model changes very quickly. For example, there may be a need to assess a new data provider where you need to make a business decision in in a couple of days or weeks. And being able to get from idea to result within reasonable time frame really becomes critical in those scenarios. If you lead a applied machine learning team like I do, idea to result is also an important gauge of productivity of the team. And productive teams are happy teams. And it is fun for machine learning engineers and data scientists because we get to test ideas faster and then get the feedback loop quicker. It is also fun for backend and data engineers on the team because through the lens of idea to results, their work is truly the enabler and force multiplier to all the impact that the team is having through these ML ideas. So we talked about what is idea to result and why that matters. How do we make it useful? The first step is to start measuring it because we can only improve what we measure. Every ML system probably has a different bottleneck. So go identify those. And very likely you would be pleasantly surprised by how much faster you can iterate through ideas by investing in just a few new tools and infrastructures. If you're a machine learning engineer or data scientist and find yourself waiting weeks or even months to test an idea, don't assume it has to be like that. Surface what takes time between your idea and the results. Discuss among your fellow engineers to come up with solutions. For example, oftentimes a live experiment takes too long to run. And this may be the time to think about developing offline simulations or offline metrics to estimate production impact of your model without having to run a live experiment for every new idea you have. If you are a backend or data engineer, your work is probably already making idea to results faster. This is truly impactful and high leverage work, and I'm sure there are a lot of opportunities that you can drive even further impact, through these lenses. With that, I think I'm getting pretty close to my 10-minute mark, and thank you all very much for attending this. I hope this is useful, and you can tell I'm very passionate about this area on the intersection of engineering and machine learning. And please don't hesitate to reach out, and look forward to chatting more with you.
Awesome. Sweet, dude. And I appreciate the fact that you took the contrarian approach and went with no slides. That's also something that I enjoy doing. So I'm going to give you props there. We've got one last talk. Feel free to ask Yu-Chen any questions that you've got, of course, as usual in Slack. And for our last talk of the day, Donnie Greenberg, where you at, man? You around?
I'm here.
There he is. Roll call. What's up, dude? How you doing?
Doing great. Wonderful
So,
talks.
for those who
also
do not
love
know
the
Donnie,
slide-free approach.
he is a product manager lead for PyTorch at Meta. I can imagine a few of you out there have heard of PyTorch before, if not, are daily users of it. So, Donnie, you've got the honor of wrapping this up. We saved the best for last. Go ahead, take it over.
Yeah, it's great to be here. And I'm taking the opposite approach, the slide heavy approach. So I'm going to go really, really fast, and I'll share these afterwards if folks are interested in looking at the code samples in more detail. So what I'm talking about today is the next generation of data tooling in PyTorch. And you can sort of ask the question, should we have data APIs in PyTorch? And we did ask that question, and actually it was a very long discussion. So what it basically came down to is that our mission is to accelerate AI in PyTorch. And as you might realize, data loading and processing has actually become a very large share of user time over the last 5 years, or considerably larger than it once was. Another reason why we decided we were going to begin attempting to begin investing in data APIs in PyTorch was that our bread and butter is basically bridging AI silos. And certain open source maintainers are actually asking us to step in and introduce APIs that can bridge the loading and processing silos in open source. And we're in a sort of unique position that we can invest a few years in trying to create a standard which is so wide that it can span the entire field across research and production, across computer vision, recommendations, NLP, various subfields, and produce something which is, very extensible, but still performant. And this is basically a very risky bet. And so that's essentially when we typically step in. We know that we can fail fast, but we can also spend like 3 years attempting to build an API, which is like ultra generic. And so to kind of get into more of the actual detailed nuts and bolts, so breaking data loading and processing into two. What we were seeing in data loading when we kind of embarked on this journey was that the PyTorch data loader, which has kind of been the thing that was appeasing the community for a long time, it was built at the beginning of PyTorch, was outdated and inflexible, largely because it was very feature bundled, like batching, shuffling, caching, all this stuff. I don't think caching was in there. All this stuff was basically built into a single monolithic thing that could just sort of allow you to get by in data loading. There was no multi-threading, and it was basically built around map or index access data sets. At the same time, there was huge innovation in data loading out in the open source. Lots of honorable mentions. So basically everybody who wanted to innovate in data loading had to just fork the PyTorch data loader, introduce their feature, and those loading features were then just incompatible with one another, right? Each new innovation was just in a separate data loader. And then similarly, you had constant duplication of the kind of table stakes primitives that were not the innovation that were being introduced in that particular data loader. And so, and also these sort of table stakes primitives were rarely robustly implemented. There are probably 1,000 HTTP handlers and AI scripts out there, and obviously they're not all handling, all the different errors properly and everything like that. So our approach is basically to introduce an extensible, like an ultra wide open extensible loading standard to replace the data loader in PyTorch and allow that to be basically the sort of inception point for a new interoperable modular community of data loading primitives. And so this is not a simple idea. It's also still quite risky, but basically the data loader has all these sort of features built into it. We basically broke it out into this new type of a graph of loading primitives called data pipes, and then a very thin graph handler to ingest that graph. And the data pipe standard is like the most flexible we could possibly make it. It basically takes a Python iterator, an iterator over Python objects to an iterator over the Python objects. And it's easy to say that, but actually to make it performant is a much harder problem. But basically, shuffling, batching, collation, mapping, filtering, et cetera, all these are basically just now data pipes. They're not things that would happen in the data loader. And so then we basically started this new project in PyTorch called Torch Data, which is a new corpus of standard data pipes to sort of seed this ecosystem and introduce those table stakes primitives, but implemented robustly. And all this stuff is extensible and replaceable by users. So we have 56 such data pipes now, anything from IO, like typical HTTP sort of requesting of a data set. We have a Google Drive requester in there, extractors for CSV, Parquet, XZ, Zip, et cetera. And then all the kinds of normal munging you'd like to do to a data stream, shuffling, sampling, collation, mapping, et cetera. And this just continues to grow. The exciting things are, one, that this whole system is streaming first. So almost all the above has been made streamable, including many of these extractors. So you can like stream in JSON without having to download an entire JSON data set at once. It's non-BC breaking, which is frankly shocking to me that was going to happen, but very exciting. It's also extremely open and extensible. So if you decide you don't like the shuffler in the default data loader graph, you can replace it with your own. We have projects working on TF record loader because people love TF record, and actually AWS just released an S3 reader data pipe, right? Like standard kind of thing. You have an HTTP reader, you probably want an S3 reader. And so this is all extremely early. We have a live beta release coming out in late June, but I encourage you to take a look. Here's just a quick code sample. You can see basically that the code allows you to either build up an object-based or declarative set of graph of data pipes, or you can build them up in this functional format. And I'll leave this again in the Slack. So now to talk about data processing. So problems in AI data processing were somewhat similar, but look a little bit sort of from a different direction. So we also kind of have lots and lots of pre-processing functions similar to like data loading primitives out in open source, but these are basically incompatible with one another in a different way. Namely, they don't have a common in-memory format, right? So like you could be using a normalizer, a text normalizer from this place and a tokenizer from this place, and they could just be working on, one of them could be working on Unicode and the other one could be working on ASCII. Like what, there's just no standard whatsoever, and this created lots of problems and sort of conversion overhead. But then also there's no common API layer. So like one of them takes a tuple of dict and the other one takes a dict of tuple, and ad absurdum, like it just was sort of a constant translation if you were trying to use data tooling from, or data processing tooling from more than one place. Also, structured data exists. So at the beginning of PyTorch, our problems fit the sort of image comma label bucket more cleanly, and now they simply don't. I mean, they didn't really then, and they really, really don't now. So like NLP, multimodal, these things don't, tabular data just does not have a data API in PyTorch. And you get these messes of dicts of tuples and such just to do basic things. And also we recently open sourced Meta's recommendation systems infrastructure as a PyTorch library called TorchRec. And we just could not do that with a straight face without having support for structured data in PyTorch. You cannot do recommendation systems without good structured data support. Also, people love TF record, but it's sort of a walled garden because it doesn't have an open in-memory format. And then again, we've seen some amazing innovation in data processing, but it's mostly sort of in silos. Like for example, NVIDIA has a library called cuDF, which allows pandas-like data processing on GPUs. Koala is a similar pandas-like data processing on Spark. Slightly different pandas APIs, right? So you can't just change over the code from one to the next to change out the backend. Honorable mentions elsewhere also. So along a similar theme, we are working on an extensible data processing standard in PyTorch. So if you think about what PyTorch is at its core, it's not really you don't have to look at it as a quote unquote AI framework down to its guts. It's really a standard front end and in-memory format for tensor processing. And so, you can use the same API and the same in-memory format for all the different operators you get for tensor processing out in the ecosystem, and they all work together and they chain together nicely. And then we have this registration and dispatch system to allow any third party to say, okay, to register their operators to be runnable easily with PyTorch. And then we've made that batteries included for AI usage, introducing things like autograd and lots of default functions and things like that. So we can do the same thing for data frames. So Torchiero is a very, very early alpha project in PyTorch that is essentially akin to, Torchiero is to pandas as PyTorch is to NumPy. So we basically created a standard processing front end or standard data frame front end, which is multi-directable to different backends. So the default backend is a high-performance CPU engine called Velox, but you can do funny things with it. You can change over to graph mode to basically trace your data frame operations that can then be optimized and lowered into like a data warehouse. We are working on targeting GPU via NVIDIA's cuDF, targeting Spark and other runtimes. Torchiero is ultra open, so we chose Arrow as the in-memory format because essentially everybody asked us to. It seems to be the thing that a lot of people like for open in-memory structured data processing. And there's no dependency on PyTorch, which is a very interesting thing. So actually Hugging Face came to us and said, or we were talking to Hugging Face about this project, and they basically said, it would be really lovely if this didn't depend directly on PyTorch, so we could use it for processing across all of our recipes if we were to use it, and not only use it for the PyTorch recipes, we could use it for TensorFlow, and we don't have to implement these things sort of separately in the PyTorch and TensorFlow silos. And we said that makes complete sense. The processing step is mostly orthogonal, other than correlation where you translate the data into tensors, than the modeling step. So that was actually a decision that we made to make Torchiero independent of PyTorch in a sense. It obviously works seamlessly with PyTorch. It works seamlessly with Torch data, and it's also quite early. So in the we're targeting a beta in late June. Targeting, I think, either alpha or beta in late June. But you can already look at it. It's an open source. Here's a code sample. It looks a lot like Panda, so I won't go through it. But you can send it to a different backend. Thanks very much. If you have ideas or questions, or you want to integrate with Torchiero, you have some project which would be nicely represented as a data pipe, definitely feel free to email me, or if you just want to chat AI data.
Excellent stuff, Donnie. I appreciate you bringing us home. This was great, man. So that is it. We have some good news and we have some bad news. First thing is that we are not totally finished because tomorrow we'll be back at it again. And you can see all those instruments in the background. I'm going to be playing some of them. Not sure if that's going to cut our attendance levels in half or not, but we're going to have some fun. We'll keep the party going. And if you would like, you can still enjoy some of the workshops. So there's a feast workshop and there is a Ray workshop that are happening right now. You can check out the links to that, and there's Slack channels dedicated to those workshops. So get involved if you want to keep this going. There's also a huge ask. Well, it's just for me, this will be the best thing that I can ask you to do right now, and that is you fill out the survey that tells us what we can be doing better on this event. What would you like to see more of? What would you like to see less of? And be honest. If you want less of me, it's all right. I understand. I got thick skin. And that's about it. So I think I should probably hand out some swag to finish this off. Like, where are we going to be if I don't hand out swag to end it, right? So last thing now, let's get the swag going. And I'm going to just go back to this website of ours. If you did not take a cheeky selfie, go ahead, click agree, take a selfie. I'm going to allow that. And look at that. Cheese. There we go. So where's the speaker gallery? You've got a link for it in the Slack. And there we go. That is me. Oh, man. So many good things that you can do, but I'm going to do that. Let's give away one last thing of swag. Who is that with the cool hat? I'm jealous already. Who is that? Oh, man. These are some solid photos. I haven't looked at them in a minute. What is this cat? Wow. All right. So what is this cat is angry. All right. So I'm going to have to, wow, this is making my life hard. I think we need to give some swag to the horses just because it's unique and there's only one thing of horses here. Yeah, there's only one horses. So who's the horses? Please reach out to me. You get some swag. The mad cat, I just can't look at that and not smile. So you also get some swag. And last but not least, whose is this? You get some swag. So there we go. Those are the last 3 swag giveaways of the day. And we're going to finish it up here. Please fill out that survey that we sent your way. And then we are going to end it like that. Hope you all have enjoyed yourselves, and we'll see you tomorrow. I've got some songs that we'll be playing. I want you to help me write some songs. And I mean, we've got a ton of great speakers too, not to mention that. So peace out, everyone. Have a good night or day. Enjoy the live meetups too, if you're going to that.
Exactly where I want.